and we want to start exactly by in next 1 or 2 minutes. Dr. Bhandari would like to see his slides. If you can show
Yeah.
him his slides.
Hello, ma'am.
Ah,
Yes,
yes, sir.
please go ahead.
So, sir, we will, sir, sir wants to take trial for his representation. Yeah, I think we can see it.
Bhandari, sir, your slides are.
See,
Yes, I am able to share the screen.
yeah. So we'll
So-
let's formally start, sir.
Yes, can we start, madam?
Yeah, we'll start. I'll
Yeah.
just
Okay.
yeah. Are we live, Yogesh? Yogesh, are we live now?
Yes, ma'am. Yes, we are live now. We may start now, please.
Yeah, great. Good morning, everyone. And this is Manjula Yadav, Education Officer from Nehru Science Centre. I'm very sorry for the sore throat that I'm having, but it's great pleasure to have you all here on this room, sir. Because it's all great stalwarts here on the same forum, and it's going to be a delight for everybody, all those who are attending this program offline as well as online. So, the program is jointly organized by Nehru Science Centre and also the Akash Ganga Centre for Astronomy and AAA the Metro Astronomy Association Mumbai and sorry Bangalore Science Club also. So there are plenty many people who put in effort to make this program happen, and I should thank the rules. I request him to take the proceedings, and I thank Professor Bhandari sir for joining us. I hand over. I hand over it to. Hello, can you please mute yourself? All others are requested to mute themselves.
Yeah.
Over to you, Adur sir.
Okay.
For further proceedings.
Thank you, ma'am, for all your support from Nehru Science Centre. And this is the fourth time we are conducting this program from Nehru Science Centre. And I'm very happy that we have been able to do this program for past 7 years. From 2017 onwards, we began. UN had started this program of International Asteroid Day in 2015. And since then, we began this program in Bangalore Planetarium, Jawahar Planetarium there. And now this program is conducted probably in many cities also. So I'm very happy. And I give all my reverence and thing to Professor Bhandari sir. Without his support and his help, we could not have been able to do this. I have known Professor Bhandari from his TIFR days and then in PRL, and he has been such a gem of a person for me that a dumb person like me also could take interest in asteroids and now learn under him. So today this session we are going to have Professor Bhandari to open this talk, and in fact it will be too much for me to tell. He is like a son to us. He can give us light. So I think he will be the best person to talk about asteroids for life on Earth. And I look forward, Professor Sir. Namaskar to you once again. I'm so happy that you are here to inaugurate this program. And we will have a session until evening also, until 6 o'clock, we hope. And this is the program that we are looking forward to. Thank you, Professor Bhandari, and we will look forward for your talk.
Hello.
Yes,
Bhandari sir, are we audible?
yes, yes.
Okay. Sir,
Should I start now?
Yeah, please.
Okay, thank you. Thank you, Bharat Atur, for your kind words, very kind words, actually. Uh, I want to talk today about asteroids and their importance for life on Earth. Actually, about a decade ago, when it was declared as Asteroid Day, I was wondering what is so great about it. And if in one sentence I ought to tell you why this Asteroid Day, then I think I would say that is a matter of life and death for us. It is because of asteroids that we are here on Earth, and because of asteroids that life has been, originated here or came here, and it is because of asteroids that life gets destroyed on Earth. So it's very important. And why this 30th June, you all know, because the great Tunguska event in Siberia, I'll talk about it a little bit, was on 30th June 1908. So that is a very strange. Actually, even today, it is a very mysterious event. We don't understand it. But that is how this Asteroid Day was named 30th June, selected. But I ought to tell you also that the big event of the, disappearance of dinosaurs, that was about 65 million years ago, that also occurred in the month of June. We don't know exactly which year, but some scientists act like, they decode the event, and they came to the conclusion that it was in June that year, some year, that the asteroid or a comet struck the Earth and destroyed about 70% of life on Earth. So actually, when you look at the solar system here, you're all familiar with various planets, starting from Mercury to Neptune and so on. There are two belts here. One is the asteroid belt, and the other one, that is between Mars and Jupiter, and the other one is Kuiper belt. But rest of the space looks empty, but that is not correct. Actually, it is full of things, dust, comets, small bodies, and so on. So I'll try to bring out the importance of this asteroids. And, I'll cover a few points which I have listed here. Why Asteroid Day? I already talked about it. And then we have tons of cosmic dust from interplanetary space falling on Earth every day, more than 100 tons a day, for example. Then meteorites, there are about maybe 1,000, 2,000 meteorites fall on Earth every year. Asteroids, once in a while, asteroids also fall, and comets. Just now there is a comet in the sky, you can see it. Now, why they are important for life? Because they are supposed to, or they are known to contain volatiles, and things like phosphorus, water, most of our ocean, and the water on various planets, including Moon, which we found on Chandrayaan-1, was also, brought in by comets and asteroids. So not only phosphorus, I'll show you how many compounds and elements are brought, and they are responsible for life. For example, the mobile life, the life was immobile. But when mobile life started, there was a big input of phosphorus on the Earth about 550 million years ago. Then, of course, they have a lot of destructive power. you all know the energy is half mv square, and velocity is very high of these asteroids. They go up anywhere around 11 to maybe 30, 40 kilometers per second. And comets can go up to, 70, 80 kilometers per second. So when there is a head-on collision with Earth, which is moving with velocity of 30 kilometers per second, then of course, it compounds. So a lot of destructive power they have. The point I want to make is that nature has chosen the same agency, meteorites, asteroids, and comets, to sustain life, to originate life, to bring life on Earth, as well as to destroy life on Earth. So it works both ways. The small ones give us the essential elements and compounds, organic compounds even, and the big ones really destroy the life. And that is why it is important for survival of life on Earth. Now, recently, as you must be knowing, NASA has brought on Osiris X mission some samples of Bennu asteroid, which is very close to Earth. One day it is going to fall. Someday, we don't know exactly when. And this is very similar to a meteorite which we studied, which fell near Jaipur in 2017. It exactly looks like that. I'll show you some pictures. And of course, I'll talk about Tunguska, after which this date was selected. And we'll talk about the Cretaceous Tertiary boundary when the dinosaurs ended. And of course, the big question is, what can we do about it? So there's some pictures of meteors, you know them. And this is a picture I've taken from Mount Auku Observatory of the Leonid shower, this big trail you see. There is one which fell on Earth on Valentine's Day, I think 2013 or something, in Russia. And it created a crater which you can see here. So meteorites come in all shapes and sizes, about fist-sized meteorites, few kilograms. And they bring a lot of material. They are iron type, stone type, and stony iron type. These are the three major classifications. So you see a lot of debris falling. We are unaware of it, but some of us have gone there and collected dozens of meteorites in India, because India is very ideally situated with a lot of population, so nothing goes missing. Of course, something may fall in oceans and some may fall in Himalayas, but many meteorites are recovered, and between 1980 and onwards, we have collected some 20 meteorites from Rajasthan and Gujarat. So, just to give you an idea, meteorites are somewhere here, they fall every month, every other day. Bharat Adur has been, having a camera, and there are many people. We have an asteroid, we have a astro enthusiast group which goes and looks for meteorites. Every other day you see a meteor trail. Hiroshima is somewhere here, 20 kilotons or something. So that probability is very less. And as the size increases, a typical nuclear bomb is here, what we have today. And, the biggest nuclear bomb is here. So they are nothing compared to asteroid impact. The energy, of course, it occurs very rarely, maybe once in tens of million years, 100 million years. And Tunguska is about here. Such an event occurs every 100 years or so. So the last one fell in 1908. It is about time we have another event. So you see, bigger the body, lesser is the frequency, but more catastrophic is the effect on Earth and on life. So this is a picture. I think India, we have a lot of erosion, weathering, monsoon, just now rains everywhere. and hot temperature. So most of the craters are erased, but a few are preserved. And we have, this is Lunar Lake, you must have seen, very close to our Ajanta caves, famous Ajanta caves. If you have not seen, I would urge you to go there and have a look. About a couple of kilometers wide and quite deep. Now, of course, it is full of water because somebody constructed a dam there. But when we first went there, it was empty and we could go down to the bottom. There was a temple and so on, and we collected some glass samples. And in PRL, our colleague Sen Gupta and others, Ashok Singh, we dated that glass, and we got an age of about 46,000 years. So this is really old. But the importance of this crater is that it is formed in basalt, same as that on Moon. You know, Moon has a lot of basaltic terrain. So we wanted to see what is the effect on, Moon-like target. Then, of course, many others were discovered. Dhala is one. Kaveri crater, you will hear about it later on in this session. Then we have Luna crater in Kutch, which is being debated very heavily. So there are lots of craters, and there are some in Himalaya. Some people are looking at satellite images to identify craters. So few of them are definitely like Lonar, Ramgarh, Dhala, Kaveri, and all that established. Some are still being debated. So we are lucky actually way that we have the umbrella of the thick atmosphere. So most of these things burn and don't damage. Otherwise, Earth would be like, or even worse than the Moon, pitted, cratered all over the place. So this is the famous Tunguska event of 30th June. It was, they say, it is a guess. As I said, it's very mysterious. About a 40-meter object disintegrated in the atmosphere. So some people say it was a comet because they have not found any meteorite in spite of very detailed search, very thorough search. Only evidence is these trees which fell and the eyewitnesses. People observed something, sound and impact and, seismic waves and so on. So there was a big event, and some people say it was even a black hole or something like that which hit the Earth. So, such things on a large scale can destroy life on Earth. I'll come to that point later on. This is the 65 million year old event when dinosaurs roamed the Earth, but they got destroyed. And we found two sites in India, one in Anjar in Kutch, and one in Meghalaya on the other end of India, in the eastern part, where we have evidence that the debris of impact of this asteroid or comet fell all over India. So this found in, I think, hundreds of sites now in the world, because we can distinguish. See, Earth doesn't have much iridium, osmium, gold, platinum, but these meteorites have maybe about near to about 1 million times more. So you can easily identify that this debris is due to meteorites. They have even identified this crater under the sea in Gulf of Mexico 65 million years ago by gravity anomaly. This is the crater here on the right-hand side, and this is where the impact took place. And there was some doubt about when exactly it fell, but we could date it from Anjar site because there are 9 basaltic flows which are dated, and it fell after the second flow. So we know the age. Now, comets, they give life. As I said, they bring water, organic compounds, and so on. And they also take away life from Earth. So many comets have been studied, and organic compounds, even such complex compounds like glycine, have been found there. You see, as I said, there are, I think, more than 250 craters all over the Earth. They have been identified, but India, we have only few, as I mentioned, because of our weather condition, our erosion, temperature, monsoon, and all that. But you can find many in Australia, in North America, and in remote Europe, and so on. So we are lucky that we have atmosphere, but the big ones will survive and create havoc on Earth. Before the West realized that these things come from outside space, Varamihir, in about 6th century, he, in his Brihat Samhita, he mentions about meteors, thunderbolts, lightning, shooting stars, ulkas, comets, and so on. And we realized here, but we, of course, got a little stray because this was all done for astrological purpose, not much for astronomical purpose. But I would say that this was known in India for a long time. And Jaidev, you know, the famous poet who wrote this poem in 12th century, Jai Jagadish Hare, he says, like a arm of like a comet comes like an arm of the Kalki, you know, Kalki is the next avatar, as in our mythology, we believe. So Keshav is the Krishna, will be born as Kalki, and like a big arm, he will wipe out people who are Malaych or who don't follow the Dharma. So this is very well, you know, it has penetrated all our literature, poetry, and is well known in our Indian circles. But why meteorites are important? I think that the point we must make. Meghnad Saha, you know, Meghnad Saha was an astrophysicist. He invented this Saha equation, which is used because before Saha, it was known that it was thought that the composition of various stars, some are blue, you know, some are red, some are yellow, some are white. It's because of composition. But he said that no, it is because of temperature. And we can even tell the composition of the sun because it is high temperature and everything is ionized. So he gave some composition of the sun. But when we studied meteorites, especially the carbonaceous chondrite meteorites, and these are, you know, studied in laboratory, so we can do all trace elements, all elements which cannot be done by spectral lines. Only iron and things like can be silicon, and you know, major elements can be done by spectral lines. But we could go all the way up to uranium, thorium, and all trace elements and so on. And we found that actually this work was done by Hans Suess and Harold Urey in US. He said that the cosmic composition out of which Earth and Moon and Sun and all our planets are formed is exactly like carbonaceous chondrites. And now we have dated these carbonaceous chondrites. We know what is their age and so on. So a lot of, they are very important. In fact, whatever we know today about our solar system because of meteorites, and in PRL, you know, Professor Kuljit Kaur is here. She is studying this cometary material, asteroid material, and Earth, and so on. So we know exactly when they were formed, and we learn so much about our solar system. We know, whatever we know, much of it comes from study of meteorites. So I want to show you this calendar. The universe was formed in a Big Bang 13.7 billion years ago. This is what Fowler and other people proposed, Hoyle. And then sun was formed about 4.5 billion years ago. so very young compared to half the age of the galaxy or the universe. And Earth was formed later, 4.47 billion years ago. And life appeared about a billion years later, 3.5 billion years ago. So there is a fossil evidence in Greenland and other places that life first appeared on Earth 3.5 billion years ago. So all this has been done mostly by study of meteorites and so on. And most important thing, what we have learned is the cosmic abundance, what we call. What is the abundance of material in the interstellar space? Some features are very obvious. Everything is started from hydrogen, and it's decreasing as the heavier elements are there. And not only that, there is a dip here at lithium, beryllium, boron, and this was not formed. And I think Hoyle gave an explanation why they are not there. So first, helium formed from hydrogen, then oxygen, iron, there is a peak, and then there is an odd-even effect. Odd elements are less, even elements, even though in the neighborhood, are more. So all this we have learned by study of meteorites. Now I want to tell you about the great year in the history of planetary science in the world. That was the year 1969 that Japanese found some rocks in Antarctica. And these were least expected because it is all covered with ice and snow. So these rocks must have come from outside. So they brought about 9 rocks, and that was the beginning of Antarctic collection. Today we have about more than 30,000 rocks collected from Antarctica. And then same year, a carbonaceous chondrite meteorite fell in Allende in South America and in Mexico, actually, in which the oldest grains of the solar system. And they are so old, they are called pre-solar or stardust, something like that, coming from stars. Actually, before our solar system was formed, and they were identified because they are rich in calcium and aluminum and other refractory grains. The same year, there's another meteorite which fell in Australia in Murchison, place called Murchison, and that was very spectacular because not only these various elements were found, but they found amino acids out of which life, they are the bricks of life. The life requires amino acids to be formed. And of course, topping it all, 20th July is not far. So Apollo mission brought samples from Moon, and these were studied in TIFR and PRL and other places. So this was a fantastic year, a turning point, I would say, in the history of planetary science in the world. And very new techniques were developed from which we have learned a lot. So there are two kind of theories about life. Let me come to the point of this talk. I think I have a few more minutes to go. One is the endogen, that means life originated on Earth itself, but that is becoming more and more difficult with time. And the other thing is exogenic. The theory says that life was brought on Earth, that is panspermia, what it is called. And now there is increasing evidence that life originated in interstellar clouds because they have a lot of water, hydrocarbons, ammonia, all these essential elements, methane, carbon monoxide, which are present there. And they have grains there which provide them surface. They have ultraviolet light, which can give them, energy. And they have, various reactions are possible. So we believe that life originated from outside and they came to Earth riding on meteorites. So just to make this point, a meteorite fell in a place called Mukundpura near Jaipur in 2017. And we went there and picked up the sample. It has 2.3% carbon, and also it has organic carbon. It has water, 8% water. So you see, all this is essential for life. And this has come in this meteorite, which looks like charcoal, essentially very fragile, dark, coal-like material. It was about 5 kilograms, but broke on impact. And we got about 2 gram sample on which we worked. And it has big macromolecules, C100, H46, and 10. Those who know about this, that means very carbon-rich, hydrogen-rich molecules are found in this meteorite. And so this is very important because more and more evidence is gathering. And we studied with Dr. Tripathi and Kalpana and others. We found about 42 organic molecules. This is the first time that fatty acids and things were found here. There's a list here of what were identified, and there's a spectrum here. So you see, all this is brought from outside the Earth, and these are all life-producing, life-sustaining molecules, and we think this is how life survives on Earth. So meteorites are the creator of life on Earth, or they bring life from outside. And at the same time, the big ones, I talked about dinosaurs. About 70% of the life on Earth was destroyed during that event. And this is a Gubbio section, in Italy, where it was first discovered. We, of course, found 2 sites, as I mentioned, in Anjar and in Meghalaya. So there is a limestone, this is called Cretaceous because it is limestone, or white limestone. Then there is a layer about 4 centimeters thick, which is meteorite debris or asteroid debris or cometary debris. We don't know because this is rich in iridium, osmium, platinum, gold. And this is certainly not from Earth, but from outside the Earth. And then comes another limestone layer, it continues. But what is important is that here you have big animals. All animals get destroyed. There are no dinosaurs found afterwards in tertiary. And very small, few animals or plants survived. I think there were forest fires here. A lot of graphite has been found. So the life re-evolved here or rebuilt from the debris left after whatever was left, whatever specimen were left. So you see this dual role of impactors, sustaining life and destroying life. The nature has chosen such an efficient way of doing both the things. So what can we do about this? There is an imminent danger, that things are going to fall on Earth and destroy life again. And I don't know, for some reason, this is inevitable, but we are worried about the wiping of the civilization. So a lot of studies are being made to watch if some big body is coming and hitting the Earth. So NASA has this NEOWISE and this Lincoln Near Earth Asteroid Search and so on. So about, I think there are more now. This slide was made some time ago. So about a dozen efforts are being made to keep a watch. But what can we do if something comes? That is the big question. And in the same, people say when it's going to happen, we can't really predict. It can happen this moment or it can happen the next millions of years, we can't tell. But I think one which is going to come very close to Earth is 2029, not far. Then another is 2036. But the possibility of impact is less, but we never know. Some bodies come and are deflected back in space. So 2 in a million chance that this can hit the Earth. I don't know. But someday it is going to happen. That is for sure. It has happened many times in the past. It's going to happen again. So in that, just to study, I mean, I must mention that there are 26 known asteroids larger than 200 kilometers in diameter. And there are many more. Smaller the size, more are the asteroids, and they are all going to hit someday. Of course, their mass is not much, but they can create havoc here. Now, to understand what happens when this thing happens, this impact happens on Earth, the NASA has sent about 7 years ago a mission to a asteroid Bennu, which is about 500 meters in size. Here we have Eiffel Tower, which is 300 odd meters. So it's quite a small body. And they brought this sample last September. It took 2 years for the mission to go, 2 years to study the asteroid, and 2 years to come back. And last September it came back. And amazing discoveries, I think the most important thing they found is it has a lot of phosphorus and water. And it's similar to Mukundpura. So we were really amazed that we have these samples available to us for study. And they have a few hundred grams of this sample brought back to Earth, and it's available for study. I think they have announced. So I just want to take a minute to tell you that the dust in Bennu asteroid is rich in carbon, nitrogen, organic compounds, and so on. And they have found magnesium sodium phosphate. That is a very recent discovery. And this phosphorus is very important. And of course, phosphates are also found in Japanese mission Hayabusa. But now the sample is abundant, so a lot of studies can be made. So I'm trying to bring out the importance of these asteroids, comets. A lot of organic material is there in comets. In fact, about 35 million years ago, whole Earth was immersed in cometary debris, and we have evidence for it. So, it's very important. And what we can do is, Earth is moving, as 30 kilometers per second. So when it is going to come close to Earth, we can deflect it. NASA is trying very hard. If you just deflect by 30 kilometers, then the Earth can miss it and we can survive. That is one way. There are other ways also they are exploring. They can break it into smaller debris and so on. But this is all fantasy. I think it's science fiction so far. I want to end this talk by saying that our astronaut Sunita Williams has got stuck in this Starliner. She went on this the space station, and she's stuck there. She's not able to come back because of some helium leak. So she's a very accomplished astronaut. I met her twice when she came to India, and we had a lot of interaction with her, with the school children. So let us pray for her safe return. I think there are technologies available. She will be brought back safe, I'm sure. But I think for now, she's stuck there. And I want to say that it is very, exciting to search a meteorite, to look for a fireball, to hear the sound, the thunder created by them. So you should all make a hobby of collecting meteorites, and you are sure to get one in your lifetime because the probability is high. If some 1,200 or 1,500 meteorites fall on Earth every year, I think in 10 kilometers, in 100 years, one is sure to fall. And we have been discussing with Bharat Adur how to have an audio or a video or a camera look for it. So I would urge you to join our astro enthusiast group and join in the search of meteorites. It can be a very unforgettable cosmic experience. And of course, this is a time when we do scientific study. But Emperor Jahangir got a meteorite, and all he could do is make a khanjar out of it, because iron meteorites don't rust, they have a lot of nickel, and is still preserved, this khanjar of Jahangir. If you want to have more details, I have a book called Falling Stones and Secrets of the Universe. You can get it from Gujarat Science Academy. It's available in Gujarati, Kannada, English, and various languages. So I have tried in this short time to bring out the excitement of meteorites and why Asteroid Day and why it is a very serious business. We can't ignore it for our survival. Thank you very much. It has been a pleasure to talk to you, and I'm happy to say that Nehru Planetarium and Bharat Adur and others have organized this program for awareness, and I'm sure you will hear some more talks on this topic later on in the day. Thank you very much.
Thank you, sir. We are very happy to have your talk, and what we lost minutes in the beginning, you have helped us in getting it into schedule, because we had to have a tea break. Now we will have a short tea break here, and we will start again at 11 o'clock. But before that, I would like to thank Professor Bhandari for his continuous support to this Asteroid Day program. The best part over here is when we conducted this program in Bangalore, they have brought his book, translated his book into Kannada. Similarly, I hope the listeners on this channel will also look for translation of his book in Marathi also, and also in other languages, because his information goes back to more than 60 years or 70 years, and still he's strong on his asteroids. And now I'm looking forward for his one more talk sometime later on Bennu. Here, I hope that will be happening shortly. Can we have one quick question? Because again, we have a lecture by Dr. Krishnamurthy at 11 o'clock. So a short question we can entertain. Is it okay, Doctor?
Yes, any question, that is fine.
Yeah, a short question. We will be unable to give that, and try to keep to our time schedule, so that somebody will like to hear the other speakers also. Yeah, if there are any questions.
Sir, Dr. Bharat sir, I am Professor Prakash Narasimha speaking from Mysore. Hello?
Yes, please.
Hello.
Yes.
I have a question to Narendra Bhandari sir. Okay. Bhandari sir, you have given a very good talk, taking us from fundamentals to the latest advancements in the field of meteorites. Really fantastic. But one thing I would like to ask you is, these meteorites are very well preserved in USA, Europe, and Australia. And you told that certain climatic conditions they are inhibiting the preservation of meteorites in India. What should be the ideal condition for the meteorite to be preserved in nature, sir?
You see, our meteorites are all stored in Calcutta, which is very humid. So there are two problems. Firstly, we have the advantage of very thick population. Nothing goes unobserved if falls from the sky, and I have a lot of experience of talking to people where meteorites have fallen. So very easy to collect meteorites, but preservation is difficult. So because firstly they should be shifted to a hot desert, kept in nitrogen atmosphere, or at least something can be, closed boxes, dry, because meteorites are formed in reducing conditions where there's no oxygen. So some people, I just wanted to mention, don't give us meteorites. They keep it with them in their house, when we go and look for them. But next year when we go, or later on we go after a year or two, they say, oh, I kept this meteorite, but it has all disintegrated. It is now powdered and lost. So you see, that is what happens in Indian climate or in any other climate. So they have to be kept dry. They have to be maybe kept in, if preferred, in nitrogen atmosphere, and they should not be touched by hand because organic compounds, get contamination from earth rocks. They should be collected in plastic bags. So there are a lot of things. It is all given in this book. Actually, I'm updating this now because a lot of new discoveries have made since this book was written. Now they have found interstellar material from outside the solar system come in our on Earth or in our solar system, and that is very rare. I think 3 have been identified which have come from outside the solar system. So preservation is a very important thing, as you mentioned, and there are techniques how to do it. So I think yeah.
Okay. Thank you very much, sir. Thank you.
Yeah. Hello. Can we now thank Professor Bhandari for his wonderful talk? And slowly we move on to the next speaker, Dr. K.V. Krishnamurthy, who will be the next speaker for this talk, who is already here with us today, and he will be talking to us about his topic. So I think I will have to also welcome him for this talk. I think this is the first time we have somebody from Geological Society of India giving a talk at Asteroid Day. Thank you so much, Dr. Krishnamurthy. And a little brief we would like to say about Professor Krishnamurthy. He had a distinction right from his academic days, and he had completed a lot of work, especially in mineral investigation in tungsten and limestones in Kumau, and he has been pioneering work in Raichur. So already he has worked as a geologist for of time, and he was also in formulation of 5-year plan for geology. So today we have a distinguished guest who is going to talk to us, and most interesting is he's an accomplished researcher, explorer, and I would move one step further, is a science popularizer also. So we have him today for the talk, and he has been also associated with Geological Society of India for a very long period of time. Interestingly, he is also a speaker, or rather, he has worked in sensing and aerial surveys from Bangalore, remote sensing. So we have Dr. Krishnamurthy today to give us a talk, and I am very happy, sir. We welcome you for coming for talk, and we are looking forward to hearing you. At thank you very much, and we look forward for your talk, sir. Thank you.
Thank you very much, Dr. Bharat, for those nice words about me. At the outside, I would like to thank your institution and also Nehru Science Centre for inviting me on this occasion of the World Asteroid Day. In fact, on behalf of the Geological Society of India, I convey greetings to all those who are present and listening to today's talk. At the outset, can I share my slides, please? Am I audible and is it visible? Dr.
Yeah,
Bharat, am I
it is
audible?
visible. It is visible. I think you have to start your
Slideshow mode.
yeah, your slides.
Yeah. Thank you very much for giving me this opportunity. In fact, I should also thank Professor Bandari because he has made my job quite easy because there are certain repetitions. In fact, I would request all our viewers to excuse me if there are overlaps from his talk and to my talk. In fact, my emphasis would be on geological aspects of asteroids and meteoroids. So now I need not go to the first slide as what are asteroids. He has already explained. We all know that they are the small rocky object that orbits the sun. While on the other hand, a meteor is what happens when a small piece of an asteroid or comet called a meteoroid burns up and enters the Earth's atmosphere. In case of comets, unlike asteroids, comets are made of ice and dust. As Professor Bandari said, that they bring in a lot of life on Earth, and at the same time they take away life from Earth. So there's a good something like they are both creators and the destroyers. In the spiritual point of view, if you say that, the Krishna says that I am the creator and also I am the destroyer. So it is something like that, which Professor Bandal also underscored that matter. So this is a picture close-up image of the asteroid Ida taken by NASA's Galileo spacecraft. In fact, what I want to say is the asteroids have got no definite shape. They are quite irregular. Sometimes they may be semicircular or spherical also. And whereas, as we all know that comet has got a kind of tail. So these foreign or extraterrestrial bodies, they keep coming at Earth once in a while. Sometimes they take 75 to 79 years, like Comet Halley, and others they come once in million years also. So most asteroids can be found orbiting our sun between Mars and Jupiter, as already been told. And they range in size from, say, the one asteroid Vesta, the largest asteroid, about 530 kilometers diameter, to bodies that are less than 33 feet, so tiny bodies, that is less than 10 meters across the diameter. And the total mass of all the asteroids combined is less than that of Earth's moon. So they are so tiny objects, but still they are very, very impactful on Earth. The current known number of asteroids or minor planets is 1,370,772. That means 1 million, more than a million, according to the NASA. There are so many asteroids, but then they are put together, they are less than the weight of our moon. As you all know, asteroids originate from the main asteroid belt that is between Mars and Jupiter. And this belt is theorized by scientists to be remnants of planets that did not completely form. That's what they say, that the asteroids which are found beyond Neptune and all, they say that Jupiter is responsible for all these fragments of the asteroids. It destroyed due to its gravitational force. And this is that belt we were talking about between Mars and Jupiter. And there are other two concentrations along the orbit of the Jupiter. Sometimes asteroids and comets are nudged into Earth's neighborhood by the gravity of nearby planets. Due to their gravitational attraction, they get nudged into the neighborhood. These objects are called near-Earth objects, or popularly known as NEOs. There are more than 35,000 NEOs, according to the CNEOS at NASA's Jet Propulsion Laboratory. About 99% of these NEOs are asteroids. They are mainly asteroids. Most asteroids are irregularly shaped, as I told you in the beginning, though a few are nearly spherical, and they are often pitted or cratered. So many craters are available within the asteroids. As they revolve around the sun in elliptical orbits, the asteroids also rotate, sometimes quite erratically, so causing their tumbling into the neighborhood. More than 150 asteroids are known to have a small companion moon. So there are some which have got 2 moons also. There are also binary, that means double asteroids, in which 2 rocky bodies of roughly equal size orbit each other, as well as triple asteroid bodies. That could be quite rare. In fact, in the our neighbor, I can say that such a type of, though it is theoretically explained, but practically so far I don't know they have got any record of having such asteroids. The orbits of asteroids can be changed by Jupiter's massive gravity and by occasional close encounters with Mars or other objects. So sometimes they just dash into the gravitational force of Jupiter. These encounters can knock asteroids out of the main belt, what we call as asteroid belt, and they hurl them into space in all directions across the orbits of the other planets. Sometimes stray asteroids and asteroid fragments have slammed into Earth and the other planets in the past, playing a major role in altering the geological history of the planets and in the evolution of life on Earth. Professor Bhandari has emphasized on this point that these asteroids have brought in the building blocks of life. And then they are also shaping the history of not only Earth, but also of other planets. So they are the one causing the evolution of Earth. And in tertiary or Jurassic period, they are the one which causes the extinction of life on Earth. Scientists continuously monitor Earth-crossing asteroids whose paths interact Earth's orbit and near-Earth asteroids that approach Earth's orbital distance to within about 28 million miles. And they may pose an impact danger, as already explained by Professor Bhandari. So asteroids coming and hitting the Earth is imminent. It is inevitable. Only thing we can only monitor and maybe caution people of the probable space where they are going to hit on Earth. The radar is a valuable tool in detecting and monitoring potential impact hazards by reflecting transmitted signals of objects, images, and other information can be derived from the echoes. Scientists can learn a great deal about an asteroid's orbit, rotation, size, shape, and metal concentration. So whatever we are having the knowledge about asteroids, it is because of the scientists who are constantly monitoring this. Let us come to classification of asteroids. What are the type of asteroids we have? The majority of known asteroids orbit generally with not very elongated orbits. They are sometimes elliptical, and the belt is estimated to contain between 1.1 to 1.9 million asteroids, which are larger than 1 kilometer in diameter, and millions of smaller ones. So such is the number of the asteroids. In the early history of the solar system, the gravity of newly formed Jupiter brought an end to the formation of planetary bodies in this region and caused the small bodies to collide with one another and fragmenting them into the asteroids we observe today. That's what we are talking about, the asteroid belt. It's because of that impact. There are something called what are Trojans. These are asteroids share an orbit with a larger planet, but do not collide with it because they gather around two special places in the orbit, that is at L4 and L5 Lagrangian points. There, the gravitational pull from the sun and the planet are balanced by a Trojan's tendency to otherwise fly out of orbit. So they are balanced because of these forces. Otherwise, they would have scattered here and there. The Jupiter Trojans form the most significant population of Trojan asteroids. It is thought that they are as numerous as the asteroids in the asteroid belt. There are Mars and Neptune Trojans, and NASA announced the discovery of an Earth Trojan in 2011. Near-Earth asteroids, these objects have orbits that pass close by that of Earth. So they are called the near-Earth asteroids, and they actually cross Earth's orbital path, are known as Earth crossers, like they are guests to the Earth. How do these asteroids are named? There is the International Astronomical Union's IAU Committee on Small Body Nomenclature, which is not very strict when it comes to naming the asteroids. With the result, what happened? We have a giant space rock named Mr. Spock. It's actually a memorial for a cat and not a tribute to the Star Trek character played by Leonard Nimoy. So this is how it happens, because they are not so strict in nomenclature or naming the asteroids. There is also a space rock named for the late rock musician Frank Zappa. There are more somber tributes too, such as the 7 asteroids named for the crew of the space shuttle Columbia killed in 2003. While Professor Bandari was giving his talk, I saw one message in the chat box that our dear and most veteran astronaut, Sunita Williams, died because of the leakage of that gas. It's very, very unfortunate to hear that. I hope this Vivo V2312 camera, I got it. Thank you for the information. Asteroids are also named after places and a variety of other things. The IAU discourages naming asteroids for pets. So people naming the asteroids on their pet names like cat or dog, I think they discourage. Asteroids are also given a number, for example, 99942, Apophis. The Minor Planet Center keeps a list of asteroid names. In fact, last year I was attending one conference at Pittsburgh in USA that was about the Geological Society of America arranged. The scientists from NASA came there, they presented. In fact, many of our netizens or citizens, they are so active there. They, in fact, discover several of these celestial bodies, and they name them. Now, this is one such habit. I think Professor Bandari also said that we all should, keep watching the sky. Sky watchers should be more. So that's how many things in the sky came to light. So I was talking about the names. See, this is a dactyl, and this is Anfrang. The biggest one here is Lutita, which is about 132 into 101 into 76 kilometer. That was named by Rosetta 2010. So they have got different shapes and different size. The biggest one, perhaps you can see on the screen here. So this International Astronomical Union is responsible. It is the single worldwide location for receipt and distribution of positional measurements of minor planets, comets, and outer irregular natural satellites of the major planets. So that is the one body, that is the Minor Planet Center, which keeps these records. The MPC is responsible for the identification, designation, and orbit computation for all of these objects. This involves maintaining the master files of observations and orbits, keeping track of the discoverer of each object. It's something like our municipalities or corporations, they keep track of the birth and death of person. It's something like that. It has come to that. The MPs cooperates at the Smithsonian Astrophysical Observatory under the auspices of Division F of the International Astronomical Union, that is IAU. So let us come to another aspect of the asteroid. Asteroids are made of what? What is their composition? An asteroid's composition is mainly determined by how close it is to the sun. The asteroids that are nearest the sun are mostly made of carbon with smaller amounts of nitrogen, hydrogen, and oxygen, while the ones further away are made up of silicate rock. These silicates are very common on Earth, as you know that Earth composition mainly silica and oxygen. They are made up of oxygen and silica, the number 1 and number 2 most abundant elements in the Earth's crust. That's how we have got, for example, we call a common mineral quartz, which is nothing but pure SiO2.
Good morning, sir.
I think there was some disturbance. The metallic asteroids are composed up to 80% iron and 20% a mixture of nickel, iridium, palladium, platinum, gold, magnesium, and other precious metals such as osmium, ruthenium, and rhodium. So they are the storehouse of some of these elements which are not found in much quantity on our planet Earth. A few of the asteroids are made up of silicate and of metallic. If you look at this chart, you can come to know so many values the asteroid body contains, the metals and minerals. For example, see what is written here as into means so many times it is richer compared to the Earth. So hydrogen is richer there 17 times, carbon 75 times, nitrogen 74 times, and oxygen 1 time. Let us come to rare earths, something like rhodium. This is 800 times richer than our planet Earth. Rhodium and rhodium and palladium is 44 times, osmium 440 times, and iridium 540 times, and platinum 196 times the richer than what our planet Earth contains. So that's why they are called the storehouse of all these important elements which are required in various industries on Earth. For example, industrial metals, they require, these days we are all familiar with our electric vehicles, LCDs, advanced materials, and several equipments in medicine. All these requires very, very rare metals such as platinum, cobalt, nickel, like that. So that's why they are very, very important as far as their metal contents are concerned. In fact, according to Planetary Resources, a company that hopes to mine asteroids in space. So there was a kind of news, they want to mine asteroids because these metals exist in such high concentrations on asteroids that a single 500-meter platinum-rich asteroid can contain more platinum group metals than have ever been mined on Earth throughout the human history. Can you imagine how rich these asteroids are? Just a 500-meter platinum-rich asteroid can give you so much platinum, which is not available on Earth. Other minerals have been found on asteroids that have been visited by our spacecraft. For example, the Hayabusa spacecraft landed on Itokawa, a spud-shaped near-Earth asteroid, and found it consists mainly of the minerals olivine and pyroxene. In geology, we call this as mafic minerals, a mineral composition similar to a class of stony meteorites.
Good morning, sir.
That have pelted Earth in the past. In addition to these metals, the elements to create water are present, as already told by Professor Bandari. There is a lot of water, and their interiors is made of ice, and there has been even evidence that water may have flowed on the surface of at least one asteroid. There are some kind of a channels, for example, observations of Vesta from the Dawn mission show gullies that may have been carved by water. The theory is that when a smaller asteroid or comet slams into a bigger one, the smaller asteroid or comet could release a layer of ice in the bigger asteroid. So that's how we find a lot of water-flown gullies on some of the asteroids. But over time, these asteroids may have changed. It's also thought that chemical reactions over the millennia or more recent impacts they may have endured also affects the composition of asteroids. Some experience high temperatures after they formed and partly melted, with iron sinking to the center and forcing basaltic. That's what we have got plenty of basalts on the Earth, basaltic lava to the surface. Only one such asteroid, that's Vesta, is known to have this type of surface. There are different types of asteroids, like dark sea carbonaceous asteroid, which make up most asteroids and are in the outer belt. And this contains a lot of volatile elements, particularly hydrogen or helium. And there is a S asteroid, that is bright S, which is silicaceous asteroid and are in the inner belt, closer to Mars. They tend to be metallic iron with some silicates of iron and magnesium. Bright M asteroids, that is metallic asteroids, they sit in the middle of the asteroid belt and are mostly made up of metallic iron. There are also D-type and V-type with near the Trojan asteroids of Jupiter, and also near Kuiper belt, which is beyond Neptune. While these have not been studied extensively, it has been suggested that they have a composition of organic rich silicates, carbon and anhydrous silicates, possibly with water in their interiors. I think I will not go into much of these details of the comparisons, because I have to preserve some time for my impact craters, which I am going to deal in detail. If we were talking about the number of asteroids, there are millions of asteroids in our solar system, and the estimate says that it may be between 1.1 and 1.9 millions, the two which are larger than 1 kilometer diameter. As of September 6, 2015, this is what the data I have collected, 13,024 near-Earth objects have been discovered. About 75 of these NEOs are asteroids with a diameter of approximately 1 kilometer or larger. There are also 1,609 NEOs have been classified as potentially hazardous asteroids, as none at this time are expected to impact Earth, because they are most dangerous in the sense they contain hazardous chemicals. So this is just a picture to show the different sizes of asteroids near that belt, and illustration of small asteroid passing near the Earth, as small as this and as big as this. When it comes to life, asteroids are too small to support life as we know it. That is because they are too tiny to even hold on to atmospheres. So atmosphere is very important for life. Their gravity is too weak to pull their shape into a circle, so they are irregularly shaped. To get a sense of just how small they are in aggregate, NASA says the mass of all the asteroids in the solar system is less than Moon. So we were talking about our Jurassic time, that is the extinction of the gigantic animals called dinosaurs. The asteroid, there is an opinion that asteroid the asteroid impact has caused the extinction of these gigantic animals on Earth. The fossil record for dinosaurs and other creatures of their era show them rapidly disappearing around 65 million years. That is our Jurassic time in the geological time scale. According to National Geographic, there are two hypotheses for this event: an asteroid or comet hitting the Earth, or a huge volcano eruption. In geology, we do believe that the Deccan basalts, or the Deccan lava, what we call in geology, so it got spread. The volcano spread these Deccan basalts around the same time of 65 million years. So there is a school of thought that the asteroids are not the only cause for extinction of these gigantic animals. It could be because of the huge volcano like our Deccan basalt. Evidence supporting the asteroid hypothesis includes a global layer of iridium. How do you know that? Whether it is due to volcanic impact or due to asteroid impact. So if you get a rich iridium layer, so make sure that it is because of the asteroid impact. Because we don't have so much iridium, though we do have iridium in volcanic rocks, but it's not so much as that of asteroid. In either case, the resulting debris blocked the sun and eventually starved those survivors of the impact. It's not only the impact due to its heat and lava, it's also impact caused due to dust and gases, which made the atmosphere dark and the life could not survive. So let us come to what are meteorites. As we all know, it is a solid piece of debris from an object such as a comet or asteroid or meteoroid that originates in outer space and survives its passage through the atmosphere to reach the surface of the planet or moon. When the object enters the atmosphere, various factors like friction, pressure, and chemical interactions with the atmospheric gases cause it to heat up and radiate that energy. It then becomes a meteor and forms a fireball, also known as a shooting star or falling star. Astronomers call the brightest examples as bolides. So they are also called as bolides. And meteorites vary greatly in size. For geologists, a bolide is a meteorite large enough to create a crater. That is where it's where we call the impact craters. A meteor is light. It is a light phenomenon or a streak of light that occurs when a meteoroid burns up. It's already there. I need not repeat. So this is how it looks: meteor shower. So if you come to how many types of meteorites are there, there are mainly 3 types. That is, one is a stony meteorite. An example is given here. The most common type of meteorite is the stony meteorite, and they are generally composed of approximately 75 to 90% silicon-based minerals. That is, mainly it contains silicate minerals, and 10 to 25% nickel iron alloy, and trace amounts of iron sulfide. There are iron meteorite. So as the name itself indicates, most iron meteorites likely originated in the course of large asteroids and are composed almost entirely of nickel iron alloy, which is also a primary component of the Earth's interior core, what we have got. And the third one is stony iron meteorite. It's a combination of stony and iron meteorite. These contain approximately even amounts of silicates and nickel iron alloy. That is 50% of silicates and 50% of nickel iron. Now let us come to another aspect, that is the impact craters. As we all know that when an asteroid or a comet or a meteorite hits the Earth, it creates impact. Impact craters are roughly hemispherical depressions formed due to impact of a meteorite. In the last few decades, geologists have gradually realized that collisions of extraterrestrial objects with Earth have significantly shaped Earth's surface, and it disturbed its crust, altered its geological history, and caused extinction of life, as we discussed a few minutes back. The impact structures range from only a few kilometers or less in diameter to as large as more than 200 kilometers in diameter. These are some of the pictures. Here you can see that when the meteorite crashes into surface, a larger solid object like a planet moon, it creates this kind of crater. So those of you who have seen the volcanic craters, they may get confused because I myself have seen several such craters in Hawaiian Island in USA. So the only difference you can see in the impact craters, we have got a central depression. And the important thing is there are breccias here and fractured bedrocks and impact ejecta. That is very, very important. Impact ejecta. So there are two types of craters. One is this is a simple crater, which I explained just now. Another is a complex crater. Here the difference is it has got more than one depression, and there is a central peak, uplifted peak here. That is called complex crater. These are some of the photographs of crater in the moon, and here the crater in Arizona in USA. So in fact, Shoemaker in 1977, he has said that impact cratering is the most fundamental geological process in the solar system and beyond. That means, so in our solar system, daily we witness such impact. So when it reaches the Earth, then only we say that this is an event. So there are plenty of such craters on the moon, as you all know. So this is the distribution of nearly 200 impact craters so far discovered on planet Earth. So many of them are concentrated over here in USA, in South America, and then in Europe, and in Australia, and sporadically in Africa. And in India, I will come to that. There are major 3 impact craters have been discovered so far. So how do we recognize these impact craters? The geological process other than impact cratering, such as volcanic eruptions, may also lead to hemispherical depressions, as I was just explaining. Owing to the intense deformation, the impact craters are highly susceptible to erosion. This is the drawback in identifying the impact craters. As ours is a tropical country, most of these impact craters are what I was telling of the rim of the crater, they get eroded away. So with the result, it becomes difficult to identify. Scientists have therefore identified geochemical and structural markers of a meteoritic impact. These markers do not form by other geological processes. This is where it is important. So to distinguish between a volcanic crater and the impact crater, here are some of the markers. Number 1, they are preserved meteorite fragments. So you don't get meteorite fragments in the volcanic crater. And anomalous amounts of siderophile elements such as nickel, cobalt, chromium, gold, and platinum group elements. Then they have got shatter cones. Then they have got high pressure, that is diaplectic mineral glasses. High pressure glasses such as tachylite we call, you do get there. Then high pressure minerals. And those minerals which you are finding there, they are all high pressure minerals. High temperature glasses and melts, and planar fractures, and in quartz, and planar deformation features. That is what we call as PDF. These are the characteristic features based on which you can say whether these are impact craters or these are the volcanic craters. Why do we study impact craters? From the economic point of view, these are very, very important. They contain a lot of gold, such as in the crater what they found in Rutherford in South Africa, nickel, copper, PGE elements in Sudbury, Canada. In fact, they are mining for these, and impact diamonds in Popigo in Russia. So these are some of the diamonds. These are the gold veins in the rock, which is created by the impact. of the asteroid. So I was talking about the KT boundary, Cretaceous Tertiary boundary. There are three important impact craters which have formed during the KT boundary. That is, one is in Mexico, it is called Chicxulub crater, and another is in Baltic crater in Ukraine. And in India, we do have such crater, it is called Shiva crater. That defines the KT boundary. In fact, the picture what I showed just now, see, you look at the position of India, it is not near this Tibetan border. So that was during 65 million years back, we were there. And this impact crater has occurred during that geological time scale. Come to this Chicxulub crater in Mexico, which is about 180 kilometer diameter. And the crater in Ukraine is about 25 kilometer in diameter. Whereas the Shiva crater in India is about 500 kilometer diameter. Unfortunately, this crater is not onshore, this is offshore. And several workers have worked on that. Recently, even Shankar Chatterjee has worked on that. And several foreign geologists have also worked on that. Based on the seismic data, they have concluded that it's an impact crater. All these craters are excellent structural traps for giant oil and gas fields. That is what we have seen in Bombay High. It is a part of that Shiva crater. I was just talking about the economic importance or the importance of crater. The effect of meteoritic impact with energy equivalent to 100 kilotons TNT is recorded yearly. That's what even Professor Bandari has also mentioned about this. So for example, the Hiroshima atom bomb was merely only 15 kiloton. Can you imagine? With respect to that, we have got 100 kilotons of TNT every year hitting our planet Earth. The impact generated a blast of air and heat, tsunamis and earthquakes. So such is also recorded. So I am just going fast because I think I'm left with only 5 or 10 minutes time. I think Dr. Bharat, can I take 5 or 10 minutes more? I think this microphone is muted. So we have got lots such impacts.
Hello.
I was just asking, sir, can I continue for another 5-10 minutes? My time I am asking.
Yeah, you can continue for another 5-10 minutes.
Okay, I shall end them.
Yeah.
Thank you. So I was talking about the evidences for impact craters. Yeah.
So I thought maybe we should give them an option to talk, ask questions.
Oh, sure. I shall conclude with a few more slides. Thank you. As on date, more than 200 impact craters have been proved on Earth. And the first one to be proved in India was the Lonar crater in Maharashtra. They have discovered shocked materials such as impact gases, as I was telling. That's way back in 1972 by Naikta and Fredrickson et al. In 1973. This is a picture of that Lonar crater in Maharashtra. It is almost a kind of a circular impact crater. And impact ejecta is affected over all these areas surrounding this crater. There is a second crater which is known as Dala impact structure, which is in Madhya Pradesh. This was initially classified as a cryptovolcanic explosion structure, and subsequent investigations by Pati et al. In 2005 have revealed that diagnostic microscopic shock metamorphic features, which resulted in the confirmation of Dala as an impact structure. This is the picture. This is where the Dala crater is there. It's a kind of semicircular. I need not go into the geology of it. So it's about 12.36 meter thick suet is found. That is the impact breccia is found there. And 1.8 meter thick layer of altered suet occurs above the impactment. Then there is the third one, which is called Ramgarh crater in Rajasthan, which is also mentioned by Professor Bhandari. In 2021, Agarwal group, they have found that planar deformation features and feather features, and which establish that it is a impact crater. This crater has got 10-kilometer diameter, and its collar is about 200-meter high, and this comes under the complex crater. This is the Ramgarh crater, some of the pictures. You can see that. This is a section of that crater, as I was telling you. You have got crater rim, which is almost eroded on either side, and you have got central uplift, and with two collars and central depression. So coming to the third crater, which I was mentioning, this is the Shiva crater, which occupies such a big, area in Arabian Sea, and a part of margin is exposed along Ratnagiri coastal area here. This is the biggest on the Earth crust because its diameter is around 500 kilometers. Okay, it has got peak ring, and several rings are there: ring 1, ring 2, ring 3. That's why it is called a complex crater, and it's about 200 kilometers, the ring 1. And another ring is 250 kilometers, and the third one is about 550 kilometer diameter. So I am not going much into details because, as Dr. Bharat puts it, I should give some space for our audiences to query and interact with us. Thank you so much for your patient hearing. And with this, I end my today's talk. Perhaps I am within my time limit. It started at 11 and ended at 11:45. Thank you so much. I once again thank Dr. Bharat and his associates for inviting me to present my talk. Thank you.
Sir, for your talk, it was wonderful. In fact, I have been talking about Shiva crater here in Mumbai. It is next door to us.
Yeah.
And being next door to us, the diameter of that or the length of it is around 600 kilometers.
Yeah.
Starts from somewhere in south of Gujarat.
Huge.
Bhuj. And then it comes all the way down to Ratnagiri or in Maharashtra.
Yeah.
And the ridge of that is limited up to Ratnagiri. In fact, I have been asking our other
Your voice is broken.
About whether they can find behind below Ratnagiri.
Yeah.
One of our objectives in conducting these asteroids is only to bring younger people into these observations and make them realize how to go about for doing field expeditions.
Yeah, in fact,
with that, I think I am not able to get more time now because we have a next speaker waiting and it's a young student.
Oh, wonderful.
So it's
Thank you.
Prasad. She is a student now of PhD and she is from Singapore. So her little biodata is she is a PhD student in Nanyang Technological University in Singapore. She has held a master's degree in earth sciences from University of Bern in Switzerland, where she researched some and identified some meteor strewn in field of Oman. That is, this is one region which now has been yielding a lot of meteorites in Oman. Then in the afternoon, we are going to hear about Morocco. or the Northwest Africa, where they have also found meteorites. So, her talk is on classification and evolution history, reconstruction of enstite chondrite meteoric material, and from Oman. But so I would request all our younger friends to take keen interest in hearing her. She's a young student, and I'm looking forward to her for this Asteroid Day program. And we are very happy that we are having young students here also in the hall. And for your information, I'm in my hand, I'm holding a meteorite. So with that, Anulekha, it's your floor, and you have people here to encourage you for your further work. Thank you.
Thank you. Thank you so much for the introduction. I will just quickly share my screen. I hope it's visible.
Yeah, it's visible.
Okay, perfect. Okay, so thank you for the introduction. I will be talking a little bit about the practical aspect after Dr. Krishnamurthy's wonderful talk where he elaborated so much on meteorites and craters and everything. So now I will explain just one type of meteorite, which is an enstatite chondrite meteorite that was collected in Oman. Just a little bit about me, just a little bit of repetition, but I did my bachelor's at University of Delhi in India. Then from there, I moved on to Switzerland, Bern, where I worked on the project that I'm going to now explain. But currently, my position at Nanyang Technological Institute, NTU, in Singapore, works on constraining the behavior of water under different pressure and temperature conditions, specifically with mineral and water interaction. So hopefully that can have further use in planetary sciences as well, to understand how, as water is ubiquitous, how we can learn more about the exoplanets and our solar system. So again, just a little bit about meteorites. So as previously mentioned, they are solid macroscopic bodies that survive the entry into the Earth's atmosphere. They are of two types, differentiated and undifferentiated. So differentiated would mean like Earth, where it's large enough that there is enough heat in the body where a core mantle crust or similar differences can be created. And the opposite of that would be undifferentiated, where the asteroid bodies or the parent bodies are smaller and do not have enough heat for global melting to occur. Undifferentiated meteorites are also called chondritic meteorites because they still show proof of chondrites, which are the basic which are considered to be the building blocks of our entire universe, almost. They are further divided into three types: ordinary, carbonaceous, and enstatite. This study focuses on enstatite chondrites that are among the most pristine representatives of the inner solar system, where inner would mean closer to the sun. And these are one of the rarest chondritic meteorites found. The numbers on this diagram show the amount of samples that are actually available on Earth. And as you can see, enstatite has merely 1% of all chondritic meteorites available. So a little bit about enstatite chondrites. So these are characterized by very reduced and anhydrous assemblages, which means that when it was forming, there was not enough oxygen for oxides to form. So everything inside is a sulfide. So the major mineral that you find, which is a silicate, given its name enstatite, which is magnesium rich, which makes up 70 to 80% of the chondrite. Then you have a metallic alloy, which is iron and nickel, that makes up about 30% of the sample, and then abundant sulfides. In ordinary chondrites or in carbonaceous chondrites, these sulfides would have been oxides. So the calcium or the iron would have combined with oxygen in place of sulfur. Ancestral chondrites are further divided into two types, I apologize. One is high iron and the other is low iron, and it is the bulk iron composition. They can be differentiated based on the chondrule size and also on the elemental silicon in the iron, in the alloy, the metal. This project has two objectives. Since this was a new meteorite that has previously not been studied, the first objective, of course, was to identify it, to identify the petrologic grade, which is also the metamorphic degree, and the shock stage, and to also classify which subgroup or group it comes from, like EL or EH. Then, with this information, I took it a step further to try to understand how this meteorite came to be. So it is part of an asteroid or a parent body, and how that parent body evolved, what was the last metamorphic closure, and what happened after that. Post breakage from the parent body, the meteor orbits the sun and is exposed to cosmic ray exposure. And that can give us a trajectory. So I also wanted to understand how long it has been floating in space. In order to achieve this, the methods that were used were traditional microscopy. There was SEM, EPMA. Then there was also electron diffraction, X-ray fluorescence. There was ICP-MS for the elemental concentration. Thermal ionization mass spectrometer was used for the radiogenic isotope studies, and the noble gas mass spectrometer was used for the noble gas, the neon isotopic studies. So my team from Bern went to Oman on two excursions, 2020 and 2022, where they collected approximately 60 samples of meteorites. Now, as you can see in these images, it is easy to differentiate between the sand or the limestone as compared to the meteorite. The samples range from really small to like about 2.2 grams to almost 3 kilograms. And one difference that was seen was that some were found on a limestone regolith, where as the water did not stay for long on the sample, the weathering degree was lower, as well as the fractures were minimum. Comparatively, the strongly weathered ones which were fragmented were found on sand dunes because the water could collect and corrode for longer. Now we have a group of, if you can see that, we have a group of 60 samples that need to be identified from an area. Like from looking from outside, you cannot differentiate which kind of chondrite it is. So the easiest thing, which is quick, it's cheap, and it's non-destructive, is to use XRF. So each sample, a fresh cut surface was measured, and as you can see in this table, the zinc content, the bulk zinc content was measured, and according to Kong et al., enstatite chondrites have a higher bulk zinc content than ordinary chondrites, and by a large margin, where error can be differentiated. So enstatite has of the 32 samples, the average was about 204 ppm, whereas for ordinary chondrites, about 20 of them, it was around 50. So the difference was high enough to easily distinguish the two types of chondrites. But there were still 8 that were ambiguous because the number fell somewhere in between. So these 8 samples were then measured in XRD. Now, as you can see, the black line corresponds to ordinary chondrite. At approximately 20, 32 36 and 40, there are these peaks that are corresponding to ordinary chondrites that do not correspond with the enstatite ones. So this method was used to then easily ascertain which of these 8 ambiguous samples belonged to ordinary and which belonged to enstatite chondrite types. With this information, for prospective, for next step studies could be that I determined the strewn field. Now, a strewn field is an area where a meteorite from a single fall are dispersed. So imagine a meteor entering the atmosphere. Because of the friction, the pressure, the temperature changes, it fractures along weaker planes and falls in breaks into multiple pieces. The heavier ones will fall farther away because of the higher energy that they have, and the smaller ones fall almost directly underneath. And you should, hypothetically, you should get an oblong shape like this. However, this strewn field does not quite correspond to it, but it still gives us a rough northeast southwest direction that can be extrapolated for trajectory. Now, after the 39 samples were identified to be from the same strewn field, thin sections were made, and now I will explain a little bit about the sample description. So the first thing that you see in the thin section, they are the chondrules, because as a chondritic meteorite, 60 to 70% of the thin section consists of chondrules. They are of two types. There's a porphyritic pyroxene, which is in which you can see distinct different grains in different orientations. Some are along the A-axis, B-axis, C-axis, in which the mineral grains are visible easily. The non-porphyritic ones are further divided into radial pyroxene, as you can see here, and cryptocrystalline pyroxenes. Here in radial pyroxene, you can see still some orientation. Even though the grain sizes are very, very small, you still see some orientation. But in cryptocrystalline pyroxene, that is at all. It is microcrystalline, and you can it almost seems glassy, although in higher magnification it's not, but you can see it from this magnification, it seems to be. What was also visible was compound chondrules, which occurs when two chondrules collide, but one of them has not yet solidified. So as you can see over here, is my cursor visible? Just wanted to ask.
Yeah, it's visible. Continue. Yeah, it's visible.
Okay, perfect. Thank you so much. So this area is where, so this one was still molten or semi-molten when this collided with it. So these are the types of chondrules that you can, although compound chondrules are rare, but porphyritic and non-porphyritic are the most common types of chondrules you will notice. Now we move on to the main minerals in order of abundance. The first is enstatite, as its name. It's magnesium rich, and it's an orthopyroxene end member. These gray black grains are all enstatite. Also previously in this one, this entire grain, these are all enstatite. Next is plagioclase. The dark area in transmitted light is plagioclase because they are not visible they're only visible in reflected light. So this darker gray is the plagioclase. The composition is somewhere between the two end members of albite and anorthite. And these are always microcrystalline. Then last is olivine with the magnesian end member, forsterite. And if you see these high interference color grains all over here, these are all olivine. This one is a particularly rich chondrule, olivine-rich chondrule, but overall, enstatite has about 2 to 4 volume% of olivine across all thin sections. Then we move on to the sulfides, which is what differentiates the enstatite chondrites from all other chondrites. The first is kamacite and taenite. These are both iron nickel metals. This round bright, the highest color reflectance is the kamacite. Taenite was also present, but the difference between the two is that just the percentage of nickel is higher in taenite as compared to kamacite. Then we have troilite, which is iron sulfide. It's present as singular grains. It is present in between enstatite grains with the plagioclase in the interspecies with the plagioclase. It is also present in the center of kamacite grains. Then we have dobrolite, which is the iron chromite. This has a similar color to troilite, but when you see in comparison with kamacite and troilite, you see that it's a different grain. There is schreibesite, which is iron phosphide. This really bright grain. It is always rounded. It's very small. It's hard to find. It's usually in the corners of grains, but it's also quite rare. And then lastly, there's aldermite, which is calcium sulfide. This is a very volatile mineral, which you can see that there's a hole over here. The black part is just that it reacts with the moisture in the air and forms a different compound, which is why it's very difficult to find stable aldermite. Alabandite, which is a magnesium sulfide, is also present, and it is used for the differentiation between EL and EH, which I will come to. What was really surprising and really interesting about this sample is the presence of clasts. Now, if you see over here, they're really small and easy to miss because they look somewhat like broken chondrules, which is very common because when the bodies were accreting, it was a very violent phase. There was a lot of collision everywhere. So there's a lot of broken chondrules. But how we classified that this is a clast was because if you see in the second image, there's a outline of secondary products that is being formed, which is not part of the chondrule. Also, you can see that the grain sizes are very distinct from what is found around it. So this belongs somewhere else, not to this part. But what this proves is this meteorite was a breccia. So there it has clasts, angular clasts, probably a monomict breccia, which means clasts of its own body. But definitively it was clasts. So it points to a violent period. Next, now that we have identified the properties of the chondrule, we need to try to classify it. This is the second part of the first objective. A little bit into how an asteroid parent body looks. Mostly they follow an onion shell model where the core has the highest temperature for the longest time. That is why they can have the highest degree of metamorphism, but it is not high enough to form to allow melting for the whole parent body. So these are for smaller asteroids. Are undifferentiated asteroids or chondritic asteroids are usually smaller, and that is again proven by the fact that only the core has extensive metamorphism. As we move towards the surface, the heat dissipates and the metamorphic grade 3 or petrologic grade 3 is the outermost layer, which contains the most pristine samples without any heat damage to it. On your left, you see a metamorphic grade 4, where you see distinct grains and you also see distinct boundaries between the chondrules and the rest of the meteorite. On your right, you see a metamorphic grade 6, where most of the grains are of the same size. These dark parts over here correspond to the sulfides, and these are also approximately the same size as the silicates. So this is how a typical asteroid parent body would look like. Now, in order to identify the petrologic grade, that is the degree to which a meteorite is thermally metamorphosed, we look at these 4 criteria. There are more criteria, but these 4 are the easiest to use for distinction. There's chondrule delineation, which would mean this boundary over here. How cleanly can you see each chondrule? In grade 3, which is the least equilibrated, you see it very well, whereas in grade 6 is highly crystallized, like here, where no chondrules are visible whatsoever. Then we look at the olivine content. So how much of olivine volume percent is present in each meteorite sample. Grade 3 has some, and grade 6 is all of it is metamorphosed to form enstatite. There's chondrule glass, which is very difficult to preserve. And then there's chondrule feldspar, which is the plagioclase. And here you see smaller grains, and here you see larger grains in grade 6. Now, in my samples, we found all of this. We found every single grade, which is something that is not something that I haven't seen in literature yet. These are 2 thin sections that I've just, as an example, I've used. This was present in most thin sections. Here, it's predominantly grade 4, which is it's less equilibrated. It's not unequilibrated like grade 3, but not as equilibrated as grade 5, because we can see clean boundaries, we can see large distinct grains. However, class A is corresponding to petrologic grade 3, because here we see glass. Glass is usually it's amorphous, it's not crystalline, and it has this brown color, and it is interstitial. So presence of glass is very distinct to grade 3. Then we have here class D, which is grade 5, where you can see 1 or 2 grains of like similar size. You can still see the boundary, but it's not very clear, and the sizes are equant. And lastly, this is class C, that corresponds to the petrologic grade 6, where no chondrules are No chondrules are visible. All the grain sizes are similar, and there is no distinction between the 2. So now that we have seen the metamorphic degree, the types that are found over here, the next step is to classify them into groups and subgroups. So enstatite chondrites are divided into EL and EH, where EL is low bulk iron, H is high bulk iron, but it is further divided into A and B in each type. The subgroup can be ELA or ELB, EHA, EHB. So my samples fall distinctly into the EL group. It has a few criteria that makes its distinction straightforward. The first is a dominant sulfide. There's either alabandite or 9-angerite. Alabandite has manganese, and this has magnesium. And there was an abundance of comparatively of alabandite, like you can see over here. Then is the nickel content in the phosphide, which is not shown here, but that would be the schreibesite. Then the silicon in the metal, like the camosite, that is lower than EH. The titanium in the troilite, so these grains, and then the chondrule size, which is much larger. So therefore, my samples fall into the EL group. Further subgroup classification is based on the sulfide studies, which is troilite, alabandite, dobrolite, and camosite. So the chromium iron content and the nickel content, in addition to just abundance of dobrolite, puts my samples decisively into the ELA group. So now the sample has been studied and it has been identified. With this information, I then tried to understand how the sample came to be. What was the journey that it followed? The first was to try to find its age. This was done with the help of manganese 53 manganese radionuclide, which decays to chromium, which is measured. Based on 2 different anchors, the age was 16.7 or 16.6 million years post calcium aluminium inclusion, where calcium aluminium inclusions are considered to be zero formation. The age is zero. The problem in this isochron is that this age does not correspond with literature. A largely metamorphic grade 4 sample should be approximately 4 to 5 million years post CAI, but as you can see, the age is much higher. So it's a much younger meteorite. The reason for this could be that since it is a brexia and the sample that was used could have had different pieces of different grades, a starting point, which is very important to draw a regression like this, was not established. So since the starting point was not found, therefore the age given is somewhat of a mean between all of the grades. Next is the noble gas systematics, which is also very interesting. So there are two types of exposures that a asteroid body encounters. The first is galactic cosmic ray, which comes from all direction, is very strong and has a very high penetration depth, which is why if you look at the legend, 4 to 6 would all lie here. Metamorphic grade 4 to 6 would all lie here. If we think back to the onion shell model, these are all inside. It's core, not the core, but like to center and then to level 4. Therefore, the depth, so you can see that the penetration depth is quite high for these samples. But for EC3, which is on the surface, you have a solar wind component. These are much weaker, have a much lower penetration depth, and therefore they are only on the surface. But my sample, this gray arrow, this triangle, plots over here, which was very surprising because it is predominantly a metamorphic grade 4 and therefore should fall somewhere here. But a solar wind component this high could have two reasons. First is that my asteroid body is a regolith brachia, which means that the pieces, there was an impact, the surface broke, and then samples or pieces of metamorphic grade 4 came on the surface, where they were then bombarded with the solar wind component. Alternatively, when this meteor broke from the parent body, and when it was orbiting the sun, it could have had an orbit very close to the sun, in which case a lot of solar wind exposure could be possible. And that also accounts for a very young exposure age, which means that every time it got close to the sun, the system was reset because it is heat sensitive. So so if I try to make a timeline out of this, my findings conform with the onion shell model. But why I am assuming only a quarter of my asteroid parent body was bombarded and broken up to a regolith brachia is, so the first is that the accretion of the parent body occurs according to the onion shell model. A catastrophic impact happens and creates a rubble pile, which is something like this, where all the metamorphic grades are mixed up together. Then there is regolith formation on the surface, on which there is surface irradiation of solar wind. Another impact breaks a part of this surface, which then orbits the sun for a substantial amount of time before finally entering the Earth's atmosphere and us finding it. Why I am assuming that only a part of it has been bombarded and broken up is because there have been other samples that have been studied throughout, for almost a few decades now. And this kind of rubble pile or high noble gas content is not found in literature anywhere. So it could mean that there has been impact on like other parts of the parent body from which we might have obtained samples, but it's highly speculative at this point. So, in conclusion, my samples were ELA with a dominant petrologic grade of 4 and clasts ranging from 3 to 6. The chromium isotopic data does not provide the chronological information that we had hoped to find, but that could be due to the heterogeneous parent body. The cosmic ray exposure age is lower; it's quite low. Could be due to a close orbit to the sun, and the parent body is likely a rubble pile from which the sample was from the regolith of this rubble pile. Thank you. Please, if there are any questions, I would be happy to answer them.
Thank you. Nulekha, it's very nice. You had a good presentation, I would say. But
Thank you.
we have another gentleman waiting for us who will be giving a talk. But you have given a wonderful talk. And I am looking forward to hearing you more about your topics. And please be in communication with us. We are conducting Asteroid Day every year. So we are looking forward for your type of work, and we are encouraging younger people to look for. In fact, I'm very happy that you are a part of the field work also. Normally, for field work, many people shy off. But here I'm finding you that you are doing a great job in even finding the sample. This is what is required. So thank you very much. And we look forward to hearing from you more. So we have now our next speaker, Dr. K.R. Subramanya, and he will be talking to us. Rather, he will be giving his lecture today on the topic that he has told us that will be very interesting, Kaveri crater. In fact, I think Dr. Krishnamurthy did mention about Kaveri crater, and now we are more interested in Kaveri crater primarily because we are also looking for the age of the crater. This is where we are also trying to find out what could be the age of Kaveri crater. So, and to say some few lines about Professor K.R. Subramanya, we are good friends first. Thank you very much, Professor. And he has been with Mangalore University, Department of Geology, and he had his background learning at University of Mysore, his MSc, and later on in Bangalore. So he is a full. He retired from Mangalore University recently, and we are asking people who are doing this kind of work to take up this work not only up to Kaveri, there could be many more craters which we are unaware of. So the floor is open for you, doctor, and we are eagerly going to listen to you. And after your talk, we are going to have a short exhibition in Nehru Science Centre on meteorites. We have already made arrangements to display that for all the observers who are attending this meeting. We are going to give them time to see the exhibition of meteorites. They are of different class and of different parts of the world. So with these few lines, the room is open, sir.
Yeah.
We are here to, eagerly waiting to hear you.
Oh, thank you very much, Dr. Bharat. It is a pleasure to speak to you, the audience here. I've been looking forward to this occasion because I want to give more publicity to the Kaveri crater because there is some reasons are there. I will tell you as I go to the next slide. So, yeah, see, this is a geological map of southern India. Perhaps some of you will be wondering why I am giving so much of importance to geology, because the Kaveri crater should eventually modify.
Sir, your slide is not changed. You have to make it full screen.
Full screen, right? One second.
F5. Press F5.
Is it okay now?
No, not yet. Or on the right side, you have that small button near to the percentage sign. Where your cursor is there, na? Just bring the cursor down. Now it is visible. Yeah.
Okay. Thank you. See, in fact, I am not very familiar with this. My son is there who is assisting me.
No problem, sir. No problem. Okay. Thank you.
Okay. So anyway, see, I am showing my first slide is on the geological map. As I told you, Kaveri crater, it's not being accepted very much by the geologists. For a simple reason, the entire geology of southern India will have to get modified. So, and again, see, I am used to speaking in a lighter way. So, please don't mistake me. Okay. So, this is another slide of the geology of southern India. This part is known as the Dharwar Craton. And as you see, these are the mountainous terrain made of charnakite, a rock called charnakite, which is a high-grade metamorphic rock that is belonging to the granulate facies. But as you can see, there is an anomaly here. Again, you have a lower grade metamorphic rock in this region. So this is why we have this particular anomalous area was of interest to me. That's why we took up this study in detail. Again, see this line, or I will go back to the earlier. This dotted line is known as the Vermeer line, which separates the amphibolite facies of rocks from the granulate facies of rocks. Or the amphiboles here gradually transform into pyroxenes. So this is the called very popularly known as the Vermeer line. Yeah. Now the Vermeer line, this was considered to be the junction between granulate and granite greenstone terrain, or the Dharwar. Subsequently, it was Moyar Bhavani shear zone that was made at the boundary. Currently, the Palghat Kaveri shear is considered to be the boundary. Like this, we geologists have been having very, very different opinions for the junction between the granulate terrain and the amphibolite Dharwar craton. So again, regarding Nilgiris, there are different opinions that have undergone dextral strike slip with respect to Bidigan-Rangan hills, and the relative movement is of the order of 70 kilometers. This is one opinion. The other opinion that there is no strike slip component in the Nilgiris, and it's only a vertical displacement. So it's obvious that there are as many divergent views as there are geologists. Am I audible properly?
Yes, sir. Loud and clear.
Pardon?
Yeah, you are audible. Loud and clear.
Thank you. Now, however, there are some observations that point to some unusual features. The block forming BR hills has been uplifted along a series of parallel faults. This is according to BP Radhakrishna. And then Moyar Bhavani shear zone dips southwards, whereas the Chennamalai Noil shear zone, Dharapuram shear zone, and Devatur Kallimandiam shear zone dip to the north, defining a regional scale flower or palm structure. This is another view in this area. And then some of the largest north-south and north-northeast trending lineaments extend to about 150 kilometers in the eastern parts and are demarcated either by dolerite dikes or pseudo-tachylite. I am underlining it. These post-date all regional trends within the area and appear to be the angles. Again, this is another important line to be noted. Pseudotachelites associated with impact structures may form in radial and concentric fault systems that help to define the megascopic structure of the crater. Now, some unusual megascale features. Now, this is the Google map, southern India. This is Bidigirangan Hills. This is Malay Mahadeshwara Hills. This is Nilgiris. This is Anaimalai. This is Kodaikanal. As you can see, there is a beautiful depression, circular depression, and then this is Meteor Dam. This is River Kaveri. So this is the area which we have identified as the Kaveri crater. This is a hill-shaded gray scale map. See, again, you will see a beautiful circular depression surrounded by mountainous terrain. One more thing which I want to highlight. Here, you see there are numerous fractures. One of these fractures here is more or less parallel to the arc. Again, more or less some similar thing is happening here. And if you come to the eastern side, there are some relict hills. If you connect them, that will be part of the circle. Again, there is one more set here. That's again a part of another eastern arc. These two arcs also have significance. I will come to that. Again, this is slope map. You can see the same circular depression. One arc of this part, a part of this circle, another arc here. Again, similar feature, and you will see that there are radiating fractures. This is BR Hills fracture. This is MM Hills. This is Shiva Hill massive. This is Kollimalai massive. And then, as I told you, this is Anaimalai, this is Kodaikanal. And again, I draw your particular attention to this fracture zone. Now, if you look at the structural aspect of it, this is the inner circle which I have shown you already. And then you have, I showed you another arc fault-like feature here. If you connect these, this will be a second or outer circle. And then within the circle, you will see innumerable granite intrusives. And also you will see a similar granitic intrusive within the outer circle. So, and then I had shown you already some radial fractures. Again, if you go into greater details, you will see there are too many such radial fractures as well as the concentric fracture. And if you draw a cross section, what you will notice most importantly is that this is the rim of the crater. This is also a rim of the crater, and there is a central uplift here. The same thing you will see in other two sections too, that this is a very important, significant aspect of the circular depression. And then look at the drainage pattern. Even here, the circular depression is reflected in the drainage pattern also. Now we will come to geophysical anomalies here. Now, this is a Boger gravity anomaly map of the area. This circle is the Kaveri crater, and you will see that there is a gravity high here. This is very unusual because all around you have gravity low, only here you have the gravity high. And this is the Curie isotherm map or magnetic basement map. You will see that along B6, there is a downfall, that is magnetic basement has gone down. Again, along B5, there is a downfall, magnetic basement has gone down. There is a better picture of that. This is minus 32 kilometer Curie isotherm point, which more or less coincides with the Kaveri crater. So, and then surrounding them are 30, minus 30, etc. Again, it shows that below the Kaveri crater, the crust is relatively cooler compared to the surrounding area. Same thing, minus 32 kilo basement surrounded by minus 30. Area has undergone retrograde metamorphism because, as I told you, surrounding rocks are all charnakites, whereas what the rock within the circular depression is amphibolite facies. Now coming to the seismic velocity structure, the Kaveri crater starts from somewhere here, 40, and it ends here. You will notice that the seismic velocity is 6.1 kilometers per second, increases to 6.5, then suddenly drops to 6.0, then increases to 7.1 and 8, and below is, this is the Mohoroisic discontinuity or Moho. And if you will notice here, the Moho is sloping like this, so all of a sudden here it raises. So there is a upwarp of Moho to the tune of 4 to 5 kilometers. And if similarly, as I already shown you, Boger gravity also more or less coincide. Positive anomaly of the Boger as well as Moho upward, they have good relationship. Same thing. So it's a Graben structure. Velocity also depicts a 4 to 5 kilometer Moho upward near Chennimalai. There is an anomaly here also, where when there is a large size Graben, normally the Moho also is down-faulted, but here is an upward. This also explains that the source for the gravity high in the region is not the ultramafic intrusions into the crust, but the mantle bulge. Okay, now these are the anomalies which led us to think whether this was created due to an asteroid impact. Now, just an introductory part. Earth in its early history must have been heavily bombarded by large extraterrestrial objects, at least 10 times more than what we see on the moon, because the surface area of the Earth is 13 times and the gravity is 6 times larger. However, the records available on the surface of the Earth are very meager, as most of the impact sites will have undergone modifications due to Earth processes, denudation and tectonism. It is now accepted that impact events, especially the large ones, have had a major role in the formation and early history of the solar system. Many chemical and dynamical problems concerning the origin of the moon are explained by the current theory that the moon formed as a result of a collision between a large-sized object and the larger proto-Earth at about 4,500 million years ago. As of now, about 190 impact craters have been recognized internationally. Craters are currently classified into 2 types: a hypervelocity impact crater. This is restricted to impacts where evidence of shock metamorphism in the target materials has been detected. This can be a simple or a complex crater. And then, what are the evidences for a hypervelocity crater? Shatter cones, planar fracture, planar deformant feature, weather feature, diaplectic glass, and then stishovite. Pseudo-trachyte is a supporting evidence. Normal impact crater, those without signatures of shock metamorphism. This is a simple crater. Normally, the simple crater, the depth will be more, slightly more, and relatively speaking, whereas in a complex crater, depth will be very shallow, less, whereas the width will be very large. This is what happens immediately after there is an impact. There is a central peak, and then there are innumerable faults, dipping faults, which we in geology call as listric faults. These are called curved faults, are called listric faults. And this is the rim. And then what may happen subsequently because of erosion, this rim may not appear. So, and then the listric fault, which is here, may look like a rim, therefore it's called as an apparent crater rim. Now, as we all know, there are some 3 large craters: Rutherford, 300 kilometers, Sudbury, 250 kilometers, and then about 170 kilometers, that is Chicxulub crater. In India, there are very few examples of impact crater: Lonar, Dhala, Ramghar, Luna, Simlipal is started recognized, and then Shiva. These are the craters which have, some of which have been recognized, some are yet to be recognized. The crater that is I am talking about is about in the southern peninsula. These are the geographic coordinates. It is part of the Precambrian terrain and to the south of the Dharwar Cretan. The region is known as Southern Granulate Terrain or SGT. However, the nearly circular depression or the crater, which is to the east of Palghat Gap, is occupied by granitic gneisses. And then I will, from megascopic, I will now go on to the mesoscopic feature. This I have already shown. This is the inner rim. This is the outer or apparent rim. The blue stars that you see here, 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 they are all occurrence of pseudotachelites. Pseudotachelites also can occur when there is a major fault. But this kind of a distribution over a very large area is only characteristic of an impact crater. So that therefore, this is one important evidence to show that this region has been subjected to an extraterrestrial impact. And these are, of course, pseudotachelites. This is also called, sometimes called impact breccia. These look like tachylite, but it's not tachylite, it's pseudotachylite because the composition of this black rock and the composition of the surrounding rock are same. That means these rocks have melted to give rise to this kind of a rock called pseudotachylite. And when you see this type of a feature, you call it as a breccia, impact breccia. That's also in use. In another pseudotachylite, a very huge one. This is another picture of pseudotachylite. This is only I am showing that there are plenty of sites where pseudotachelites occur very close to the rim and also up to beyond the rim up to apparent crater rim. This is one I am not very sure about this. This looks like a shatter cone, but it may or may not be. We have not come across another shatter cone, undisputed shatter cone so far. Then I come to the microscopic feature. I think all of you are familiar with this type of a structure. These lines are planar deformation features. Thin, closely spaced lines are PDF, and then thick black lines like this are PF. The crystallographic direction of PDF is 1013, and that of planar fracture is 2241. How did I come to this? I must acknowledge here that the Geological Society of India, along with the Savitribai Pune University, conducted a workshop on universal stage. I am sure most of you will not have heard of that. When we were in MSc and doing research, we were using universal stage mounted on a microscope for determining the twin laws in plagioclase as well as the anorthite content of the plagioclase. And subsequently, these have become obsolete. Nobody is using it. Luckily for me, the Geological Society and the Pune University conducted a workshop. And this workshop was, the resource person was Professor Nehru Chirukupalli, emeritus professor from City University of New York. He had come all the way, and I personally took part in that workshop. And then with his help, I was able to identify the crystallographic orientation of the PDF as well as PF. And when I showed this to some foreign expert about the PDF and PF, he said, no, this is not acceptable. Then I told him, the crystallographic plane, the crystallographic plane, if this is the plane of the thin section, and if it is the plane of the PDF, you naturally, along this plane, you will see it wider and not sharper. But when you tilt the h-axis by 25 degrees or so, this becomes very sharp and closely spaced. That's what I explained, and finally he accepted that it is a PDF. So there is a PDF with 1013, and there is a PF with 2241. Now this PDF 1013 normally develops when the pressure is about 15 GPa, gigapascals. So therefore, this is almost 100% confirmation that this mineral, quartz, has undergone shock metamorphism. And this mineral is from a quartz vein, which is in the Shivan-Malay cyanide. Shivan-Malay cyanide has been imported by both pegmatite veins and the quartz vein, and the quartz sample is from the quartz vein. And so it is the Shivan-Malay is very close to the center of the crater. Therefore, there is 100% absolute confirmation that this is a shock metamorphic feature, where the pressure could be of the order of about 15 GPa. Now, this is another example of this quartz from the same area, more or less. You will see here two sets of PF, planar fracture. Again, this is a definite conclusive evidence for the shock metamorphism. This is again another quartz grain. This is a quartz grain. This has been surrounded by pyroxene. Here also. Now, this is under polarized light. If I see this under the analyzed light, what you see is this portion has become glassy. It has lost its crystal structure, whereas this part still retains its crystal structure. Same thing here and also to the texture. That means this part has been subjected to high pressure and it has lost its crystallinity. It has opaque. That's the reason why it's opaque. So this normally is referred to as the diaplectic glass. This is a picture of the plagioclase grain. You will see that there are a lot of clouding, and also plenty of iron material is here. And this iron material looks like a cobweb. And if you concentrate on this area, you will see numerous fractures, which can be planar fracture, and also there is slight bending of the fractures which are in this direction. The same, this part, enlarged portion of this part, you will see in the next slide. As you can see here, you see the PF and also bent lamellae, but what you will also see that some part of it has become diaplectic glass. That means it has lost its crystallinity. It's amorphous. This is another grain of plagioclase bordered by fracture. And again, if you look at the analyzed light, look at it in the analyzed light, this part has become diaplectic. Some portion retains the twin lamellae, some are hazy. So you will see that this grain has also been subjected to very high pressure. This is again another plagioclase from another side of Voddanchatram, which is very close to the southern rim or north of Kodaikanal. Here you will see that there are PDF-like features running like this. They have been intersected by PDF features running more or less north-south. This portion gives a checkered appearance. And then again, this is in this direction, you will see there is another set of PDF in this direction. Again, these two crisscross. There is one PDF, another PDF, third PDF. They are all intersecting each other, and there may be one or two PFs also, planar fractures too, which is not very prominent. This one, for example. This is again under cross-nickels or analyzed light. There is no birefringence, very low birefringence, and of course, there is no twinning. Plagioclase will have a lot of twins, but here the twins have disappeared because of high pressure. This is another grain is from area close to Malay Mahadeshwara Hills or MM Hills, which is to the north of the crater, that is just adjacent to BR Hills. Now, this has, all of you must have heard of clouding in feldspar. Here, this clouding is so intense, this is called as a sooty feldspar. That means it has become so dark, that's why it looks like as though there is a smoke here. And this part, if you see the enlarged portion of this part, again here you will see two sets of lineament-like features. This again is a checkered PDF. You will see which crisscrossing, it looks like checks. Again, this is another very significant example or proof of high pressure. This is the thin section of garnet. As you all know, garnet doesn't have cleavages, but in this case, you will see at least 2 or 3 sets of cleavage. One set, second set, and then one third set is there. So normally garnets do not have cleavages, but you see here planar fractures. This is again another addition of proof. All these evidences point to a hypervelocity impact because, as I told you, at least 15 GPa pressure has been, minerals have been subjected of at least up to 15 GPa. And checkered plagioclase in particular happen when the GPa is in the order of 25 to 30. So, therefore, it is right to call this as a hypervelocity impact crater. The diameter of the crater is about 120 kilometers. Accepted ratio between the diameter of the pre-impact land and the crater is 1:1.25. On this basis, the diameter of the pre-impact land can be taken approximately as 100 kilometers. The ratio between the diameter of the asteroid and the impacted land is 1:20, which gives the diameter of the asteroid as 5 kilometers. Now, therefore, this after Rutherford, Sudbury, Chicxulub, this becomes the 4th largest crater on the surface of the Earth. And then, can we approximate the age of impact, age of the asteroid impact? As I told you, shown you the quartz grain, is from Shivan Malay cyanide, and age of the Shivan Malay cyanide is 623 plus or 21 million years. This I have already mentioned. Now, Vaddan Chatram anorthosite, which I have showed already, the age of intrusion is about 560 plus or minus 12 MA, and it has PDF developed in plagioclase. A huge impact normally creates large quantity of melt, and it has been seen that within the crater and also within the apparent crater, there are innumerable emplacements of granitic bodies. Ages of these granitic bodies range from 580 to 510 million years, with a mean of 545 million years. And then the metamorphic age of paleoproterozoic rocks, that is originally belonging to 2.5 GA, within and close to the crater range in age from 576 to 512 million years, with a mean of 548 MA. These age data indicates that the impact could have occurred at the Proterozoic-Paleozoic boundary. Whether the impact has contributed to the Cambrian explosion is worthy of investigation. Cambrian explosion is sudden explosion in the organic world at the end of Neoproterozoic and the beginning of Paleozoic. Okay. Now, with all these data, if we look at the geological map and take a cross section, it should look something like this. From north, Dharwar Craton with green schist facies, that is the lowest grade of metamorphism. Then as you move southward, you get the amphibolite facies, which is slightly higher grade in metamorphism. If you first move a little further, then you have the firmer line, where the amphiboles gradually convert to pyroxene, and then it retains the banding in some area. Therefore, pyroxene bearing rock is called now we call it as a charnockite, and you have banded charnockite close to the firmer line. As we move further south, the charnockite becomes granulated. And if you go further south, you have charnockite, which is ultra high temperature metamorphism, which has experienced ultra high temperature metamorphism because you have sapphirine minerals here. That means there is a continuous increase in the grade of metamorphism, green schist, amphibolite, banded charnockite, granulatic charnockite, ultra high temperature charnockite. So it is a simple, very simple increase the grade of metamorphism as we move from north to south. But here there is an anomaly. Now, this area where you have the crater, it is lower in surface by about 1 kilometer, and then in this region, the charnockites have converted to gneisses. That is, there is a retrograde metamorphism. You have charnockite, whereas here you have gneisses, which is amphibolite phase. And if you look at the magnetic basement or Curie isotherm, again it is deeper at least by 1 kilometer or more than 1 kilometer. That means because of the retrogression, the rocks here are cooler, therefore the Curie isotherm is also depressed. Again, if you go further down, you will see Moho itself has been uplifted by about 4 to 5 kilometers. So all these evidences, mineralogical, petrological, geophysical evidences confirm that it is a hypervelocity impact of a huge nature, very large nature. Therefore, now this needs support. There a lot of further studies are to be carried out, but whatever evidences I have provided so far definitely confirm that it is a hypervelocity impact crater. Now, in spite of all these evidences, some of us geologists are not willing to accept it because you have to change the geology of Southern Peninsula, where instead of so many suture zones, shear zones, here, we have to eliminate all those things, and we have to say that these suture zones are nothing but the result of a hypervelocity impact which has created the Kaveri crater. Okay, with this, I almost come to the end. So I am extremely grateful to Professor Narendra Bhandari for this opportunity. Dr. Bharat Adur has been in constant touch with me to see that I take part and make a presentation. Professor Prakash Narasimha of Mysore University and Professor Tirukumaran, Government Autonomous College, Salem, have been of great help in this work. Nehru Science Centre and Akash Ganga facilitated my entry into a new group of astro enthusiasts. My thanks to all and also those who are present for this presentation. Thank you, and I will be happy if there are some questions. I will try to answer them. Thank you again.
Thank you. Thank you, Dr. Subramania. Your queries on Kaveri crater has been very interesting. Has there been any impact melts that you have been able to collect?
Pardon? Can you please repeat, Dr. Bharat?
No. In your sample collection, I would like to know whether you had any impact melts.
No. Impact melt, as I told you, all the granite bodies which have injected into the crater, they were impact melts which have subsequently injected into the rock above, and they have consolidated, they have become granitic bodies. We don't have only pseudo-tektites. They show evidences of melting. But pseudo-tektites, of course, there are plenty of pseudo-tektilite occurrences. All these are result of partial melting of the rock in the surrounding area. Whereas a thick sheet of melt is not seen because all those melts have become magma and they have injected as granite into the crater and also into the apparent rim of the crater. So as such, you don't have evidence of melt. You don't have, only, as you can see, diaplectic glass indicates that it has lost crystallinity. If it is solid state conversion. And pseudo-tektilite melting is there. And the all melt within the crater have become granitic bodies.
Okay. Thank you. Is there any questions, short questions, because we are going to break for lunch, because we have to again return back to the further part of the program, which will be from 2 o'clock. There is a question, I guess, from Dr. Prakash, Professor Prakash. Yeah, please ask your question, sir.
Yeah, Gopal Krishna. Yeah, please go ahead.
You will have to unmute yourself. Please unmute. Whoever
it says, yes. Okay. Thank you. It was a very nice talk, Professor Subramania.
Thank you.
We had discussed about this almost 10 years ago.
Okay.
Yes. Now, I just wanted a simple query. The radial fractures that you talk about in the crater, they are all only going sort of outside radially, or do you see cracks or fractures within the crater body also?
Within the crater body, there are not many fractures, and they are not specifically oriented in any direction. For example, the Noil River, it joins the Kaveri, is a east-west line. So there may be a small fracture running east-west within the crater. But as I told you, the entire crater is highly fractured. Therefore, it's very difficult to find linear fracture within the crater.
Okay. And just a corollary to this question, are there any breccias that you have seen inside the crater body or adjacent to the crater that may have formed at that time because of the impact? So, have you seen any breccias? Breccias, that is where admixture of rocks which have been consolidated. Is there any sample of that available?
So breccia, no, see, only within the crater there are no, we have not come across any breccia yet.
Okay.
Within the crater.
Okay.
Outside the crater, the pseudotriangulate breccias are there.
Okay.
And then we saw something similar to a sewage sample.
Okay.
Near Kambam. You must have heard of Karur Kambam.
Yes, Karur Kambam, yes.
Yeah, we came across some material which is very similar to breccia, but we were not very sure. Therefore, we have not conducted any further experiments on that. As you know, we did only, we had, we have done the field work for only about a year. A lot of work is to be done, but unfortunately, we did not get any financial support from the government agencies. Therefore, we had to discontinue our work. And if, to the extent possible, now I am trying to collaborate with Professor Tirukumaran of Salem. So we are trying to do whatever we can do. As I told you, even going to the Savitribai Pune University, I went on at my own car. So there is not much of a support from the government side for this kind of a work. I am really sorry to say that. So that's the reason why we have not been able to pursue the work with the vigor that is required for this kind of a huge study.
Okay. Very nice work. Congratulations on putting up a very nice talk. It was very good. Thank you.
Thank you very much. Thanks to all of you.
Hello. We are breaking for the lunch now, and we'll
I will not join
back
Bharat.
again at 2 o'clock.
Dr. Bharat, I will not join you.
Okay. Okay, sir. Thank you. So we meet at 2 o'clock, and it's the same program will continue till 6 o'clock. So it's supposed to, we have to keep up to times because we have more professors coming online. So we meet again at 2. So thank you very much, Professor, and we look forward to seeing you further.
Thanks a lot.
Thank you.
Hello, everyone.
Hello. Good afternoon.
Good
We are
afternoon.
back from the lunch. Now we will start the second session for the afternoon. Before the talk, one of our members and our speaker has decided to show his small 7-minute small video about how meteors are captured. And this is done right from Mumbai. So I hope I think we need more number of people to come by, right? Should I wait for 5 minutes? Hello?
I think you can wait for 5 minutes.
Madam. ज्वाइन नहीं हुआ है क्या लिंक Hello.
Hello, Dr. Bharatji.
Hello. How are you?
I am fine, thank you. I see there are 8 people online right now. I think 7, 8, 10.
Yeah, we are open now. We want to show you a small video clip. So I thought,
yes.
People come by. Can we show that?
What was the total audience before the lunch time?
Yeah.
So
Okay.
I think we can start because those.
No, we need the speaker.
Okay.
And
Okay,
participants for
speaker.
that. We are awaiting for them.
Yes. The morning session was very good, full of knowledge and very well done lectures. So I really learned a lot. It was very good.
Now,
very
I think the afternoon session also we want to make it. We have got one meteor here and we just visited. We just visited the Nehru Science Centre. There is a stall for asteroids named Meteorites at the entrance of the Science Museum. So we were looking at those, and then there are moon rocks, Mars rocks, and I guess there are some asteroids samples also.
Okay.
So we have an exhibition already along with the talk, and we are expecting children to see that in the Science Museum.
Okay. Only those people who are sitting outside will be missing it. Online, because we'll not be able to see. Onliners will not be able to see those exhibits.
Onliners, we have not actually planned this, but I think it was late night arrangement to have the exhibition. So we have asked for that as a video clip, and I think we post it to you wherever you are, and you can watch it on your set computers.
Okay, that's wonderful. That's
See,
wonderful.
our International Asteroid Day doesn't only mean meteors. It means meteorites, talks, and also the exhibition.
Exhibition, yes, of course. It does.
And we have a program from 10 to 6. The museum closes down at 6 o'clock. So the museum will be able to show until 6 o'clock, I guess.
But also your the time management is excellent. I mean, things are happening just in time. So everybody is keeping this. Yes. I said the time management is excellent.
Okay.
All speakers have stuck to the time, and so everything is happening.
There has been a delay of 5-10 minutes because we don't want to cut the speaker till he concludes.
That's all right.
I hope Madam is there, Dr. Maras.
Yes, Bharaji, ma'am.
Okay. We are going to welcome you with Meteorite in my hand.
That's excellent. So which meteorite is this?
So we want to begin the talk with showing you the meteorite, and then we want to introduce you to the audience.
Okay. So actually the initial talk that I made was basically asteroid, an explanation of asteroid, which first two talks have covered. So I tried to put something else quickly, and I hope it's okay then.
Yeah, we can.
It's okay.
The reason why this exhibition happened is primarily every program we do have an exhibition of meteorites, so that the school children can come and see some samples. They can hold it in their hand and give them that thrill, and then they are able to see more about it. This is one objective. Second objective is we encourage citizen scientists also to come by. So we have one citizen scientist who has given a small video clip of his meteor observation from Mumbai. Is that right, sir? So he has given a small video clip. So if you allow me, we can see the video clip and then we can start the lecture, madam.
Oh yeah, that sounds good.
And then I welcome you already with my meteorite in my hand. This is the meteorite. It's essentially a tektite and it is known as a Indochinite.
Indochina, okay.
So this is the meteorite we actually carry it from every meeting. So the objective is to make the speaker's talk more relevant with the meteorite. So we keep showing that all the time. And we have a surprise from Hasna. We have been able to get one sample from Morocco also.
Oh, that's great.
Yeah, we want to welcome her with her sample. Morocco sample. No, nothing personal, but it is visible in our museum also right now. So with that few words, I would like to welcome Professor Kuljit Kaur Marhas. She is a very good friend of ours, and she is the section head of Planetary Laboratory. Please understand this. Planetary Laboratory is a big analysis section, and she is also her research interests are in isotope cosmic chemistry, stellar evolution, and nucleosynthesis, origin and early evolution of solar system and its planetary bodies. She's also she has won several awards. In fact, for me to enumerate, I would already congratulate Kuljit for so many awards. We are very happy to have you get so many. But what I'm most interested is which I want to share with all of you. She is actually heading nanosecondary ion mass spectrometer, which is shortly known as nanosims, which is used in analyzing I guess, madam.
It's kind of non-destructive, yes, you can say.
Yeah. So she has, and her earlier learning was in Indore. BSc was in Indore, MSc was also in Indore, and her PhD is from Physical Research Laboratory. And the latest that I had to congratulate her last year, she was a Fulbright scholar at Carnegie Institute of Technology. Is that right, madam?
Carnegie Institute of Sciences, yes.
Yeah. So, besides that, she has been on several committees of planetary sciences and also on these topics which she is already working upon. And I am looking forward to her in our future Asteroid Day programs too. So, besides that, she is also a council member for Meteoritical Society. And our interaction with Hasna was from 2015 when we had presented our papers at that meeting. And I'm very happy and proud that you were able to support us even in that Meteoritical Society meeting. So, beyond that, her basic work, she's an advisor also to uh, her programs in that. And the best part, which I would definitely like to share with you, she has also published several papers, I'm using the word several papers in both national, international, and also in recognized journals. So we have today a fantastic person and a very good friend of ours. So I'm opening up this session with Professor Kuljit. We are very happy to have you for this International Day program, and we would like to have your advice. If we have made some shortfalls or we have made some mistakes, please correct us and help us out in future programs. Thank you, ma'am. We look forward for your talk.
Thank you, Bharat Agrawalji. Thank you so much. It's a real pleasure to speak to all of you and introduce Asteroid Meteorite to everyone and the kind of work we do. And I thank you for giving me this opportunity. It's a great work that all of you have been doing, and I'm sorry that I couldn't join you last year, but I promise to stand by you whenever you do this kind of work. I'll be always there and support you. So, do you want me to start the talk, or you want me to wait a little bit until people come in? I can start. Hello. Hello. Can you hear me?
You can start. We can hear you.
Yeah, thanks. Okay. So I have been hearing to the morning session and Bandari ji, Krishnamurthy ji, everyone talk about asteroid, and really they have covered up very well why we want to celebrate Asteroid Day. So I'll just summarize in a sentence why people have been thinking about Asteroid Day celebration is basically to make everyone aware of the catastrophic event that can happen due to asteroid, and also it is related to origin of life. So in both sense, it's a big event that asteroid does. So all of you have been introduced to the asteroid belt or Kuiper belt from where comet comes. So these are smaller bodies, yeah, which have been saved in their pristine state. When I say pristine state, they haven't been altered much. So they give us a lot of information. We know that Earth has life either from, it could be indigenous or it could be exogenous. And there has been a talk that the life on Earth could be from asteroids or from comets. So we know this. There is a great participation of asteroid belt or comet belt for our existence. So why can't we use Earth samples? So why are we talking about asteroids or meteoroids to understand anything that is related to solar system? The reason being is Earth has been churned a lot. Yeah? So there has been volcano, there has been wind erosion. We have altered most of the pristine stuff. So it's very difficult to find very pristine stuff on Earth to understand the solar system or evolution of solar system, right? Now, here I just wanted to quickly show the asteroid belt and Kuiper belt. So we know that Jupiter didn't let the planet form near it, and there has been a gravitational instability somewhere between Mars and Jupiter. And these objects are very small, thousands of kilometers. So few of them are just as it. Few of them did have radioactive element to go through the differentiation. Like Earth is a differentiated body, has a core which is metallic and has a surface more silicate lithophile kind of a substance up. So asteroids have also gone through differentiation. So one of the talk, somebody talked about asteroids. So there was a differentiation part in it. So there's a huge classification for these meteorites that comes from parent body. So one of the question to be answered is which meteorite is from which asteroid? Yeah. So until and unless you classify them, it's very difficult to do so. So there are many classification system, and some of them have been talked by Alekha. I think the name is Alekha. So we have carbonaceous chondrite, we have stony meteorite, stony iron, and iron meteorite. So if you come to PRL, sometimes we have this in display. Yeah, all three of them. So when I say iron meteorite, it's basically core of the asteroid. Yeah. So there's a core. If we get a material from the core, it is metal. Yeah. So iron meteorite. If it is in between the crust and the core, then it is the inner material. It's stony iron kind of a material. And if you get the above material, it's the stony. Yeah. So if you want to understand differentiation, you will look for a mixture material and try to do some studies. Or if you want to know which asteroid it belongs to or what elements, for example, somebody was talking about the mineral resources. Yeah. So through meteorites, you can understand the mineral resources one type of asteroid can have, and you can target that asteroid. So it's very important to have a meteoroid asteroid to understand that. So for that case, you need to know meteoroid first. But meteoroid does not only explain that. Meteoroid has much more to explain than that. So one more point I'll put for meteoroid classification is that when the asteroid was forming, it was going through certain regions. So there are volatile region, which is called snowline kind of a region. So it has moved through a snowline region. So it has collected some ices during that, and during its formation also there are ice chunks that goes into the asteroids. So eventually this melt, and then they altered the asteroid. So this is the process that is happening after the formation. So if I want to understand the processes, chemical or physical processes that were going on in asteroids or any planetary body, solid planetary body, you need to understand these kind of alterations. So it has been meteoroid classification also has been done in two types. So it's based on aqueous alteration and also thermal alteration. So if you ever read about meteoroids, and for instance, they say it is a carbonaceous chondrite of type 3. So that means that it is kind of unaltered. If I say it's a carbonaceous chondrite of type 2, like Mukundpura, Bhandari ji was saying, is of type 2 because it has aqueous alteration. It's pristine, but it had aqueous alteration on it. So, and if I say anstetite, like, so anstetite EH4, so I know that it's anstetite meteoroid, and there has been heating till 700 or something of that, so 700 degrees. So there are classification, and you can choose according to your study which meteoroid you want to study and from which asteroid it comes. Yeah. So with this, I will try to tell you why you want to study asteroids, or other than just mineral resources, meteoroids, or say comets. Yeah. So let me give you a general view of what all can be done. Yeah. So it starts with solar system, and we can understand solar system either by observation, telescopic observation, and then back tracing or understanding other planetary system, right? But the best way is to learn through meteorites. Right? Now, meteorites that are pristine, which haven't been altered, will talk about things that happened early. The one which has differentiated will talk to you about how terrestrial bodies. So you can make a range from the T is equal to 0, formation of solar system, till the evolution till now from meteoroids, yeah, from asteroid body. So there are two ways probably you get the sample. One is you go with a mission. Yeah. So you have various mission, NASA mission, like Stardust mission went to Comet, brought back the sample. Hayabusa 1, Hayabusa 2 brought back the sample from stony asteroid and carbonaceous asteroid. Now NASA went and brought by carbonaceous meteorite from Bennu. ISRO is planning for a Chandrayaan 4 mission. We are going to get some samples from Moon probably. Yeah, from Moon in 2007, 27, 28, I guess. So we all are planning to get samples from there. But for people, I mean, for researchers who cannot get such resource, money, economically cannot get samples from the sample return mission, they bank on meteorites because they are part and parcel of subsystem. So meteorites can come from either Mars, Moon, people say from Mercury too, and from asteroid belt. Okay, so major meteoroids are from the asteroid belt. When I say I'm studying meteoroids, probably I'm talking about the asteroid belt material. Yeah? So asteroids, I'm talking about asteroids. But few of them have been classified to come from Mars. So we have Martian meteoroids, we have Moon meteoroids. Yeah? And certain orborites are thought to have are precursors of Mercury. Yeah? So this is still in question, but yeah, there are people who discuss about this. Now, coming back to the solar system formation, just quickly I'll tell you how solar system has formed. So we know that there was a molecular cloud which collapsed to form a sun at the center and then a disk around it, yeah, from which the material. Now, there are questions to this kind of a collapse. Now, what material, I mean, which material, what has contributed to the initial mix of this solar system? For example, if you look at yourself, you have iron in your body or calcium in your bones. Yeah. So where do this come from? You need calcium and potassium for your body. So where does this element come from? If you look at sun, it is mainly hydrogen and helium. It is not processing other elements. Yeah, it's a small star. It doesn't process heavier elements. So the elements greater than hydrogen and helium are inherited from the nearby stars. These nearby stars, when they contributed to the molecular cloud, they also gave up some organics from the interstellar medium and circumstellar dust from their material. So organics and pre-solar grains entered the material of solar system formation, and they went into every part of solar system, but it gets preserved into meteorites. Pristine meteorites, you will see these organics. You will also see pre-solar. So if you study organics, you can talk whether these organics are really from interstellar medium, or they are indigenous, formed within the solar system. And probably you can link these organics to the life form that we are in today. So when people are talking of origin of life, they have to bank on some of the information from meteorites or asteroid body. Yeah? So you understand it's so important. Yeah, it is all linked up now. And what does the pre-solar grain or circumstellar grain give you? It talks about the nucleosynthesis that is happening in the stars. So from a material of a meteoroid, I will go into the star. I'll tell what is going into the stars. No telescope can give you this kind of information. When you do a spectroscopy, when you look through the telescope, you are looking at the photosphere. Yeah. So you're looking at something which is very it doesn't go beyond a few kilometers. Yeah. So, but when I talk about nucleosynthesis, we are going into the center of the star and looking at the fusion processes, or we are kind of giving a range of neutrons or what kind of reactions can go in stars. So from meteorite, you can do that kind of a study. Now, this I wanted to give you an overview how important meteorite or asteroid study are. This information of the classification of asteroids. So there is a classification of asteroid also. If you look at the x-axis, you see distance from the sun. So we are moving from 1 AU till 5-6 AU. This which encompasses something of asteroidal belt. So C is for carbonaceous chondrite, S is for stony, E is for astatite. So there is region of asteroids from where our samples are coming, yeah, from our meteoroids are coming. Or if we go and collect the sample, we can decide from here which kind of sample I want to do organic study. So I need to go to the carbonaceous meteorite. So which region I should go in. Okay, so there's a lot of information that is there in it. Now, was this region exactly where it was from the very start is a question, and people have looked into it. And there has been a severe discussion on this. Maybe if it's okay to tell me when I have to stop, otherwise I'll go on. So I'll just go on with the mission study and tell you how this mission study or meteoroids have contributed to understanding of solar system formation, or how asteroid region has been built up. Okay. So first mission that I started is not an asteroidal one, but it is a comet one. But let me go quickly through it because I worked on it. So it's a first mission that brought back the cometary sample in 2006. Yeah. And in this, we analyzed that's the aerogel component from which we removed the grains and analyzed in nanosims to look for pre-solar grains. So the idea before this of solar system formation was, the idea was to form the solar system formed from a general region of protoplanetary disk. Yeah. So the idea was that all important stuff, volatile stuff, has to be at 40 AU, yeah, because it's a region where you don't reach to a higher temperature and everything is unaltered. So the cometary region will be enriched with volatiles, pre-solar stuff and everything. Yeah. So, but when the sample from the comet came back and we analyzed, we really didn't get many pre-solar grains that we were expecting from it. There was not a lot of volatiles that we were expecting from it. Instead, what we found was it was very, very similar to the material that is formed very close to the sun that you see in meteoroids here in general from the asteroidal region. Now, this was like a question mark. Is this only a this is because of the characteristics of this particular comet, or it is really from all comets are built like this? That is the question until you get the material from second comet. But what came up is the model parameters changed of how solar system evolved. people talked about the turbulence and the X-wind, which said that the inner material, when the planets were not formed, before planet formation, the inner material that was being formed was being there was a wind which is called an X-wind, which takes the inner material far off to the outer region till 40 AU. So the dynamic system was again introduced and worked upon for the solar system formation. So that is the power of analysis of meteoroid and asteroid formation. It can change the model of solar system formation. Now, why you also have to understand there are so many exoplanets that are being seen today, and we are looking for habitable world basically. So you need to understand your solar system formation to understand a exoplanet or if is there a life there. Yeah? So this is like an analog sample. Solar system, anything that we are doing is analog sample for study of exoplanets too. So and this is also related. Yeah. Now, yeah. So I also wanted to talk about this is a cartoon diagram I made for another actually for missions work that I did on sample from Hayabusa 1. So this is it's a stony asteroid basically, and they brought by sample from this. We analyzed in PRL with nanosims. So we analyzed these samples, and these were like small grains. You see such small grains like 40 to 70 micron grains. We had 4 of them, which we analyzed in sample for, say, short-lived radionuclide aluminum magnesium, which we are not talking today. What I want you to understand is we did some calculation, and when we did some calculation, we could talk about the dichotomy which we see in solar system. So there are models that say that when the Jupiter started forming, the embryo of Jupiter was the first one to form. So this embryo, what it did, it really isolated the outer solar system material from the inner solar system material. Now, the inner solar system material was non-carbonaceous kind of, and the outer material was carbonaceous. So it is called dichotomy of solar system, isotopic dichotomy we talk about. And as I was saying earlier, there are inner material that are being thrown. So from this, also people have talked about in 2011 migration theory of solar system formation. So how everything is related is so beautiful that the Jupiter was migrating inwards initially. So the proto-Jupiter, not the Jupiter, it migrated inwards around 1.5 and then came back because the Saturn's pull was, the resonance was such that both of them, proto-Saturn and proto-Jupiter, came back to their original position that we see as of today. But during this time, the outer material, which was carbonaceous, and the inner material, which was non-carbonaceous, basically were thrown here and there. And that gave the asteroidal belt classification that we were seeing, which was typically carbonaceous, either a stony carbon, stony metal yahan hai, stony yahan hai. So that kind of a system before Jupiter, you see all amalgamation of all kinds of material. Yeah. So that is because of the migration of planets. It has been explained in this way. And we also see this from the Hayabusa sample that it belonged to a non-carbonaceous material asteroid and probably doesn't have a fusion of carbonaceous material in it. So we pinpointed where it could have formed the asteroid. Now for the second Hayabusa 2 mission, we again have samples in our lab to analyze. So we are analyzing this for pre-solar grains. We want to talk about organics and pre-solar grain here. So it's being analyzed, being analyzed. So this material is important like Binu, because these both are carbonaceous chondrites. So what we have done to analyze such carbonaceous material and to talk about how organics came into the system or how asteroid or comet, which one is more important in understanding the origin of life, something like that. So we started doing organic studies some 5 to 6 years back, and we started isolating our organics in lab and studying them with nanosims as well as spectroscopic experiments like Raman, FTR, Zanes, doing a scanning electron microscope, TEM. So we did a lot of work on this. This is what has been reported earlier from NASA, and they showed that there are organics which look like a globule. Organics, when I say organics, it just means a collection of carbon chains, aromatic or aliphatic kind of, with hydrogen, nitrogen, oxygen, sulfide, phosphorus kind of small elements into it. I think Bhandari ji also gave you a molecular structure crystallography. 100 hota hai. That is the composition of these macromolecular particles, which also has globules in this. So this was very exciting time when this was discovered, actually. So there are many studies to talk about how this organic can come into the system, whether it is from the Earth, or it's from the asteroid, or it is from the comet belt, or it is from the interstellar. It is an interstellar material. Yeah. So people have been trying to analyze these globules by nanosims and looking at carbon and nitrogen isotope to understand how they were forming. We have also analyzed Mukundpura, Murchison, Moraine, our lab, and have seen that they do have a huge anomaly that cannot be understood by terrestrial, anything physical or chemically you change the system cannot explain the anomaly that you're seeing in these. So we think it is not from obviously from terrestrial, it is extraterrestrial stuff. And the idea is to delineate if it is from ISM or from the nebula itself. Yeah? So yeah, I will. If I have time, I will go through this. Otherwise, I'll skip it. Do I have time?
Of course, you have time.
So if I have time, I'll just tell you one more thing. So these are the grains that we have isolated from meteorites. Yeah, pristine meteorites. So they're different. You have to understand that pristine means which is untouched kind of and more carbonaceous kind of material we have taken, and we have isolated these in our lab also. So these are pre-solar grains. So pre-solar grains can be like carbonaceous grain, nitrite grains, oxide grains, sulfide grains. So there could be many kind of grains which are pre-solar. From pre-solar or circumstellar disk, I mean, they are formed in the interstellar medium. They're not formed in solar nebula, not in our solar system. But we find it in meteorites. So if you find them in meteorites, mean that we are getting material from the other stars also, right? So people have analyzed the time scale kya hoga from chronology of short-lived nuclides. We can tell कि इसका cosmogenic nuclides करके बताया कि इसका time scale क्या है cosmos में घूमने का and to come into the solar system formation and stuff. Now, if you look at the right-hand side, you will see that yahan it is not very focused. Yeah, you have that feeling it's not focused, but it just says if you see the background, it is well focused. It just says that it has a layering, and when this layering was analyzed, it was seen that it is organic material. Organic means again what I said, yeah? Carbon chains. So it has an organic material over it. Now this is where the question comes. If a pre-solar grain, which is not from the solar system, has an organic layer in it, is it an interstellar medium material? Okay. So that's how the questions arise. Yeah. So this was again analyzed in electron microscope to understand formation scenario. Fortunately or unfortunately, this hasn't been delineated as such because every components that have been seen can be explained by some ion molecule interaction going in solar nebula very early in times, yeah, 4.5 billion years ago. Yeah, so there is some ion molecular interaction which can give you fractionation of deuterium, hydrogen, and formation of 15 nitrogen. So all the anomalies that you see can be explained by both as of now. So we are still working on it. So this is the ongoing kind of a work which I was talking about. And this is a very, very interesting work. I'll end with this actually. So a very interesting work. I hope you can get a gist of it. I know it's a bit involved, but let me try to still make my point that how we understand what was the size of the meteorite that I'm analyzing. From IR spectra, from composition, I can say that I have a carbonaceous chondrite and it is coming from a certain meteoroid region, or maybe from certain parameters, I can identify the meteoroid itself, asteroid itself, the parent body, right? But in general, it's difficult to understand कि कौन सा parent body है meteoroid का. तो to relate a meteoroid to an asteroid becomes difficult at times. But how did the body form? How big the body would have been? People have done different kind of work and try to understand it. There is also theoretical modeling. We, in turn, did this new work, very new work. This is for the first time and we have just put it for publication. So what we have done is, we have looked at the temperatures this organic from these material are coming. So you take out the organics, analyze them, you can deduce temperature from them. So we took two different analytical instruments and tried to reduce temperature and then compared them and did some modeling calculations to fit in the lines. So you will see there are, it's not very clear, but down there in the plot, you will see the lines which are theoretical modeling. And there are the spots. These are the analysis that we made. There are Rigu spots, which are not our Rigu spots, which are not our analysis, but there are 2 points just to understand. People have talked about how Rigu body is a rubble pie kind of a body, yeah, asteroid body. So we are trying to understand the body through meteoroids. So we put them there, and we put our points, and you see 2 dashed lines. There are 2 dashed lines which with our parameters or our calculation is a delineation between the duration of aqueous alteration. So if I put that parameter, I can tell what kind of a body it was. So anything which has a duration of alteration more than 1 million years, I say the body was a big, large body, more than 500 kilometers of 500 kilometers. There could be an impactor which would break it up, and then you will have a rubble pile kind of a scenario. But the duration where it is less is there are many small bodies with similar composition, more or less similar composition, and they can coagulate to make the rubble pile. So if you know, Rigu is coming under this kind of where they are small clone kind of a composition of the body and makes a rubble pile kind of an asteroid. So our parameters for these, so I can say these meteorites have a parent body which has similar kind of a structure as Rigu. Yeah. For these are different meteorites. Yeah. So I can name few meteorites like Cold Bokeville or Haripura, ACB. Now there are few which have very short alteration. Now this can be understood only from impact. So they don't define the body structure, but they say there was a huge fast impact between the 2 asteroids. Yeah, that is what we see in organics. So from organics, not only I talk about light, I can derive so much more about the asteroids and the meteorites. And with this, maybe I'll stop and let you all ask me questions, or you all are welcome to PRL visit lab, look at meteoroid collection that we have. Thank you.
Hello. Hello.
Yes.
Thank you so much, madam, for your talk. And it was really very exciting. In fact, there are a lot of things that I had personally have to ask you, because for me it was a complete education of what we learned in school, what we learned later, and what now we are going to learn. So I think your talk was excellent, and we will like to have question answers, but I guess we have other speakers to talk to. So we look forward to hearing from you further. And once again, I thank you for your time and effort. And also, we would like you to come sometime to Mumbai. I think you are aware that Mumbai Nehru Science Centre is very popular, and your talk the children would love to have it here, because the children come here even for today's program. I'm told that they had an essay competition and also a painting competition on the asteroid day. So, with these few words, I personally thank you very much, madam, and I look forward to you to be in Bombay and be a part of our programs. Thank you.
Sure. Thank you. Thank you all.
Okay. So now we have our own Mangesh Sutar to give a talk. But before he gives a talk, I want to tell you Mangesh Sutar is an MSc in physics. And I guess it is solid state physics?
Electronics.
Electronics. And he's fascinated with astronomy. And one interesting thing that I have to share with you, he conducts stargazing programs also. So, those of you who are interested in stargazing programs, you can contact Mangesh, because he conducts, I think, not in the monsoon. He conducts completely from November onwards all the way down to May. So he has been doing this work for many years, and with Amateur Astronomers Association, he has been a great help. I would emphasize the word great help. So, with these few words, I would like to ask our good friend Mangeshi Sutar to speak to us about his topic, which is a futuristic topic. And I think I would also request him, because our next speaker is a foreign speaker. So I would request him again to keep some time for the foreign speaker to speak. So his topic is space missions to asteroid. And again here, we would like to start this talk right away, and we want to keep up to the timing as much as possible.
Thank you, Bharat sir. Good afternoon to everyone. So myself, Mangesh Sutar from Amateur Astronomers Association, Bombay. So my today's talk is about space missions to asteroids, exploring the unknown. So today we have seen people talking about asteroids, meteorites, study and all that things. So getting those, one is thing that all these meteorites, whatever we can get them terrestrial and all that things, but there are missions also being carried out to collect these samples, or to study the asteroid and asteroid belts and all these foreign particles. So today we embark on journey through the cosmos, focusing on fascinating and dynamic field of asteroid exploration. So mostly the asteroids are often referred to as a building blocks of the inner of the solar system, which are the remnants from the formation of over 4.5 billion years ago. These rocky bodies, ranging in size from tiny pebbles to hundreds of kilometers in diameter, hold invaluable clues about the early solar system and the process that led to the formation of the planets. Our understanding of asteroids has been dramatically enhanced by the space mission dedicated to this study. So my talk is more towards the study of asteroids through the space missions. So we are going to see what all the space missions have been carried out by different agencies across the world. So first, let's understand why do we need to study asteroids? Okay. So agenda is asteroid exploration, importance of studying asteroids, then historical missions, then missions from 2000 to 2020, then what are the future missions like Lucy, Psyche, and then what are the scientific and technological advancement we are going to achieve through this asteroid exploration, and what are the future prospects of the asteroid exploration. And then we end up with the question answers and thanks. Okay, so let's move ahead as we have shortage of time. So what is asteroid exploration? Okay, as I said, These are just the tiny pebbles to hundreds of kilometer diameters, but they still hold a valuable clues about the early solar system. And that process led to the formation of the planets. Our understanding of asteroid has been dramatically enhanced by the space mission dedicated to their study. These missions have ventured millions of kilometers from Earth, utilizing cutting-edge technologies to observe land and even written samples, and then ancient celestial obstacles. Each mission contributes to our knowledge in a unique way, revealing the composition, structure, and the history of asteroid and offering insights into the potential resources for the future space exploration. So let's start. So what is first is the importance of studying the asteroids. So studying of asteroids was understanding of the early solar system from the primordial remnants formation process, again the composition and structure from a diverse materials, mineralogy and chemistry, understanding the origin of life through the organic compounds, water delivery. Then as these objects move around the Earth. So we see near Earth objects, news or impact mitigation. Then resource utilization, that is mining potential, inside resource utilization, technological advancement, innovations and spin-off technologies. And then finally, the scientific curiosity and inspiration. So the expanding our knowledge and inspiring the future generation. As we say, we are the explorers who are going to not only live on the Earth, but as you see, a lot of space missions are going there, going to the moon, going to the Mars and beyond. So this mini space mission helps to study and understand a lot of technological advancement as well as resource utilization as well as planetary defense system. Okay. So let's see first what all are we have the historical missions. So first mission was Galileo in 1991. Primarily this mission was launched by NASA for study of Jupiter and Moon. On this journey, there were 2 asteroid flybys. It was performed the first asteroid flyby by doing close 951 Gaspra in 1991 and 243 IDA in 1993. So what was the key discoveries? Provided the first close-up images of asteroids, revealing their irregular shapes and surface features. IDA was discovered to have even a small moon called Dactyl, making it as a first asteroid known to have a satellite. So you can see on the right side the trajectory, how it started from the Earth and then it moving towards the thing. Then first it has done the flyby at the Gaspra and then 243 IDA. Okay. Next is the Near Shoemaker, that is in 1996. This mission was basically a near-Earth asteroid rendezvous mission, later named as Near Shoemaker. Flyby was at 253 Maltida. Okay, the flyby produces almost 500 images covering 60% of Malta's surface, as well as the gravitational data, allowing calculation of Malta's dimension and mass. The target was actually the 433 Eros, a near-Earth asteroid. It became the first spacecraft to orbit an asteroid and eventually land on the Eros in 2001. It also sent back detailed images and data on the Eros and surface composition of the structure. So you can see on the right side the entire journey of the Eros, right from the Earth it lands and then how it landed on the Eros. You can see the structure also of the Eros, 433 Eros, and the small asteroid Maltida also. Next is the Deep Space One, that was in 1998. Again, this mission was carried out by NASA. This was basically an technological demonstration mission, which flew by an asteroid and a comet. So asteroid encounter was planned on 9969 Braille in 1999 and to include an encounter with comet in 19P/Borale in 2001. You can see the again on the right side the trajectory direction, how it is how it has encountered the 9969 and then it went to comet 9P Borale. So what was the technological innovation tested in this mission? One was the ion propulsion, which was crucial for the later missions, example Dawn. So most of these future space missions what are right now carried out to the asteroids are mostly ion propulsions. And also the technology demonstration was autonomous navigation. I think almost now all the space missions requires autonomous navigations because of the distance of communication required, where it reduces the need of extensive ground-based support. So that was the technological demonstration carried out under this mission, and that is what NASA has achieved and which are being used in the future missions also. So let's see now, after the historical missions, the missions in the 20th century, that is from 2000 to 2020. First was Hayabusa in 2003. This was launched by JAXA, that is Japan Aerospace Exploration Agency. This was targeted for a rubble pile asteroid 25143 Itokawa in September 2005. The key achievement of this mission was study the asteroid's space, spin, topography, color, and composition and density. The first mission, this was actually the first mission to return the samples from an asteroid. Though it faced numerous challenges, including communication failure, fuel leak, and also, but ultimately succeeded in bringing packed particles from Itokawa to Earth in 2010. The spacecraft also carried a detachable mini lander Minerva, but however, it was failed to reach the surface. However, all the learnings from Hayabusa 2 was to future missions. So let's see. The next mission was Dawn, which we talked earlier, which was the predecessor of Deep Space One. So Dawn mission was planned in 2007. It again NASA's mission aiming studying two largest bodies in asteroid belt, that is Vesta and Ceres. Dawn orbited Vesta from 2011 to 2012, providing the detailed map and data on its surface and geological history. Then it traveled to the Ceres, arriving at 2015, where it discovered bright spots like salt deposits and evidence of water ice. The spacecraft operated well beyond its planned mission duration, providing a wealth of scientific data. So you can see on the right side, the Vesta, the round circular side. Again, you can see the Ceres also. Ceres is the biggest, I would say, the object in the asteroid belt. And you can see the bright spots, which actually looks like a salt deposits or even the evidence of water ice on the surface of the Ceres. This is very interesting. This was in talk for last couple of years. And even today, people are talking about the Bennu as an asteroid. This again mission was carried out by NASA Origin Spectral Interpretation Resource Identification and Security Regolith Explorer, that is OSIRIS-REx. Its target was 101955 Bennu as an asteroid. Successfully mapped the Bennu and collected samples from its surface in 2020, which returned to the Earth in 2023. Its primarily aim was to study the Bennu's composition and provide insight into the early solar system and sources of organic compounds. So whatever the samples has been collected from the Bennu, they have been given it to respective agencies for further studies, and we are just awaiting the further studies. So you can see on the right side, the touchdown sequence of the OSIRIS spacecraft, and then you see the Bennu asteroid and the return sample which landed on the Utawa Desert in 2023. This is the entire, I would say, infographics of the mission, where it shows the size of the Bennu. Bennu is much bigger than what you comparison to the Eiffel Tower and the OSIRIS mission spacecraft. How does it landed and all the things. There are beautiful videos also available online. You can study. It is really a technological deployment kind of mission where actually they picked up the samples from the asteroid and got it back safely to the Earth. This is the second mission from JAXA. Again, that's the continuation of Hayabusa 1. This is Hayabusa 2 in 2014. Again, they targeted the rebel pile structure, that is a carbon-rich material and hydrated mineral at Ragu, that is in 2018 and 19. You can see the structure, the 360-degree view of the Ragu asteroid. The key achievement of this mission was 2 successful samples, collection maneuvers and return samples to Earth in 2020. Successfully deployed the Mascot on Minerva 2 rovers to explore the data from the surface. The mission provided valuable data on Ragu surface and composition. Next is the DART, that is a double asteroid redirection test. So this mission again done by the NASA. This was actually targeted the binary asteroid system, Didymos and Diphromos. Here it was actually a demonstration of kinetic impactor techniques as a viable method for asteroid deflection. So you can see on the right side, the spacecraft was actually impacting the asteroid, and it is trying to alter its orbit by some distance. So you can see there are a couple of images where it has, as it is approaches, the image is getting bigger and bigger, and that's what is to target and see how does, when it impacts the any particular asteroid, whether the orbit is getting changed or deflected. That was the test of this mission. So there are now only a couple of missions, future missions and prospects. One is the LUSU mission that is in 2021, which was launched. So this is actually to the study of 7 celestial bodies intercepted between the Jupiter and the Trojan asteroids. So main belt, which is going to get encountered. So this mission is just started. It is on its target. So by 2025, LUSU will first go to the main belt of asteroid, and 55246 Donald Johnson it will target, and then it will move ahead to the Trojan asteroid encounters in 2027, 2028, and by 2023 it will complete its mission. So it's completely almost a 12-year mission. So we will await the results of this mission further on. Okay, this is again the infographic of how the mission and the spacecraft and how it is going to fly across the Trojan asteroids. This is the last recent mission, I would say Psyche mission in 2022. Again here it was the mission to explore a rich, metal-rich asteroid, 16 Psyche. It will be orbit from August 2029 to 2031. To study the composition and characteristics of Psyche, believed to be the exposed core of the protoplanet. Its main primarily also geological features of the Psyche, including its surface composition, topography, and magnetic field. Psyche uses solar-powered Hall effect thrusters for propulsion and orbital maneuvering. This is the first mission to use laser optical communication beyond the Earth-Moon system. Okay, these are the way how it is going to orbit the cycle. This is as of now proposed. However, this is going to happen in the near future. Okay, so we are at the end of the presentation almost. So we'll just quickly see, run through the slides, scientific and technological advancement for the space missions to asteroids. One is the understanding the asteroid composition and structure, what we are already doing, insights to the early Orlo systems. Then we see planetary defenses, then geological and geophysical data, then spacecraft propulsions and navigations, what we have seen, then sample collections and returns, and then also rovers and landers which were sent by the various space missions. Then again using the advanced imaging for spectroscopy, and then communication and data transmission. So these are all technological, scientific and technological advancement we have done. Let's see what are the spin-off benefits. Earth applications are like mining technology, material science, then space exploration like mission planning and habitat designs. So all these technical and technological advances from space missions to asteroid has far-reaching implications and enhancing our understanding of cosmos, improving our ability to protect our planet, and driving innovation in space exploration and beyond. So with that, the future prospect of asteroid exploration, what we have already seen. So I'll just quickly go to the last, that is a case study which I have put, just asteroid 99942, that is Aphosis, which has been talked by a lot of earlier speakers. So there is a serious threat from this asteroid. However, closely studying, we say that we are not in, as of now, current situation that close by 2099. But however, there is a small chance of impact in 2068. Okay. However, still the technology, scientific and technology advancement can help us to protect from this dangerous asteroid. With that, I think I thank everyone for allowing me to talk and listening to me. Okay, if you have any questions and answers, we can discuss or we can conclude the lecture over here. Thank you very much.
Thank you. Thank you, Mangesh. I'm awaiting for Professor Hasna, whether she has joined us. Professor Hasna. So if she is not arrived, can we see a short video clip before the program. The video clip is 7 minutes, if I'm not mistaken. 12 minutes. So we wait for Aster Changdao. So if she's around, we can wait for her and she can start the program. Is she around? No, she's from Morocco. And the video down. Yeah, here I would like to make a small comment. Like you always see, we are so far talking about the events. Now, this is an event right in Bombay, showing you how we can do this astronomy also from Mumbai and probably from Dombivli also. So, so can see. So you can see this low budget solutions. According to Rajiv, Ravi, he has been doing this work for last so many years. And from 2017 onwards, we are on with him. So now we will see a 12-minute clip of how he photographs these meteors which come. He stays fairly close to the coast, that is Arabian Sea. So from there, what he can see, you can watch it here. This is the circuit which he has put up to look for the meteor. All the details are there, whatever he is showing. So you can, during the tea break also, you can talk to him.
That is PoE, right? PoE, power on Ethernet. Oh, once this road starts, then there will be a lot of light. Once this road starts, then you will have a lot of light over there. Started, huh? You need to move the setup then. That's the irony of astronomy. Yeah. Or you can use that also. Use this. Use the mic. You can talk. You can speak whatever you want to say or explain. So it started capturing, huh? It started capturing.
I had a question here. Will you try actively cancelling two frames and maybe doing that multiple frames so as to remove the noise and pick the the object? Have you tried doing that with AI or ML? Instead of eyeballing it, like if you have like first say one frame where you got lots of lights on the street and everything, right? You got a second frame, then you take this 2 or 3 or maybe multiple frames, cancel them out with each other, like. And then what you got left is the boogie. So maybe that could help out.
That's a very time-consuming process. And
Yeah,
what we're talking about is 900 videos.
Hence comes AI or ML in the picture. If you have tried artificial intelligence or machine learning programs to do this.
To train that.
Yeah.
That to find that anomaly. What you are saying, he need to train that, where he is using the reverse technique to do.
Yeah, he's doing eyeballing, but then have you tried using computers to do that sort of thing?
No.
Calculation thing. Okay. Thanks.
But I run two cameras. So whatever time I'm spending on one set of captures, I'm doing double because I have to do the second set. So
right,
it goes on till 4 o'clock in the afternoon.
That's a massive
Just
data,
with
yeah.
two cameras. Now imagine like 4 cameras.
Yeah, yeah.
It would be like.
So when you say you have a two cameras, are they scanning the same part of the sky?
Northwest,
Or
southwest.
maybe covering two
One northwest, one southwest with a common.
Pano kind.
Yeah.
Or maybe you're with multiple cameras, you're trying to capture more part of the sky.
Yeah, but I only have.
So I was saying, when you're using multiple cameras, these cameras are actually used, multiple cameras are used to capture more amount of the sky, not of the same part of the sky, right?
Correct.
Okay. Why I was question is that, like, for example, if I have set up a particular part of the area of the sky using two cameras from two different angles, and then because one image is capturing, then it is second image, second, third. So in that switch of two images, there is a chance that your blink of the thing could missed out.
No.
But you are capturing the videos, that's why.
Yeah, it's videos. So I'm capturing it at least
Continuous.
10 FPS. So
10
nothing
FPS.
can happen in 1/10 of a second.
Yeah.
I mean, it is possible. Some
It's possible,
cometary
yeah, but still.
material, but it's highly unlikely.
Okay. खत्म हो गया क्या? That video ended?
Yeah.
It's going on, right? Okay. Second video started over.
So good morning, everyone. Can you hear me?
I'm Bharat Adur.
Yeah, so can you hear me?
We are here to welcome you.
Thank you. So I was waiting for the link.
We are welcoming you with your own meteorite.
Yeah. So
Yeah, it's a chondrite. My name is Bharat Adur.
okay, nice to meet you.
Hello, madam. We are awaiting for you to talk. We are waiting for you. So can we start?
Yes, of course.
Yeah, thank you so much, ma'am.
Thank you. So
a little introduction I can give for you.
Okay, please.
Yeah. We have Professor Hasna Shanaidun, and she is the coordinator and center of research and also the president of Atrik Foundation. Am I right, madam? It's Atrik or Atrik?
It's Atarik. I will talk a
Okay.
little bit about Atarik later. Thank
My
you.
contact with you, ma'am, goes back to 2015 when you welcomed our student for the Meteoritical Society of India. And we are very thankful to you for your help in getting our student the opportunity to speak to the Meteoritic Society. So, welcome once again. And in Marathi and Hindi, we say welcome is in Marathi, it is Zaruriya. And we will look forward for your talk. Before that, I would also like to introduce today's speaker is one of the finest speaker that we have to hear about. And I have heard her in Meteoritical Society meeting. And the best part is she's an awardee of the Meteoritical Society award. So congratulations, madam, to your award. We are following you very ritualistically. And we are so fascinated with your namaskar. So we are also looking forward to your talk on the Northwest African. In fact, why I am referring to your meteorite, we have done some work on the meteorites which have come from Northwest Africa. Every year we have been doing this Asteroid Day meeting in India, and this time it will be in Science Museum. So it's your place and your time. So she has done a lot of work. Her publication is in several areas. So of meteorites, and also I must tell you, she has single-handedly created a meteor museum, which is we are aware of, madam, this kind of a museum, which I think one must look forward to. So, with these few words, madam, we are eager to hear you, and we have a big audience waiting for you. It's a national program, and we welcome you for this program. Thank you, and we look forward to listening to you, madam.
Okay, thank you so much for your introduction, and many thanks for the invitation. And I'm happy to be with you today and to contribute to this Asteroid Day with you. So if you allow me, I will share my screen. Yes.
We cannot hear you, madam. Can you?
Yeah. Can you hear me? Is it okay?
Yeah.
Okay. So thank you so much. I will try to give a lecture about meteorites from Northwest Africa and Morocco, especially as heritage, but also as science and also passion. So before talking about meteorites, I will just talk a little bit about what is the interest, why is it so important, why is it so important to have meteorites, why is it so important to work on meteorites, and why meteorites coming from our countries in Northwest Africa are so important. So, of course, there are different space missions with telescopes, with satellites, with rovers, and a few of those space missions are with sample returns, such as Apollo, Stardust, Hayabusa, and now you have all those results that we begin having from Bennu asteroid, and it's absolutely exceptional, and with a huge opening of a window on the knowledge of the solar system history and formation. But those space missions are extremely important, but we have also all meteorites coming to Earth. It's free. It's coming naturally to Earth, and it gives a lot of samples to study from the solar system. So just a brief introduction of one of the most important contributions of meteorites of the knowledge is about the solar system constitution, chemical constitution, and what meteorites gave as information about this. So, of course, if we see where is the sun, so where is the sun in this diagram? Our sun is a star that is young and small. So it's in the main sequence. So it should have only hydrogen and helium, but our solar system contains hydrogen and helium, but also among 2% of all the others chemical elements that should normally came from a bigger star, a much bigger star, and even for the higher elements, it should come from supernova explosion. So that means that those 2% of those elements are not coming from our solar system, because the sun cannot produce those elements. So this is what we know from the astrochemistry and from so what we know about astronomy. And but what is the input of meteorites here? So again, here you have the atomic number of the elements and their relative abundance, and of course, so hydrogen and helium are the most important elements in the universe, actually, because they are created in the primordial nucleosynthesis. And to have even carbon or nitrogen or oxygen, you should arrive to red giants, etc. And for having the higher elements, you should have supernova. Here, it's how those elements are created. So, okay, what is the input of meteorites? So about the solar system age, we know that the solar system age is about 4.55 billion years, and it was calculated by the isochron of Patterson isochron, and it didn't change since 1954, and of course it was calculated on meteorites, and even now it's more precise, but this age haven't been changed since this time. Okay, let's move now to those elements that we have in the solar system that should come from an older and bigger star. One extraordinary work that have been published on 2020 about Murchison meteorite, that is a carbonaceous chondrite, show that there was some dust and some elements that are much older than the 4.6 billion years. And so they found dust and grains that can arrive to 7.5 billion years. Those grains are found in this meteorite, and it's a proof that it's coming from an older star that's the Sun. If we go to the water origin on Earth, you know that by analyzing the carbonaceous chondrite especially, and other meteorite, but in the carbonaceous chondrite, when we look at the oxygen isotopes and the deuterium, so it's very close to what we have in is very close to what we have in some carbonaceous chondrites, and so it's one proof of the origin of water on Earth, that at least for a part of this water coming from out of the Earth. So it's coming from comets. So this is one comet that was very close to Earth on 2024. And for example, one of those meteorite that give this kind of information is carbonaceous chondrite, such Cerda meteorite that was a fall that occurred in Morocco in August 2020. So there are also a lot of research going on the different meteorites coming from Morocco, for example, Ticint, and looking for the organic matter, and of course with the background idea of looking for the source of life out of the Earth, and the source of life in our very close planet, that is Mars. So this was a work that was published on 2014 about Ticint, about the organic carbon, and more recently on January 2023 we had one paper that has published in Science about carbonaceous, about the organic matter in Ticint meteorites, that is the most rich and diverse in comparing to any other known rock on Earth or in the solar system, meteorites. And of course, this image that is very well known of one Martian meteorite collected in the Antarctica. It's ALH 84001 that was this was supposed to be a bacteria, but it turned out that it was a contamination, Earth contamination. But it's just to talk about this new and very important and interesting development of meteoritics, that is exobiology. One important thing also that was, and we are on the Asteroid Day, so it's important to talk about this. It's how impacts was fundamental for the development of the solar system. We have, for example, the formation of the moon. That was a result of a very big impact of planets, Mars-sized planets, and in many rocky bodies of the solar system, we have lots of impacts, and it was been shown that the solar system experienced a very important bombardment called the late heavy bombardment, and we can see this on meteorites. And of course, just talking about the Chicxulub crater and extinctions of dinosaurs, but also 75% of the life on Earth that was created by the fall of an asteroid about 10 kilometer size in the Chicxulub area in Mexico. So so this is a work that have been published by RAMP in 2015, trying to find the correlation between the basalt flow, max extinctions, and impacts. So there are some very nice correlations between the mass extinctions and the important impact craters on Earth. So showing that the impacts and played a role in the extinctions masses on Earth. So just I will skip this because I think that all of you know, just to talk about asteroids that are main asteroids are in the main asteroid belt between Mars and Jupiter, and so the major number of meteorites are coming from the asteroid belt, and some of them, a few of them, are coming from the surface of Mars. A few of them are coming from the surface of the moon, and a few of them are coming from comets. And depending of their origin, we have primary meteorites, primitive chondrites, and more differentiated meteorites such as iron, or pallasite, mesosiderite, and lunar, Martian, and echondrites such as the ones coming from Vesta. Why I'm talking about how to recognize them, because when you go to the field and you're looking for meteorites, you have to train your eyes on how to recognize. And of course, when you have a fresh fall, you have a nice fusion crust that is black, etc. But so those are fresh falls. This is Ben Guerrier and this is Ticint. But when the meteorites is on Earth for a long time, this fusion crust may disappear completely, and so it's became mostly brown. So you have to have other ways to recognize. Of course, you have also the fact that there are iron, and so it attracts metal. But some meteorites are not containing a lot of metal, but even there is a small magnetism. Most meteorites have chondrules that are formed in the early solar system. And of course, this is the first way to recognize a meteorite. But of course, and you know that after that you have to go to the lab and do a lot of analysis And one of the most important analyses are the oxygen isotopes with the different kind of different families, meteorite families with different signatures. So each family have its own signature, except for the moon and the enstatite, chondrites, and albright that are on the terrestrial fractionation line. Make this oxygen isotopes not a good tool to recognize those kind of meteorites. And so now moving to where they are collected. Of course, they are collected on the deserts. So the most important place on the world on desert collection is Antarctica. Then it's the cold desert, but we have also the hot desert, and such as the one in Northwest Africa, and such as the one in Morocco, Algeria, Libya, Tunisia, Mauritania, etc. And so one of the most important place in the world for meteorite collection is Morocco, because of the big deserts, because of the fact that this desert is inhabited. There are lots of nomads living there, crossing the desert. It's a safe place, so you can move without some big problems. And we have a very big and good community of hunters that now are well trained to find, to recognize extraterrestrial rocks. So it's what we are saying here. We have, so Morocco is located in the western parts of the Northwest Africa, and all this area is desertic. So those are the falls. So we also have a lot of falls in Morocco. I will talk about this after. Today we are we arrived to I think more than 16,000 of West Africa meteorites. It's a huge number, and we have in Morocco 24 falls recognized, official. This is a very important source of research for the whole community of meteorites, meteoritics people in all over the world. And now we also have one impact structure. So just to remind how we work on when we find a meteorite, it's internationally. So if you have a rock, you have to analyze the rock, to classify it, to put reference mass in one lab that should be recognized by the Meteoritical Society and the Nomenclature Committee of the Meteoritical Society. Then you should submit your classification of the meteorites, and then when it's accepted by the Nomenclature Committee, it's published in the Meteoritical Bulletin. And of course, you know that now for a few years we have a wonderful database with all information, and you can search with different tools with falls, finds by countries, etc. And why I'm talking about this? Because it's the hard work that we had in Morocco for 24 years now of documentation of all meteorites that fell in the Moroccan territory, but also many finds. So this story in Morocco, as I said, began from 2000, and it's wonderful story with a lot of passion and a lot of field work, lab work, formation of students, PhD students, etc. So here you have some photos of field missions, and you see how. So for those falls, it's in the desert, and you see people that are there. It's mostly men's, etc. So what was the strategy that we implemented in Morocco since 2000? This strategy was based on three axes. The fundamental one is scientific research. So the scientific research was about all publications or classifications, all PhD students. Now we have 7 PhD students that defended their thesis on meteoritics and impact craters. And there are many others that are still preparing their thesis, a lot of publications. And the second axis is the curricula. So one course of cosmochemistry was introduced in the curricula of all students in the nationally in Morocco, for all students preparing a bachelor on earth science. It's something that was new, and it makes all geologists aware about cosmochemistry and aware about meteorites, especially that there are so many in our country. And the third axis, and it was also very important, is communication. And in communication, there are two different communication. It's the communication with TV, media, radio, social media, etc. But also the scientific communication, as you mentioned in the beginning. So we welcomed the 77th Meteoritical Society meeting on 2014 in Casablanca, and it was for the first time in Morocco, for the first time in an Arab and Muslim country. And we organized also different other desert meteorite workshop, impact crater workshop. So, and those are also communication and allowing people coming to Morocco, people that are working in all over the world in all labs on meteorites coming from Morocco. So those people are coming to exchange with Moroccan students and Moroccan researchers. And in the communication also, I will mention that we worked also on the regulation. So I published a paper a few months ago about the new regulation on meteorites in Morocco. And this regulation was is important for us. And we worked hard to have a clever regulation that is a win-win, because when you go to Oman, it's totally forbidden to export any meteorite. But there are many meteorites coming from Oman or from Algeria that are illegally exported. We didn't want to have this model. We tried to work on a model that would be more convenient for everyone and also for the country. So our regulation now allow people to collect officially meteorites by asking for permit, and to export legally, totally legally, meteorites by a process and a permit also from the Moroccan Geological Survey. So talking about some very important faults in Morocco, I will talk a little bit about Ticint. Ticint is the 5th Martian meteorite a witnessed fall on Earth. It was collected very quickly after the fall and analyzed very quickly. So it's a wonderful meteorite because it's giving a lot of information about Mars. So we had the privilege to have a paper published in Science in 2012. In this paper, we were talking about discovering that when T-SINT was launched from Mars, the surface of Mars was weight. We calculated the ejection age that was about 1 million years. And we also proved in this paper that actually all meteorites that was recognized as Martian meteorites are really Martian meteorites because we could analyze the gas that is trapped in the glass. So T-SINT has a wonderful glass. So this glass trapped in the gases from the Martian atmosphere, and so we could analyze this gas and prove that it's really coming from Mars. So of course, T-SINT it fell on 2011. And it's still giving a lot of inputs on meteoritics. There are some examples of the papers that was published on T-SINT, and we still have papers coming because it's unique material of work and a unique material to have information about the Mars. I will move to another very important fall in Morocco, talking about Tigert. Tigert is a meteorite. So it fell on July 2014, the same year of the METSOC meeting, on the summer time. It was very special history because it fell during the Ramadan time. It fell during summertime, and it was the Ramadan month. And so people were praying outside because it was very, very hot, and all people praying have seen the meteors. It was so close to one village that is called from Hsen, and the first pieces was found very quickly the day after. So this meteorite is amazing because it's a meteorite, it's a fresh fall, and I had one PhD student that he defended his thesis last year, and we have 3 wonderful papers about Tigert, including this one on talking about the fluid-assisted metasomatic processes to form some iron grains. So this is about Tigert. In this table, actually, we have all meteorite that fell in Morocco. And so, as I said, now we have 24 fresh falls. So our lab, I began working on meteorites on falls since Benger. So all those falls have correct field mission work, correct description, and the classification that we were involved in, of course, with the contribution and cooperation with different labs in the world, in Europe, in US, etc., especially for the analysis, because we don't have facilities in Morocco. So I have to move to different countries to do some electron microprobe analysis, etc. But we are very, very proud to have all those meteorites that have not an NWA name, but a name with a place name and a Moroccan identity because we were not happy with the NWA nomenclature that is not that doesn't give the right place to those meteorites. Now I will talk a little bit about how we moved from how we are building different other things based on the science that we are working, that we are creating on meteorites and meteoritics and impact craters in Morocco. So, as you mentioned in your introduction, so I created on 2019 the At-Tariq Foundation. So At-Tariq actually in Arabic is the name of one surah of the Holy Quran talking about a shooting star. But in the same time, it's an acronym of All Together Task Force for Advancing Research, Innovation, and Knowledge. And this NGO has 4 important objectives. Of course, the first one is promoting meteoritics and planetary science in Morocco, research. The second one is valorizing our geoheritage. We have a huge, important geoheritage in Morocco, and it's important to show this heritage and to valorize it. The third objective of At-Tariq is disseminating science. We have one wonderful museum exhibit now, including meteorites and fossils, etc. And the third and the fourth objectives is developing territories by geotourism and astrotourism. And we have different experiences and different activities in schools, in cities, in the countryside, etc. So some of the works that we are doing is, for example, celebrating, here we were celebrating the 12th anniversary of Tamdacht fall. Tamdacht is the biggest fall that occurred in Morocco on 2008. It's an ordinary chondrite, but the biggest piece was about 82 kilograms. And we estimate the total mass of the pieces to more than 500 kilograms. And the strong field was about 50 kilometers. This meteorite is nice. It's so we use this anniversary to go to schools in the area and to give workshops and to discuss with students and explain them what is a meteorite, etc. Here with At-Tariq Foundation, we are, as I said, we are trying to develop the countries by developing geotourism. Here it's in the south of Morocco, so we can propose to people to take them to different regions. All regions in Morocco has a very rich diversity on geology and can be used as a good tool to develop the tourism. This is another activity in the southern part of Morocco, in Dakhla, again with students explaining what is a meteorite, and so we created also those flyers and different tools to make the public touching a meteorite, living something that they cannot live in other place. A few words about this museum exhibit that we have. It's very special because it's welcomed in a commercial mall. We would like to have a permanent museum but it's not yet. We don't find yet someone to have this museum. So with Atariq, we could construct one exhibit museum that was for first edition in a commercial mall during 1 year. Then we moved to another mall with a bigger place. And this exhibit is welcoming students, children, the public. We have the meteorites, we have fossils, we have minerals. And also, so this was for the first edition. I was encouraged to write a storybook about Standard this fall. That is the biggest. This storybook is in French and also translated in English. So this is the second edition of the exhibit museum. It's in, as I said, in the second mall. And so you have as you say, we have the model of the solar system. We have many artistic views with different sceneries, and also what we have here in this exhibit is planetarium. So we have a planetarium, and we welcome people, and we can project some movies, some shows about the solar system, but also we prepared a show for the planetarium from the storybook of Tamdart. So just to summarize, sorry, it's in French, but so just to summarize, meteorites from Morocco, we have so many meteorites. It's a very important heritage. It's a heritage that is open to the whole world, because there is no single lab in the world working on meteorite that doesn't have a meteorite, NWA meteorites, at least 1, 2. So it's a material that is open to all labs, to all researchers. It contributes to more than half of the publications of meteoritics in the world. We still have, so one of the work that was conducted with one of my PhD students was the calculation of the density of meteorites in the Sahara, and we still have a lot of meteorites to be collected. It can be also a good support of disseminating of science, and it's what we are doing now. It has a huge heritage importance, and we hope that we will be able to continue developing meteoritics and planetary science in Morocco, and having next generation that will be employed in the universities or research centers to develop more those research and meteoritics in Morocco and abroad. Thank you so much for your generous listening. If you have questions, I would be more than happy to answer.
Thank you, Hasna. It was a really nice talk. We really can't emphasize the need for young people to understand this. What you're doing here is really wonderful. Any questions, anyone? Maybe the online viewers or anybody here? Hey, I guess I'll thank Hasna again, really. Thank you so much for coming in. Sorry for the blooper earlier. We couldn't send you the email and all, but thanks a lot.
Thank you.
I'm sorry, there's a question here. Can we just please take it, Hasna?
Okay, for the just a moment, I'm trying to.
Yeah.
Okay, for any fresh meteor capture effort and preparing, which technique has?
Okay, the question is for any fresh meteor capture effort and pinpointing, which
Uh,
technique has proven more useful? Better survey camera system scanning the sky or reports from general public about any fireball etc.
Thank you so much for this question. I didn't talk about our. So we have camera network. This camera network is called MOFID, Moroccan Observatory for Fireball Detections. It's a part of the global fireball network that is built by the Australian colleagues in Perth. It's a huge project, international project, and we are part of this project. So we have cameras that are implemented in different places in Morocco. Those cameras are scanning the sky, of course, during nighttime. And so we should have more than what we have actually now, because the number is not enough. It should cover all the country, because if you have a meteor detection, if you can have 3 detections, you can do the calculation of the orbit, and having the origin, you can calculate the origin, where is it from, and you can also calculate, predict the area, the fall area. And so this camera network is really performant, and we could have one detection. So we could have many detections, but one detection ended to finding the meteorites. And we will be talking about this meteorites and this fireball detection during the next Meteoritical Society meeting that will be held in Brussels. So the cameras detection, at least it's what we have experienced in Morocco, it can be very helpful. I should mention that it's not very easy, because it's a lot of technical issues. As you have cameras in different parts of the country, it's very difficult to maintain to maintain the electric power, to maintain the connection, internet connection, etc. So there are different issues and concerns, but the camera networks is definitely something that can work very well if you have the ability to have such a network.
Thank you, Asna. Okay, we can move on to the next speaker. Yeah, okay. Okay, thanks everyone. Thank you, Asna. Can we move to Mahesh Patil for your talk? Yep. You on the mic? Oh, okay.
Thank you.
Can we start? Okay.
So, good evening. I'm Mahesh Patil. I'll be presenting on Asian tektites. But before moving to Asian tektites and the unique signature of grazing impact, the process in which they form, I'm not too sure about the group people who are on the Zoom. So I'll just start with basic because I was told that there will be some students also. So our first introduction to night sky is obviously moon. That's where our most of the curiosity starts about night sky. As we grow young, it's not getting transited. Okay. As we grow, our fantasies around this body start increasing more and more. But as we realize, as we go too closer, I'm talking about moon, we start realizing it's a scary thing. And then most of us keep wondering what caused this. So obviously, wherever there is a damage, you can expect our close relatives to play some role in this. So in our context, it's asteroids and comets who are our close relatives who are responsible for most of the scars that we see in the moon. So we are no different. Even we are same. Now we'll talk more about, we'll just highlight more about cometary bodies because comets are little different. I think most of the earlier speakers have already spoken about it. Just to cover up few points, there are long period comets, the comets which have orbital period of more than 200 years, which comes mainly from Kuiper Belt or Oort cloud. And then there are short period comets who have life of less than 200 years, who are revolving within Jupiter and Sun or within the terrestrial planet zone. These comets tend to disintegrate. And one of the thing we in the morning we have spoken about Tunguska event and various other meteor events. It's something which most of us must have seen our during our lifetime. Is 1994 Schumacher-Levy 9 event, wherein a fragmented comet or disintegrated comet Schumacher impacted Jupiter, forming 21 impact sites on the Jupiter. They are visible and they were captured by most of the observatories. Now imagine a case, what if Earth come across this or any planet? When we talk about impact, generally the talks are that there is one impact site, one crater. No, that is not the case. Impact can be really, really devastating and one body can literally wipe out. So if event like Schumacher-Levy 9 happens to Earth, yeah, it's a disaster for us. So my study will involve a pattern which is similar to this. That's the reason I thought I'll highlight this particular aspect. I'll most of the scientists have covered, so I'll not talk about this. So in the recent past, we have come across Tunguska event. That's a reason why we are remembering this today. And then the 2013 Chernobylskaya event, if you can please play the video. It is just for those people who are not familiar with this subject. It is just for understanding. So a small body enters into Earth's atmosphere, it starts burning, it becomes very bright. And that's a okay, fair. So fair. If you can go back to presentation. So the small event of airburst costed nearly more than 1,000 people were injured. It was a small bolide. So Earth has been visited by these celestial visitors on a very very regular basis. Dr. Bhandari highlighted that at every 100-200 years we have Tunguska-like events. You want to play? It's okay. Go back to presentation. Yeah. Okay. So, if we look at the available records, we have already discussed there are nearly 200 craters. Now, the question is how craters are identified. So, people have talked about circular depression that are generally known as impact craters, high pressure minerals, shattered cones. And one of the ways to identify impacts is tektites. So, tektites is a very unique thing. It is not a part of meteorite, but it is an impact melt. So when a celestial body impacts Earth, the the ground melts, and this melted material is flushed back into Earth's atmosphere. And while coming down, it acquires aerodynamic shape. So Dr. Adur has one sample right now. Dr. Adur, can you give me that sample of Indochunite if you can highlight? Yeah. So this is a tektite which is on display in today's thing. I think they will try to show you. So these tektites, they acquire aerodynamic shape and they are spread in the region of impact. And now this whole distribution, right now it is shown to you. This is one of the tektites called Indochunites, which is found in Southeast Asia. Okay. Fair. Done. Thank you. Now, depending upon angle of impact, a distribution takes place. So normally most of the impacts, they occur at around 45 degree. So ejecta of that impact is circular. More or less it is circular around the crater. But if this impact take place at a lower angle, say 15 degrees, I have just put a stone in the background which is skimming on the water surface. So imagine a case you are throwing a stone in the water. In normal case, it will go down. But if you hit the water with a particular angle, then stone will not go down. Stone will jump off that surface and it will start bouncing. So similarly, when an impact angle is less than 15 degree, this skimming take place. Okay? This is called oblique impact. And ejecta of this impact is very different. Now, probability of such impact or a grazing impact is hardly 0.75. So 15 degree or less, it is 6.5. And less than 10 degree or 5 to 10 degree is 0.75. So this is what Schumacher has proposed. Okay. So in grazing impact, crater and distribution ejecta will be very, very unique. This we are talking to discuss about our today's subject. Australasian tektites, unsolved mystery for more than 200 years. Now, look at this map. Right from Southeast Asia to Australia, the whole material is distributed. Okay, in the sea, on the land. And the surprising part is that this is a very, very recent impact. So in the morning, whatever impact we discussed, there were some 30, 40, 50 million, 450 million year ago. Now this impact is only 0.7 billion year ago. So in human history, 7 lakh year ago. So this is a time where definitely some sort of humans were on Earth. If not Homo sapiens, at least Homo erectus का कोई species तो था. That is for sure. The crater which is expected from this is 70-kilometer large crater. So obviously, if impact is so recent and if crater is 70-kilometer crater, it should be visible. But despite of all modern technology and all the efforts, we haven't been able to identify where the crater is. Okay, now let's look at this problem in a little different way, keeping the angle of impact in mind. We are going to analyze this problem and try to understand where you can get impact site. So if you look at the distribution pattern, most of the debris is in Southeast Asia. Now there are two types of tektites you get. One is homogeneous Indochinites or similar tektites, what was just shown to you. And second is heterogeneous Myeongnong. And these Myeongnong are heavy tektites. So it is assumed that these larger tektites, wherever they are found, impact crater should be closer to that. Assuming that bigger tektites will not travel much of a distance. Because of this assumption, the whole work is, or the search for impact crater is happening in Laos, Vietnam, and these areas of Southeast Asia. So that's a problem we defined. That area of search is around Vietnam, Cambodia, because Myeongnong heavy tektites, the assumption they will not travel. Okay, but grazing impact, people are simply ignoring. That's our assumption. Grazing impact, one, leads to very elusive shape of crater. They don't produce oval shape or circular craters. They are elongated craters like some found in Mars that we will show in next few slides. Also, they ignore the fact that at oblique angle, projectile itself is getting ricocheted. So projectile fragments will continue traveling in a downrange direction of an impact at the same velocity at which a projectile has impacted, or near same velocity at which it has impacted the Earth. So thus the ejecta distribution of oblique impact is going to be very, very different. Okay. So this is a figure that simply shows at 45-degree, ejecta will be more or less circular. Okay. At lower angle, ejecta is in a narrow fan and it will have two components. One, impact melt, and second is fragments of projectile which have ricocheted. Because in normal impact, projectile generally melts. But in case of oblique impact, projectile doesn't melt. And fragments of projectile travel in the downward direction. So distribution will have two things. Plus it will also have sibling craters near the parent craters. So while studying the oblique impact, we need to have much more detailing. Now, if we look at the whole distribution pattern of Southeast Asian tektites, there are two more things. In Tibet, tektites are reported, but they are not taken into this field for some strange reason. Dr. Gangadharan has found tektites in Myanmar also. So when calculating this ejecta distribution, it is important to look at these two tektites or these two reports as well. And now if we look at, there is a possibility that this tektite field may be little upward than what people are looking at. Okay? Because in Laos, Vietnam, they have not found any crater. They are not finding any high pressure minerals. Okay? So let's look little beyond. Okay? So most of the points we have already discussed. Okay? And we are saying that right now the possibility is Tibet is a possible site for impact crater. There is a reason behind it, because to identify crater, we also depends upon high pressure minerals or glass which is found in that area. And in Tibet, many such factors are already under discussion. Question is that can Myeongdong kind of a tektite travel so much of a distance? So if we do the trajectory calculation of a projectile, assuming that Myeongdong are ricocheted fragments of projectile, and projectile is impacting at 5 degrees, 7.5 and 10 degree angle at various speed. So at 7 to 10 kilometer per second distance, these fragments can easily travel 1000 to 3500 kilometers. So current distance of Tibet from these localities of Myeongdong is in the range of 2.5 to 2000 kilometers. So safely we can say if Myeongdong are fragments, because Myeongdong are not melted. Generally tektites are complete melt of a terrestrial rock. Now Myeongdong is not a melt. Myeongdong is a heterogeneous material. So it's quite possible that Myeongdong and splash form tektites are nothing but ejecta from this impact, oblique impact. Now this is the region, this is a smoking gun. This whole section of Tibet we are proposing is a possible site. Now think about Schumacher-Levy 9. So when Schumacher-Levy 9 impacted, it created a geometric pattern. In Tibet, if you look at these lakes, it has a geometric pattern. China does heavy mining in this area. So earlier speakers have said when impact happens, you get many precious minerals. So China mines gold, China mines copper, zinc, many unique minerals from this area, and they have complete hush-hush on this subject. China has found cosite, stishovite, many impact related findings, but they keep mum on this. Now, high pressure minerals from Tibet. So if we look at the biggest sign of impact is cosite after stishovite, because that is a glass that can, or that is a form of quartz that is produced only in case of impact kind of a situation. So Tibet is known for a cosite after stishovite. You have diamonds, and these micro diamonds have OS and IR. Throughout the day, people have talked about rare platinum group mineral. They are found over here. High pressure TiO2, native form of iron, high pressure nitrides. Now, cubic boron nitride is a very unique thing which is not found anywhere in the earth. Okay, in a natural formation. It is found over here. Boron carbide, again not found anywhere on earth. It is found here in the natural environment. Now to produce this, you need a temperature which is 10 GPa and temperature of 1300 degree. It's not a normal condition. Okay. Now this is possible in the mantle at 300 kilometer. Now Tibet is a ophiolite. In simple term, this is this was a sea which was uplifted during the plate movement. Now, ophiolite is a 30-kilometer phenomenon, not a 300-kilometer phenomenon. That is the first contrast for mantle origin theory. Second, to have minerals like cubic boron nitride, at depth of 300 kilometers, there is no boron. But Tibet's surface has borax, which is a basic requirement or basic source of boron available on the surface itself. So if you look at mantle origin looks difficult. Now, if we look at a simple impact scenario where a cometary body which has ammonia, carbon dioxide, water is impacting Tibet land which has borax, it easily explains how cubic boron nitride, boron carbide were formed. It also explains how cosite and stishovite coexist with this along with microdiamond. So explanation is quite simple that there is a possibility that Tibet has faced a cometary impact. And all minerals, high pressure minerals that are required for this are present on this particular surface. So these are the equations which clearly prove how these high pressure findings can be confirmed basis the interaction with cometary body. Now, question is that if Tibet is impact site, where are the craters? Now, if we look at ejecta distribution, it clearly confirms it's a highly oblique impact. In oblique impact, don't expect circular craters. Look at craters on Mars. They are highly oblique in nature. So if you look at models also, they clearly show elongated kind of a structures rather than circular depressions. Now, if you look at various lakes in Tibet, you will realize they have some similarity. Right now, this is proposed thing. China is very secretive about any study on Tibet. They don't allow expeditions. Whatever work is done is by few of their scientists only. But if you look at all these lakes are surrounded by mines. This is a very remote area. In Indian context, to visit Mansarovar, we feel we are going to a very remote place. Now, these locations are much remoter than that. They have all the railroad network, they have all airports where people don't stay. So their commercial interest in this area is very, very high because they are getting some rare minerals. And if you look at these structures right now, they somewhat resemble. We don't want to claim because, yeah, field investigation is necessary, but minerals definitely support this logic. As we said, whenever there is oblique impact, there is also sibling craters. Now, around these lakes, if you look at other sites, these are satellite images. So you will find many smaller crater or sibling crater kind of structures around these lakes or possible impact sites. So we propose that on the basis of available data, Myeongdong tektites and oscillation tektites, it appears that the strewn field is a mix of layered tektites known as Myeongdong and splash form tektites. The distribution in narrow fan is consistent with study of oblique impact crater on Mars by Sculpts. Inclusion of FENIS. So FENI, many people have already highlighted its importance. Okay. So inclusion of FENIS and volatiles like Cl and Br along with cosites in Myeongdong support the argument that at Myeongdong may be fragments of projectile like comet. Okay. Myeongdong and other Asian tektites may be result of a highly oblique impact at an angle of 5 to 10 degree to the horizontal surface. If we look at these tektites, they have lithium and boron in abundance. Now, entire Southeast Asia can't justify lithium and boron, but Tibet has deposits to justify these inclusions. Okay. So Myeongdong restrict the search for impact to localities of like Southeast Asia of Indochina and Tibet Lake region. Presence of cosite and stishovite and other UHP minerals in Tibet Lake region, along with unconfirmed report of tektites from region, support the argument of impact in Tibet. The basic trajectory calculations are in line with current geographical spread of Myeongdong. Hence, we suggest that oblique impact in Tibet may have been responsible for tektites reported from Asia. Thank you. Any questions? Happy to address.
Well, thank you. And one of the things that I have to tell you, the Indochinite tektite, which we call it as Indochinite, Dr. Gangadhar was very specific about Indochinites.
Yes.
And Myong Nong also.
Yeah.
And then we looked at some meteorites which are called as Kimberley meteorites, which were on the border of Australia and Philippines.
Yeah.
So the observation of these meteorites is still not very well understood.
No, they are not, because the confusion.
But still, there are some questions.
Yeah.
That the meteorites which have been found there, especially on tektites, I have to emphasize on tektites for two reasons. Tektites normally don't get it so easily.
No, you don't.
So to get a tektite, it needs a different kind of an object to come down.
Yes.
So we do not have much objective on that part of it.
Okay.
And the angle part which you have been referring to as a narrow angle, according to Dr. Gangadhar, I have his thesis also with me, in which he very specifically mentions that these are Struven meteorites. Now, Struven meteorites may extend all the way from Burma, now Myanmar, to all the way to Cambodia and Laos.
Yes.
Now, meteorites are available there. They are also available in Vietnam. Now, the question of Kimberleys lie mainly in Philippines. Some part I have personally visited Indonesia. There are also some meteorites.
Yes.
But the information on that is incomplete.
Yeah.
So the best bet I have to ask you is, then why only tektites fall in this region?
Okay. So why tektites? There are 2-3 things. One, as I said, when cometary body is impacting, like Tunguska, will always remain mystery, is my opinion. I'm not as qualified as people are. But unless and until we accept the fact that comets are different class of impactors than asteroids, problem can't be solved, because one, its composition is very unique. Second, the way in which it behaves in atmosphere. Most of the scientists during my initial day, it was told to me that cometary body will get dissolved in the atmosphere. That's a myth, because if you look at Schumacher-Levy 9 event, the plume it created was around 3,000 kilometers. Jupiter also has atmosphere. So comet doesn't behave the way in which we anticipate it. Second, when cometary body impact, it is not a single crater. It is spread over a large area. Some of the material may hit Earth, and there is a possibility that some may get airburst also. So it's a mix of both. Some fragments will burst in the air, some fragments will impact. And this impact will be much over a much larger area than in the case of normal asteroid or a normal meteorite, stony or iron meteorite. So these factors are going to create a lot of complications. One, signature, since it's a low density material, signature will be maybe very bleak. That's my assumption. There are no data to prove it, because nobody has studied comet nucleus in detail. Okay, so that's one of the limitations right now we have. But yeah, we need to keep few things in mind. Disintegration before it enters the atmosphere, some airburst, some ground impact, its basic composition. It's going to create illusion. Third and most important, the velocity at which comet enters vis-a-vis asteroid. As Professor Bhandari said, asteroids generally will enter in the range of 10 to 30 kilometer. Comet will be in the range of 50 to 70. So I may be wrong, but I believe this hypervelocity plays a role in distribution of ejecta to a great extent, because the level of energy which is created on such impacts is different. So rather, a cometary model, impact model, needs more attention. And Schumacher was doing some excellent work. But after that, I don't think Skulls has done some work. But barring that, most of the models are based on a metallic or stony asteroid. That's one of the reasons why there are many unanswered questions.
Thank you once again. If there are any questions by any of our online people, it's open for discussion. And immediately after, I think my talk is last. Yeah.
I had a question.
Yeah,
I
somebody has.
cannot open my video, but I will just ask. You very nice and excellent talk. You distinguish between light and heavy type of tektites. So in this fan structure, these light and heavy type of tektites, are they all distributed in the same fan-like structure, and you attribute both of them to the same comet or different bodies?
Okay. So if you look at heavy and light, there are not only weight-wise they differ, they also differ in their composition. So heavy tektites are called Myeongdong. So generally tektites are impact melt. So it should be a homogeneous front. So what we showed you on the camera was a homogeneous tektite called Indochinite. The heavier one are not homogeneous, they are heterogeneous. It means they have not been melted sufficiently before they came back on ground. Now, this scenario, in case of impact melt, is not possible because if tektite is formed due to see when project, obviously all of you know that when projectile impacts the ground that area melts. Okay, the target as well as a projectile both. Now, once it is melted and thrown out, while coming down, they are bound to be a homogeneous thing forming glass. So all these Indochinites or oscillation tektites, they are glass. But Myeongdong are not complete glass. They are heterogeneous. It means melting has not taken place in that. That creates the doubt that oblique impact is a scenario where a projectile doesn't completely melt. Rather, some fragments of projectile keep traveling in the direction of impact, and thus distribution pattern of oblique impact will have two type of things: one, impact melt, and second, fragments of projectile. So we are proposing that Myeongdong are fragments of projectile which have some contamination of target site.
I see. Yeah. So, do these Myeongdong tektites, do they show any specific chemical signature? Because you said they are heterogeneous. I am assuming they are heterogeneous in density, in composition, and many things.
They have layered structure. So, there is a layering in those structure. So there are a few specific things rather that has raised doubt that this impact is by comet because they have high degree of volatiles. So they have chlorine and some other volatiles which are there in them. Second, they have a particular signature of FeNIS. I believe it's called Shenzungite. Now, FeNIS is a rare kind of finding. Recently, one comet, similar findings have been done of FeNIS. So these are very unique things. Plus, Myeongdong have cosites in them. Now, cosites in a body is possible only when that body has experienced a shock. Okay? Shock at a very high pressure. So again, it suggests that this is a projectile when on impact would experience the shock, but it didn't got melted. On fragmentation, these fragments kept traveling downrange, and that's the reason many of its original properties, like having volatiles, having FeNIS, were retained. But because of the shock, cosites were formed. These are my hypothesis. Nothing is proven yet. Yes, Tibet is a smoking gun because Tibet, most of the minerals can't be justified as a mantle origin. I have a complete paper on high pressure nitrides from Tibet, and till date, no one has been challenged it. Rather, people from other part who are working on it, they have just sent us the communication that we are also not denying impact, but they are not supporting impact for some strange reason.
Okay. Nice presentation. Thank you.
Sir. Thank you.
Can somebody unlock my video? Actually, it doesn't open.
Yeah, it is activated now.
Thank you. Thank you.
Are you going to present something?
No, no, not at all. I was just wondering why it is locked.
Okay, okay. So I think we don't have any further more question. We'll go to the last exciting session, or rather, I would say the most important session of the entire event by Dr. Bharat Adur, Director AGCA, that is Akash Ganga Centre for Astronomy, Badlapur. So he is going to talk on the nuclear probes to understand the meteorites. So with this, so with that note, I will welcome Dr. Bharat Adur to start his talk. Okay, meanwhile, the technician set up the presentation. I will hand over to Dr. Bharat sir. Full screen.
Yeah.
Okay.
Yeah. Good afternoon, everybody. The topic that I have chosen is a little different topic because this is actually the work done by young students. And at that point of time, I was working with Nehru Planetarium, and the work which we had started was a meteor happened to hit. I'm going to show you those images also. The images which I'm going to show you first now is a Lonar Lake. I'm going to come to that also. But what had happened is there was a meteor shower in the month of September, and one of our observers had observed this meteor observation from, I think it is from Mulund. He was able to find a very bright meteor coming down, and then it went into the east. Now, we did not have any information what had happened. But the following day, we only got a small article in Times of India stating that there was a fireball event. And nowhere they had mentioned where it could have fallen, nothing of it. So we took the lead and we decided to chase. This is a small story I want to share with you, where a senior citizen scientist, an amateur astronomer can come together and do good science. So this observation was picked up, and then we came to hear that it happened in Odisha. Now, Odisha is not a small place. It's a very large state. And it has, I think, over 16 to 17 districts, or rather more. I'm not too sure. I don't have that visual, but I would have shown you that also. But why I'm telling you this, it's just a background. So we reached Bhubaneswar. And as we came out of the Bhubaneswar station, we decided to go to GSI. There is a GSI place in Bhubaneswar. So we decided to go there. But by then, it was already 3 to 4 days beyond the meteor hit. So we took the rickshaw, and the rickshaw fellow told us the story that there was a large fireball. When that fireball happened, it was 8:30 in the night. And at 8:30, it was so bright that it looked like afternoon. And it came down with a lot of sound, crackling sound and all. And nobody knew, people ran inside the house. And then we were further given that he had to also run to a shade and stop his rickshaw and make the passenger also wait. This was the happening of a simple happening of a rickshaw driver. Now, as science people, can we just believe that and carry on? So next morning, after reaching, we went to JSI office to find out whether there was any really a fireball hit or a meteor hit. And then I think the director was very helpful, Dr. Mohanty or somebody. He helped us and showed us the meteorite sample. And immediately it was, we confirmed it that it was a chondrite. Because in chondrites, you have several features which you can see. So we were able to identify it as a chondrite. Okay. He said that the person who brought it to Kendrapada, I'll show you that picture also. And he said that it was not just one small piece, there was one larger piece also, which was brought to the GSI office and then it was deposited there. So we asked the director, after all, director of GSI knows about that place. So we asked him, where all did it fell? So he gave us half a dozen names, saying that it must have fallen here and there and there. Eventually, we reached a bus stand, an ST bus stand of Odisha, and asked the person at the station manager or whatever that he is, and he gave us all the information. He said that meteorite had not just fallen in one place, it has fallen at least in many stands around in the state. And all the places we could not travel. So then we asked him which was the place which happened and it was dangerous. And over there, amongst the people, there was a big fear. What had happened actually? I'm telling you of the local situation there. So even the bus conductor, driver, everybody was shocked. What had happened? Because there was one hut which roof got burnt and there were some people being affected by that. So, and that place was in Baran. So the station manager said, you go to Baran and you will be able to find the place. Yes, and we traveled to Baran overnight, around 800 kilometers or so. We traveled. In Baran, again, we went to the superintendent of police there and we asked him. So then he told us there is one place called Patmundai, a small town, Patmundai, and you can check with the police station there and and then see the place. So we decided, we went to that place. So I think the next slide that I'm going to show is not much relevant. I think most speakers have told you about how meteors are, what meteorites are. So can I skip this slide? Yeah. Can I skip this? Okay.
If you have any
Yeah. Now this is the place where, how do you light? We have to light. If I have to show. Light. Yeah.
You have to press it. Modi press kar nahi the. Varti. You have to keep it pressed. Screen verse press kara.
Yeah. Now the picture on my left hand side, the top picture.
नहीं आ रहा है वो सर ऊपर पकड़ रहे हैं
प्रेस करके होल्ड कर सकते हो।
नहीं, वो कंट्रोल उधर है।
नीचे और नीचे और नीचे और नीचे और नीचे। हाँ
हाँ, आया ना।
ठीक है।
तुम्हाला दिसत नाही का ते लाल मार्कर?
दिख रहा है?
नहीं दिख रहा है.
तुम्ही
So
बोला मी
anyway,
सांगतो.
the top picture on the left hand side is a paddy field. And the paddy field is a rice paddy field. So the place where I am standing down, there is the meteorite fall. So there is a meteor, sorry.
मी प्रेस करू नका, छोडो, मैं करता हूँ. You speak, sir. I'll point.
So below that is the paddy field in which we had to find out. Now, please remember one thing, the meteorite which had fallen there had gone below the ground about 30 feet. Yeah. Not 30 feet, about 15 feet. So we had carried one staff about 20 feet long to find out what was the depth of that meteorite which went. And the place was completely flooded. And where we had stopped to see that hole, we had to use that. So the lower picture, you will see a person holding the staff in the hand, and he's trying to show you the how deep it had gone. So there this was a place called as Paschim Sunit. And then there was a place called as Purab Sunit. These were two places where it had fallen. Now I'll show you further. I don't have the other one where it had went into a ground making a spiral hole. You get me? That means these fireballs, when they come in fragments, they don't just fall, they are also rotating. So when they pierce down the ground, you find that they have made some kind of vortexes. So this is what had happened in Paschim Sunit, and then we went to another crater, which was again a fallout of this, in a not a paddy field, but on the ground. And the grass was burnt. And there it went about 6 to 8 inches down. So there we were able to pick some sample. Now on the right hand side, in the right hand side, you will see that hut which was burnt. Now, how was it burnt? That the roof of that got burnt. And the people who saw the fireball was passing over the hut. And when we went after 4 or 5 days, the inmates in the house, a small girl was still crying. And it seems the person, I have not shown him particularly, I have his picture also. He was called as Nayak. He was staying in this hut. And the place where the fireball fragment fell was in a kitchen. So we saw that, and then we came to the Tehsildar there. And he's holding that sample in his hand. Now this sample is known as Kendrapada. See, nomenclature which Asana was mentioning, she's a committee member of that. So we presented this data in her meeting in Casablanca in Morocco. So at that meeting, we did discuss this and we asked, when a fireball has burnt over an area of around 33,000 square kilometers, And people in that villages were telling us when this was the fire was passing, they were finding metallic things falling over their roofs. So this fall was not seen only in one place. It was seen over a very large area. I am telling you this as a first-hand story. I am not quoting any captain or anything. So the question of saying Jagannath meteorite came to us because of that. It was not one area that we were able to pick up samples. We picked up samples here also. We picked up samples in Baran. We picked up samples in even in Panchmudia and Paschim Sunit and Purab Sunit. So then the question comes, what would be the nomenclature for that meteorite? So the best bet over there in Odisha is Jagannath. It is considered as a prime god for Jagannath. Is a prime god like in Maharashtra it is that Pandharpur, Vittala. So like that it is Jagannath there. So the people around only told us it is Jagannath's happenings. And let me tell you, when we came back to Baran, we were asked by the in charge of the police complex to give a talk. And we gave a talk on what is a fireball, what is a meteor, what is a meteorite. And mind you, the experience was beautiful. Every person down there, including the peon of that police station, came and said, "Thank you, sir. You are all shocked." So why am I trying to tell you this as a story? Is that still we have myths connected with meteors, meteorites, and meteor showers. Now, in normal term for sky gazing, also when a meteor happens, people are told you wish. I'm telling you the myths also. Now, these are the things which are prevalent, and what is required is the observation. So I want to now move to the next visual. Yeah. So what we did, we took the sample and we did not have any objective because the samples were not very large. There were small fragments in that Sutsudia, small fragments in Paschim Sunit and Purab Sunit. So we had to actually compromise of what test we should do. And this was the first time we used meteor testing in reactor, BRC reactor. So this experiment after we got so many elements. 20 major and minor and trace elements, and you will find that the similar thing for other meteorites we had compared. And hence we said that it is Jagannath meteorite. Okay, can we go to the next? Yeah. Now these meteorite samples that we have got, you will see shatter cone at Amber Lake in Lonar. Do you know where this Amber Lake is? Have you been to Lonar? Okay. If you have not been to Lonar, there is a bigger Lonar and a mini Lonar. Now, mini Lonar is next to a place called as Zoplela Maruti, Sleeping Maruti. And there you can take a magnet, but don't show it to the priest. They will not allow you to use it. But it's a lodestone. I don't want to say that word because again I will be called as Sanatan and anti-Sanatan. But the magnet or your compass, the pointer starts deflecting. Now this anyone can do, school children can do. So this is where we began for Lonar, and this is the shatter cone we found at Amber Lake. Now normally the feeling is you don't get samples. Samples don't fall from the heavens. Yes, they fall from the heavens as meteorites. They don't tell you and say, okay, I have fallen here. You have to scout for it. So what is the best scout for it? People go to Lonar as a Lonar Darshan. I'm telling you that also. Am I right, sir? Lonar Darshan. Yes, there are a lot of temples below, and all the temples have magnetic rocks. If you take your compass near any of the pole, the needle deflects. Any temple. There is one temple called as Kamalja temple, which is where we think is the meteorite. Now, why we are saying that? There is a reason. We have studied this Ambar in 2 field trips with 2 sets of school children and college boys and girls, and have scanned the whole area, the lake area, as well as the rim area. There is lake as well as rim. And I would strongly suggest all of you to go and see that. The reason being, it's one of the finest scientific meteor crater in India, and that too in basalt. And you do find, we found tektites. In fact, if you come to Badlapur, we have over 600 samples of only Lonar and 200 soil samples. Again, why I'm telling you all this is it needs study. So we did take this sample also on reactor, and the result was fantastic. We were told by BRC that you should go for a second field trip and pick up the soil. And another thing which I have to share with all of you, that when we took the first sample of Jagannath, we did not have the soil sample. So BRC was asking us, where is the soil sample? I'm telling you the technical part of it. After you take a sample, please collect the soil around. Now, this event happened in 2005 and 2011. We collected Lonar samples and we have good results. And it shows very strong platinum group elements. Now, why platinum group elements? In platinum group, we find a lot of iridium. We have heard in the morning about iridium and all these. You find there. For me, it is a living laboratory. And your type of observation, which you showed in as we have been doing it at Badlapur since 1977. It's not the first time we are doing this. We have done it for last from 77 till date. We are observing meteors, meteor streaks, then fireballs. All this is recorded. And our boys have been even recognized by the International Meteor Observers Group. So the reason here is you need a subsequent follow-up of the event year after year. It's not that this year I have seen enough. No, there is nothing enough in science. You have to keep doing it. And let me tell you, for young people, I have a persistent. एकदा बघितलं ना, that is a common statement. एकदा बघितलं ना, परत काय बघायचं? This is the statement. But every time that same meteor is not going to fall. There is another one. It is either a yellow, it is a blue, it is red. Some color specifications also come about. and nobody records it. Unfortunate part is today nobody wants to record it either on pen, pencil, or paper also. So this is where I strongly suggest why International Asteroid Day is that we must learn to log it up. If there is no logging, you never know what you have seen. Another very interesting thing that I want to tell you, that after you log, what do you do? Is the question. After you log and tabulate it proper, IMO is there to take your observation. Now, nobody says that don't send us, and they give you a certificate that you are our IMO observer. Like people who see asteroids, they get a certificate that he is an asteroid observer. Yes. You have not seen, but I'm telling you about it. But the observation which now they do it with asteroids, the observation is done somewhere in England and America. That observation is sent here for people to make claims. So people make claims. Yeah, make claims because they are not classified in their catalogs. So these are the issues which are connected. I'm sorry, I'm taking too much of your time. Can we go to the next? Yeah. Do I have to talk too much about geochemistry and detection of meteor components in impacteds? All that has been said in the morning. Do I have to repeat that? No. Okay, then we go to the next. Now, this is something interesting. We have heard about Lona Lake. We have heard about in the morning is about Ramgarh, and then there is another one in near Ramgarh. So there are, according to the history, it is 3 craters. And we have been following Luna crater from 2015. Why did we go there to Luna? Again, we had 11 people with us. See, in all these field trips, one thing which I want to strongly suggest all of us, that sitting here and talking about the topic has no meaning. One should physically get down on foot, go to those places, you can get samples. And what samples are you looking for? Mostly magnetic. So carry a magnet with you, wherein you can yourself verify whether it is a meteorite or a non-meteorite. So this is one place where now we have got a lot of samples from Luna. I have also some samples with me in Luna, and we are now again trying to do the same trick which we did in 2003, and fortunately we got a publication. And in all this, mind you, young people, when we observe, we put your names as an co-observer. So even at your first year or even at your SSC age, your publication is in record. And let me tell you, just seeing a Luna crater, you will not get anything. You have to go there and look for. And nowadays, you are so enriched with your GPS, nobody uses GPS. We show, माझ्या computer, माझ्या mobile वर आहे. As if it is a crown on your head. Then what do? Even the GPS is not used for determining the diameter of a crater. So these are the issues which one must overcome. Again, I'm not going to talk much about this slide because already people have talked about it. How pressure, I'm talking here of pascals. And you will find what all elements are possible, or rather minerals are possible. In the lower picture, you will find curves, and then you will find how the breccia appears. So it is our strongest contention that please look for samples. And samples are not, people say, oh, they have been carried away to the geology department and it is hung up with them. But you can always go and pick up. When a meteor falls, it doesn't fall just the meteor. There are fragments of it falling around. I'll give you another example. In Shirdi, Kopargaon, you have heard this name? Kopargaon in Shirdi, there was a meteor, right, coming right inside a house and falling. Now that meteorite is known by Kopargaon meteorite when it is fallen in Bojde village. So where is your nomenclature? Nomenclature, which Hasna was talking about. Where is it? Whether it is a village or whether it is a town or whether it is some unknown place, yes, you mentioned that. So these are the things which one has to be very careful to watch also. And today the technology has developed so much, I'm going to tell you young people, that you can find in two observations whole spectra. Spectra, here I am using that word, where you get, when you use neutrons and bombard it on your meteorite, it doesn't get damaged. Let me tell you. Whereas in chemical analysis, you have to crush it, then add water to it. Then for finding different samples, you need at least 5 grams. And the samples that we get is not 5 grams, it is less than that. Fortunately, I got this because Gangadhar was there. But I'm telling you what happens. So we have to look for examples or other samples which we are not able to destroy it or destruct it. So these are the contentions which one must look for. So we are now looking at a medium called as neutron activation analysis. And for that, at AGCA, at Akash Ganga Centre, we need 8 good observers. Observers means not just looking at literature and sleeping off. No. We need observers to actually analyze the data. And that data comes in a spectral form. And in that spectra, you find isotopes, you find rare earth elements, you find platinum group elements. So our hope is now to see up to what elements can we see. And in some cases, in some meteorites, people have even found uranium. Now, how does it happen in uranium, in a meteorite? Pardon? It is in parts per billion. See, when I mention this, here I am not telling you in terms of what. I'm just saying that what is available. Whether it is required or not required is not my content. I'm talking of when you use neutron activation, it depends on its own exposure time. Please remember this also. Exposure means how much the one which we used was 8 hours. 8 hours of neutron hitting the sample, we could get about 40 elements. So you can well imagine if you need more elements to come by, the exposure needs to be larger. Another thing with meteorite work is, here the sample which we give is in micrograms or milligrams. So you are not actually cutting anything. And now one more thing I am going to tell you, for which we need young people. When I mean young, it doesn't mean you are out. It means all of us. We need younger people for a simple reason of calculating the analysis which has come by. Now, analysis is not radioactive. It is a spectra. Lines where you will be seeing some graphical lines like that. And in that, you will find sodium, you will find all the elements and their isotopes. So, our ma'am, Marhas ma'am is working on isotope. So, but their method is different. They use nanosims. And here we are talking of neutron activation. Okay. So I want to quickly go further. Yeah. Again, this you need not have to worry. We have given you some idea of what thermodynamical analysis is required for finding out. You said about the angle, oblique angle, and what happens if it is perpendicular? Yeah, I'm telling you. When the meteor comes, does it decide its angle?
Trajectory.
Huh? Yeah, it is basically the material with which it is coming. And see, all the materials don't come straight from the sky because your Earth is also rotating. So even if it is coming, because of the atmosphere in the air, it is getting slanted. And that slanted gets when it starts having friction with the atmosphere. And that is where you find the burning sensation. And in these cases, you will see everywhere it is burnt. Why? It has to burn. And this is called as ablation. And this ablation actually protects the meteorite from inside. So this is what we have seen for lunar. I don't want to go into the other details, but you will see a white pattern outside, and that is called as a ejecta. Ejecta, lunar. And the white patches you see is the ejecta which has come out of that crater. And that is what you are seeing. And nearby, just on your right side, you will see another crater. And that is called a Chota Lonar or Mini Lonar. And that is where you find sleeping Maruti, Zoplela Maruti. So the reason for all this, again, we are not seeing here only one secondary one. But when you go there to the crater itself, there was not secondary one. There was secondary many. So any fragment which came out and hit the ground made a small hole. Not a great hole, small hole. But you can see it here. Sorry. Yeah. Now, I want to give you what all the features you can see here. Shatter cones are there. Our Dr. Subramanya spoke about planar, that is there. And again, what are the highest abundances in crystal? And if you see more of it, you can find that there are many more features you are able to see. Rock melts are there. Impact diamonds are there. Now, once you say diamond, everybody will run to find a diamond. But that's not the case. These diamonds, if it depends on what meteorite it was. Again, if that meteorite had a lot of carbon and a pressure of about 5 gigapascal, then probably you will find a diamond. Okay. So I think now I'll take 2 minutes from you. Now, what we intend to understand in nuclear probes is we are intending. Have you seen tomography? Electronic tomography, where your body part you can see it under different X-ray tomography, where it shows you how your liver is, how your lung is, whether there is any benign tumor or whatever. Now that we intend to do for this. To understand what is inside this, tomography for that reason. To understand, and these particles are there in the skies for millions of years or billions of years. So what all particles it has caught? Huh? It came from Indochina and Malaysia. And I'm not here to sell. And I'm trying to tell you that this is very important to. It is only for experiment that we are using. I don't take any meteorites, so-called meteorites, for testing also. So these are mainly used. So this is the one which we want to do, tomography. The idea in doing tomography is two ways. We want to see inside the meteorite whether it has caught up any elements. It could be even a particle. A cosmic ray particle can also get trapped in that. I do not know the science of that, but I am just speculating that we are trying to use this technology to understand whether we can see inside a meteorite. And this topic today, why I have taken up, is to tell people that this kind of observation is possible in India also. It's not you have to go to US or you have to go to Canada and America and all. Go and see and come. I have no problems. But this kind of work, if we can do it here in India, it will be best. So this is what I thought I will tell today's thing. And if you have any suggestions, please tell me. I think mine is the last talk. No?
Yes, yes.
Yeah. Now the hall is open for you for discussions and also for participants, online participants also.
I would like to ask a question. I'm a bit confused. The international scientific community on meteorites keeps reiterating that meteorites do not land hot. They do not start fires. They land cold because once they pass the burning phase and they've come down in altitude to say like 50 kilometers or lower, they have been cooled down by the atmosphere, and at the most they might be a little warm to the touch but never hot or on fire. But I have heard of reports made by people who've handled meteorites just as they've fallen, where they've touched them and immediately dropped them because they're hot. So I want to know what the right answer is. Can a meteorite land hot?
See,
can a meteorite start
for
a fire?
general purposes, I will answer this question. Why I'm giving you this meteorite in your hand is that you should have that, not a fear, but a feel. This is important. Until you, on the road also, you will pick up a rock. Do you just pick up any rock? No. Yeah. So when it is something different, you have to be very careful. When we go in the field, we use gloves so that they should not get any more contaminated. The objective is that. And for your information, at least we have tried looking at it Whether it has any other rays, no. No beta gamma rays come from within so far. Maybe in near future, you never know. Many of these are man-made. The radiation part is like your other technology. So, yeah, you have any questions?
No, can I just try to answer or like comment upon what you just said? Okay, maybe I can. Yeah. If I understand correctly, your question was about whether meteors would land hot or warm or cold.
Or set something on fire.
Or if they're like hot, they would bound to be doing that sort of thing. My understanding would be that it will depend on the angle of entry. If, for example, it's a grazing angle, then it has a long time in the lower atmosphere, maybe cools down to warm, or like just warm or just like touchable. Size and the angle of entry.
Like a 1 kilometer wide would definitely be burning.
It depends upon the size. The more bigger the size, the more time it will have to burn and fall and impact. Like today we are celebrating World Asteroid Day that because of the Tunguska event. It is believed, still they were not able to find anything over there, but they found that, there was shattered windows, trees were, burned or uprooted or something like that. So again, it depends upon the size and how it is.
The Chicote one that we saw in the exhibition, Chicote, when it was found on ground, it was hot. Because it all depends upon at what height it bursted and its tube. If the height at which it air bursted, the altitude is very high, then by the time it comes down, the smaller fragments may cool down. But if it is at a low altitude, you will have hot fragments because that heat is there.
Capable of setting something on fire?
Yeah,
it depends. What? Yeah. It depends, Anil, because like assume that it is a big and it is hot. And what region it is going to fall? If it is falling in the desert, if it is falling in the forest, what part of it is falling, that depends on the size. The size is the most important. And as Mahesh said, at what altitude? Okay, at what altitude it is going to fall? That is more important.
The temperature would be about a few hundred degrees Celsius at least.
Correct.
The temperature would be about 400 to 500 degrees Celsius, approximately, maybe a bit around that. Right, if that's the case, it's bound to set something at fire, but it touches paper or dry wood or bamboo huts and those kind of things.
If you try to tell some scientists from the international community this, they will totally reject your statement. They maintain that meteorites land cold. They do not land hot. They do not start fires. That's the current status. I mean, that's what they say.
Are there any questions by the online people? Please do have, if you have any queries, please ask or give. If you, another thing which we are strongly asking you is to give your suggestion and comments. Because, and do we need to have this kind of a program every year? This is also very important because this kind of a program, we are doing it at our own initiative. So if you want to continue, have this continued year after year, please tell us in advance so that we can plan it well in.
One question is here. Question about lunar meteorite samples and other places. Are they typically found on surface or need to actuate at a few inches or feet?
No, I'm not. I'm sorry. I did not get your question right. Who is speaking?
Questions about
Anurag Shevde.
So the question is from Anurag Shevade. The question is, about lunar meteorite samples and other places. Are they typically found on surface or need to excavate a few inches or feet?
You want to answer?
Yes, yes. Do we need to dig
See,
or we get it on
yeah,
the surface?
one of the queries which I have is where, see, all the meteorites which fall, they fall at different times of the year. Rather, every month you should be able to find some meteor dust at least falling on Earth. But the amount of it is not really, one can see it only when you have some kind of a heavy meteorite which falls. Yeah, it does make some crater and it creates, but the depth of it is depending on the density of that particular meteorite. If the meteorite is an iron meteorite, it is as good as putting a shot put. If you are throwing a shot put in a vertical direction and then it falls, yeah, it will give you a round. If it is a muddy ground, it will give you a muddy crater impact. Similarly, if you use it at an angle, it will show you some kind of an ellipsoid. So, where the meteorite falls depends at what angle it has fallen. Even this lunar crater has an angle of I think around 27 degrees. Huh? So it has also an angle. So these meteorites which have fallen, normally they fall obliquely. They don't fall vertically down. So this is one thing which I can share with you. And then in Luna, again there is, you find a very small inlet. So these possibilities, when something falls from the sky, it depends on many things, including Earth's rotation also you should consider.
In fact, in the desert like Morocco, Rajasthan, or Sahara, where you actually find them lying on the surface of the desert. Which reminds me of this amazing fireball network in Australia run by the Curtin University. They call the Desert Fireball Network. Dr. Hasna had mentioned something about them. They have used drones to scour the desert. So they use many drones, and each drone has an assigned block. They have cameras with algorithms, with running AI to detect something black on a white surface. And even if it's really small, the camera will report back. The camera is fitted on the drone. And they'll scan the whole desert and they're making recoveries. We have a desert here in Rajasthan. We should be doing the same thing.
Yeah. I think the question is an open question, so one can answer.
Yeah, that basically can be used, but again, it depends. I mean, the drones itself is expensive thing as of now, and what technology you're talking about is the multispectral payloads which needs to be used, and uh, whatever you're talking about is AI, because every day you scan, you have a data back of yesterday's. If there is any change in pattern or layout, that will actually tell them that okay, there is something different is there, and then they will probably investigate and collect all those samples. But again, if you see meteors, if till yesterday there was no meteor and today it fall, then the possibility of finding it is much easier. But if what about those meteors which were lying over their years, which will be most of the time get covered by the ground because of the sand dunes and all the things. So there you need to use the special techniques of finding the meteors, which Bharat sir is already aware, like magnets or metal detectors and all those kind of things.
Yeah, but if we had a nationwide camera
Yeah,
network,
correct.
meteor camera network, It would be beautiful. We would make so
Yeah,
many
yeah.
recoveries. We would know what happened. Now, nobody is sure about what happened in 1908 in Tunguska. Nobody has
Nobody
evidence.
has, correct.
Nobody had cameras back then. We are still in 1908, I would say so. 100 years later, we don't have a camera. It's a shame. We need to start a camera network all over the country. If they had it back in 1908, they would have known what happened in Tunguska. If Tunguska happens again out here, we won't know because there are no cameras.
Right, right. Absolutely right. That is why we actually trying to, set up our own network and see how it can become more easy to build from a student perspective. And we want to take it to the schools and colleges as a project. So at least every school, every college should put up on their rooftop, because they have internet, they have a network, everything, and then they have a student, and basically this will fuel the scientific, expedition kind of thing, and doing research on that perspective. So, like, assume like at least every 1 kilometer, every school you will have so much a big network, at least in Mumbai. That is what we are starting to begin. That's why when we were having lunch, I said that at least by end of this year, I'm planning to have at least 2 to 4 cameras set up. And if that is successful, then multiplying it will not be a challenge, because by the time we'll have the overall understanding and taking it really to the schools and colleges as a project, as a something which students would like to do year on year and all the things. Anyone else has any other question? I think once on the field, apart from the metal detector, any other instrument used?
Hello.
So apart from metal detectors, any other instruments people use for hunting meteorites? Magnets?
Yeah. Can I say something?
Yeah,
here?
please.
Let me tell you, in Luna, we did try to use metal detectors to look for meteorites under the ground.
Luna or lunar?
Huh?
Luna or lunar?
No.
Where do you use metal?
Luna.
Luna in Gujarat. Yeah, Gujarat.
Yeah, it's a dry area.
It's a dry area.
No, not in the water. There is no water.
There is no water. It's a dry.
It's a dry land.
Luna.
So in the dry land, we did try to use metal detectors for detecting samples. And we did get samples. Yeah. And in the West, I mean in the Europe, they have larger metal detectors. So here the metal detectors that are there is generally to look for metals like rings and all that which fall in the ground, to pick up that. But mind you, even that is good enough.
Yeah.
You can see even a ring or a golden ring which falls 6 inch below or 8 inch below the ground. You can pick up. So we use this to detect meteorites by using a metal detector. Now the metal detector's frequency, what we had to modulate, which we cannot do right now, but we are looking at that possibility to change the from kilohertz to at least 1 to 5 megahertz, so that we can go deeper into the ground. So this is one set of technique we are trying. We are not very much successful, but we are sure that we'll find how deep we can go. So metal detector is yeah, there are ground penetrating radars also. Yeah, but see, radars they are not mobile. You have to fix it at one place or keep that place once and look around. But here we are trying to have a mobile detector. See, electronics guy, everything is. You are also electronics guy. You also fit up electronics thing.
See, basically what we can do is what you said about the drones. There are payloads which are getting developed. and these drones will be flying and they will taking. So
And
a
here
lot
we
of
need-
technology is getting developed in the drones experiment, where you can use your lidars, your multispectral, hyperspectral cameras and all that things, and which will give you the complete layout and lot of things. So eventually, maybe down the line, 5 or 10 years, we might have something which would able to get that kind of details.
Can I add something on this? Okay, I'd just like to add a small trivia here about this same context. Something maybe like some kids watching can probably do some fun with. I was just trying with my phone. There's a magnetometer on my phone, right? Every phone has it. I mean, you have a small coil at the back, which you use for NFC and those things. That also acts like a magnetometer. So there are apps available. You can just use a Compass app or a magnetometer app on the phone and try. I tried this meteorite and the Moroccan sample. And I found that both of them, when I went in many different ways on both the samples, this guy didn't show any deflection. I mean, there was no magnetism as per this detector, whereas the other sample showed about 10 microtesla. So it could show about 10 microtesla. That's a very small amount. I mean, a very small field, and it's a very small instrument. But yeah, if you have a little bit of better one, yeah, exactly. So, right. So I was just like wondering, like, if you do take a magnetometer, a big one, and go over Lake Luna, for example, you may still miss many of the meteorites. Right, but it's a small fun thing for kids to try out and see how rocks respond to various things on the phone itself, right? You can always build a bigger one, but yeah.
There is one question is, what is the current state of development of the subject of finding underwater impact sites? Underwater impact sites.
Yeah. For
Mike.
For underwater, there are seismometers which are available for underwater also to find out gravity anomalies. So that is one possibility is there. The best way to detect for this is to go to Indian Institute of Petroleum. They have the piles of the Bombay gas. You can get the piles and then look for the KT blocks in that. So one of the experiments which was done on these piles was by an Indian American from there, and he did ask me whether one can go to Indian Institute of Petro, where they keep these samples. So that is one possibility for even looking for petroleum. What you can call is petroleum logs, what they pick up from the seabeds. So this is one way of looking at seabed meteorites. Even in Chicxulub, they have done that. So that is how they could find it out that it is a meteoric. Huh? Yeah. 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 Yeah, there are some questions. I think Pratik wants to ask some question. Pratik
is saying
are you there?
LiDAR can be used to detect the underwater impact structures. Yes, LiDAR can be also used.
Anyone?
Can probably work from satellites in space.
Yeah.
No, not required. Even drones can also use.
Yeah, okay, yeah.
So
there are some more questions if you scroll down.
No, that is the last question. LiDAR was the last.
Yeah, but before that, there was some.
In the Meteor camera system shown earlier, how does the data reduction method of differentiate between ever-increasing satellite trails during the affected hours and Meteor trails? In other words, are individually exposure very short to know if it is a short meteor or a satellite? You want to take up this question, Ravi?
Yeah.
Can you read that?
So
question?
basically, he is asking, how do you reduce the size? Because amount of data what you will be collecting will be huge. So how will you differentiate between?
Yeah, how do you make out the satellite from the meteor trail?
Okay, a satellite would take about 4-5 minutes to cross your horizon.
Correct.
A meteor would take a few seconds. Now, you also see satellite flares. Now, satellite flares barely last 3-4 seconds. and they are slower moving than meteors. Any orbital object which is man-made, like space junk or a satellite or a rocket, is up in a Earth orbit, traveling at 7.6 kilometers per second in low Earth orbit. But a meteor reaching low Earth orbit would be like between 15 to 45 kilometers per second to 60 kilometers per second. So definitely you can easily tell. It takes a little of practice. Once you've got your meteor station running, you can learn to differentiate between satellites, rockets, satellite flare, meteors, fireballs, mosquitoes, planes, birds, drones. So you spend 1 month with the system and you become an expert. But please start the system. Did that answer your question?
If you are ending, can I just add something here? Association basically for next year. I was thinking like if we can rope in more students of this age, like Okay. Yeah. Okay. So I was thinking that how we can use up. I mean, how we can rather organize a program. So, for example, if we have activities, around schools, maybe few days before the program, this day, or maybe on this day itself, and we organize this in a school rather than like NSC or some other place. I can offer my school for that. It's in Dombivli, but you can always have it. And we get the children to actually, not just see the meteorites, but experiment with them at a very basic level where they don't destroy the meteorite. But from the upfront, like magnetometers, for example, or other things, they just play around with that, learn the properties, or they can use some of your data to see can they spot the meteor in among, say, 1,000 frames. Just like a quick activity for them, and that will really rope them into the thing. They can start doing their own projects after that. But maybe we should do more of this rather than just have talks and a lot of tech stuff. Anyway, this an idea. That's my problem. I can do that. So if you do it in school, like for example, my school, for example, I can have 100 people there from everywhere, or maybe more than that. Yeah. Okay, so are we winding up, Magesh?
Yeah.
Yep.
The sample collected, I think it should be collected from Lonar Lake showing magnetic nature can be treated as a part of meteor. Yeah. Basically, if it is showing a magnetic phenomena, so I think then it should be treated as a meteor. But still, it needs further validation and all the things to really call it as a meteor. I mean, that could be the first level of understanding that it could be a meteor.
Yes, but that's not the only criteria. There should be other supporting criteria like regmaglyphs, flow lines, fusion crust.
It's sensible to use electric resistivity to detect the subsurface object. I mean, you can test it out from a metallic thing like, the multimeter to check whether it is showing you conductivity or something like that. To just first level. These are all very basic level, just to make sure that whether you are falling into that criteria or not. No, I'm not saying. अमित और कुछ क्वेश्चन है क्या? और ये ना अमित, ये जो चैट है ना, चैट वो हमको मेल कर देना. I think if we do not have any other questions, I think we should conclude this today's event over here. Just wait for 2 minutes. So I think, sir, we should conclude it. You want to conclude? We can conclude now. There is no more questions. अमित एक वहां से फोटो लोगे क्या? You take my camera. Just come little bit closer. इसको नीचे.
Now to conclude, we hope to meet again next year on June 30th, 2025. I do not know whether we can have it at Nehru Science Centre, or if people elsewhere want to take this activity even in their city, we are welcome. You are welcome to take it. We will, whatever help we can give you, definitely we will try to give you that. And please do comment and give your suggestion how you would like to have Asteroid Day meeting at your premises, and whether we should continue to have it every year here at least Nehru Science Centre, or in your place. If you want to do it, we will give you all the resource persons, everything, and you can conduct it. And another thing which I strongly would like to tell all the geology departments in the, not only in our states in all over the country, to start taking these activities to their respective departments. And we can definitely help them in conducting these programs over in their city also, or even in their town or wherever they are. We'll definitely like to encourage this kind of an activity. Most, even in, to give you one fact, for doing even nuclear probe research, we do need, BRC needs people to do this kind of work. So again, through your columns, I have been told by even Professor Maras that they have on November, they have a program in Ahmedabad PRL. They have a program on meteors, meteorites in their place. And she has asked me to convey this to all of you, that we should take part in their program also. And for us, it's a very good opening. And I thank all the participants online as well as offline, and for also Nehru's Science Center technicians, particularly, who have been with us for all the whole day's sessions. Thank you.
Thank you, Amit. Thank you.
And most important and very, I have to convey this to Dr. Umesh Rastogi, the director of Nehru Science Center, who readily agreed to have this meeting in this premises. Now we will be having this for the fourth time, and hope we continue to have such programs in future also, wherein we are able to show you meteorites, we make available our sources so they can talk to you, and let us have an open dialogue and discuss. Even I have suggested in one of my reply to all of you that we are contemplating to start short certificate courses. If people are interested in particular subjects, say for example, how to make petri dish, petrographic slide. This is normally available in a geology lab, but of late people even don't have an idea how to make petrography slide. So this is one reason we want to do. Similarly, newer instruments have come. For example, scanning electron microscope. One can start looking at how to work on a scanning electron microscope. They need good technicians to run these advanced equipments. What we call them advanced, for them it becomes a regular feature later. But definitely they need people to run these instruments. And finally, I would also like to thank our foreign friends, Professor Hasna. Yeah, she was a bit late, but I think she gave a very good talk. And also, all the speakers, in fact, the speakers who came from right from Professor Narendra Bhandari, he is our mentor actually. Still, he said that after this his program, he had to go somewhere, but he said, "No, in morning I am going to keep it for you." And all the speakers who we had from Geological Survey of India or ex Mangalore University. So all of them have given us very good support, and we are really very thankful to our speakers. And last but not the least, our good online people who attended the program, we cannot forget them. So I strongly suggest you, please give us your opinions, your suggestions. We are open. We do not have any bureaucracy in that. We are open for any ideas. We are, in fact, going to suggest to all the people who are from the uh, other institutes to see if they can start smaller, even X-ray, how to be an X-ray technician. Even in hospitals, they need X-ray technicians, and even for dental, they need X-ray technicians. So, like that, in different subjects, if you think we need short courses, you can definitely suggest us. Even I would go to the extent that I will also speak to people at BRC whether for their AC reactor also is a specialized line. And for that, also one needs reactor technicians. So it's just not the scientist only or this. We need also such supportive staff for that, and they should be also trained into taking up newer and newer tasks. So I once again would like to thank all of you because we have to wind up by 6 o'clock because Nehru Science Center has a time limit of 6 o'clock. So, with that, thank you and namaskar to all of you. Thank you, sir.
Thank you, everyone. Thanks for the session.
Record